Real-time data has been growing rapidly over the last few years, majorly because of the internet, social media platforms, website traffic, sensors, online transactions, and many more. Storing, processing, and analyzing these vast volumes of data was a major challenge until Apache Spark came into existence. Hi guys, welcome to this complete Apache Spark tutorial by Simplilearn. Apache Spark is an open source data processing engine to store and process data in real time across various clusters of computers using various programming constructs. But before we begin, make sure to subscribe to our channel and hit the bell icon to never miss an update. In this video, you will learn what really Apache Spark is, the architecture of Apache Spark, and how to install Spark on Windows and Ubuntu. Then, you will understand in detail about the various components of Spark, such as Spark Streaming, Spark MLlib, and Spark SQL. You will also get an idea of analyzing data using PySpark with the help of a hands-on demo. Finally, we will look at the important interview questions in Apache Spark. Now let's first look at a small animated video to understand big data in 5 minutes.
We all use smartphones, but have you ever wondered how much data it generates in the form of texts, phone calls, emails, photos, videos, searches, and music? Approximately 40 exabytes of data gets generated every month by a single smartphone user. Now, imagine this number multiplied by 5 billion smartphone users. That's a lot for our mind to even process, isn't it? In fact, this amount of data is quite a lot for traditional computing systems to handle. And this massive amount of data is what we term as big data. Let's have a look at the data generated per minute on the internet. 2.1 million snaps are shared on Snapchat. 3.8 million search queries are made on Google. 1 million people log on to Facebook. 4.5 million videos are watched on YouTube. 188 million emails are sent. That's a lot of data. So, how do you classify any data as big data? This is possible with the concept of 5 V's: volume, velocity, variety, veracity, and value. Let us understand this with an example from the healthcare industry. Hospitals and clinics across the world generate massive volumes of data. 2,314 exabytes of data are collected annually in the form of patient records and test results. All this data is generated at a very high speed, which attributes to the velocity of big data. Variety refers to the various data types, such as structured, semi-structured, and unstructured data. Examples include Excel records, log files, and X-ray images. Accuracy and trustworthiness of the generated data is termed as veracity. Analyzing all this data will benefit the medical sector by enabling faster disease detection, better treatment, and reduced cost. This is known as the value of big data. But how do we store and process this big data? To do this job, we have various frameworks such as Cassandra, Hadoop, and Spark. Let us take Hadoop as an example and see how Hadoop stores and processes big data. Hadoop uses a distributed file system known as Hadoop Distributed File System to store big data. If you have a huge file, your file will be broken down into smaller chunks and stored in various machines. Not only that, when you break the file, you also make copies of it, which goes into different nodes. This way, you store your big data in a distributed way and make sure that even if one machine fails, your data is safe on another. MapReduce technique is used to process big data. A lengthy task A is broken into smaller tasks, B, C, and D. Now, instead of one machine, 3 machines take up each task and complete it in a parallel fashion and assemble the results at the end. Thanks to this, the processing becomes easy and fast. This is known as parallel processing. Now that we have stored and processed our big data, we can analyze this data for numerous applications. In games like Halo 3 and Call of Duty, designers analyze user data to understand at which stage most of the users pause, restart, or quit playing. This insight can help them rework on the storyline of the game and improve the user experience, which in turn reduces the customer churn rate. Similarly, big data also helped with disaster management during Hurricane Sandy in 2012. It was used to gain a better understanding of the storm's effect on the east coast of the U.S., and necessary measures were taken. It could predict the hurricane's landfall 5 days in advance, which wasn't possible earlier. These are some of the clear indications of how valuable big data can be once it is accurately processed and analyzed. So, here's a question for you. Which of the following statements is not correct about Hadoop Distributed File System, HDFS? A. HDFS is the storage layer of Hadoop. B. Data gets stored in a distributed manner in HDFS. C. HDFS performs parallel processing of data. D. Smaller chunks of data are stored on multiple data nodes in HDFS. What do you think will be the most significant impact of big data in the future? Let us know in the comments below. If you enjoyed this video, it would only take a few seconds to like and share it. Also to subscribe to our channel if you haven't yet, and hit the bell icon to get instant notifications about our new content. Stay tuned and keep learning.
I hope you're excited to learn more about big data and Spark. Now we have Ajay who will take you through this journey of learning Apache Spark in detail. With that, over to you, Ajay.
Welcome to this tutorial on Apache Spark, one of the most in-demand technologies and processing frameworks in the big data world. And here we will learn on Apache Spark, history of Spark, what is Spark, Hadoop, which is a framework again, WES Spark, components of Apache Spark, that is Spark Core, Spark SQL, Spark Streaming, Spark MLlib, and graphics. Then we will learn on Spark Architecture, applications of Spark, Spark use cases. So let's begin with understanding about history of Apache Spark. It all started in 2009 as a project at UC Berkeley AMP Labs by Mate Zaharia. In 2010, it was open sourced under a BSD license. In 2013, Spark became an Apache top-level project, and in 2014, used by Databricks to sort large-scale datasets, and it set a new world record. So that's how Apache Spark started, and today it is one of the most in-demand processing framework, or I would say in-memory computing framework, which is used across the big data industry. So what is Apache Spark? Let's learn about this. Apache Spark is an open source in-memory computing framework, or you could say data processing engine, which is used to process data in batch and also in real time across various cluster computers. And it has a very simple programming language behind the scenes, that is Scala, which is used. Although if users would want to work on Spark, they can work with Python, they can work with Scala, they can work with Java, and so on, even R for that matter. So it supports all these programming languages, and that's one of the reasons that it is called polyglot, wherein you have good set of libraries and support from all the programming languages, and developers and data scientists incorporate Spark into their applications or build Spark-based applications to process, analyze, query, and transform data at a very large scale. So these are key features of Apache Spark. Now, if you compare Hadoop WES Spark, we know that Hadoop is a framework, and it basically has MapReduce, which comes with Hadoop for processing data. However, processing data using MapReduce in Hadoop is quite slow because it is a batch-oriented operation and it is time-consuming. If you talk about Spark, Spark can process the same data 100 times faster than MapReduce, as it is a in-memory computing framework. Well, there can always be conflicting ideas saying, what if my Spark application is not really efficiently coded and my MapReduce application has been very efficiently coded? Well, then it's a different case. However, normally, if you talk about code which is efficiently written for MapReduce or for Spark-based processing, Spark will win the battle by doing almost 100 times faster than MapReduce. So as I mentioned, Hadoop performs batch processing, and that is one of the paradigms of MapReduce programming model, which involves mapping and reducing, and that's quite rigid. So it performs batch processing. The intermittent data is written to SDFS and read back from SDFS, and that makes Hadoop's MapReduce processing slower. In case of Spark, it can perform both batch and real-time processing. However, a lot of use cases are based on real-time processing. Take an example of Macy's, take an example of retail giant such as Walmart, and there are many use cases who would prefer to do real-time processing, or I would say near real-time processing. So when we say real-time or near real-time, it is about processing the data as it comes in, or you're talking about streaming kind of data. Now, Hadoop or Hadoop's MapReduce obviously was started to be written in Java. Now you could also write it in Scala or in Python. However, if you talk about MapReduce, it will have more lines of code since it is written in Java, and it will take more times to execute. You have to manage the dependencies, you have to do the right declarations, you have to create your mapper and reducer and driver classes. However, if you compare Spark, it has few lines of code as it is implemented in Scala, and Scala is a statically typed, dynamically inferred language. It's very, very concise, and the benefit is it has features from both functional programming and object-oriented language. And in case of Scala, whatever code is written, that is converted into bytecodes, and then it runs in the JVM. Now, Hadoop supports Kerberos authentication. There are different kind of authentication mechanisms. Kerberos is one of the well-known ones, and it can really get difficult to manage. Now, Spark supports authentication via a shared secret. It can also run on Yarn, leveraging the capability of Kerberos. So what are Spark features which really makes it unique or in-demand processing framework? When we talk about Spark features, one of the key features is fast processing. So Spark contains resilient distributed datasets. So RDDs are the building blocks for Spark, and we'll learn more about RDDs later. So Spark contains RDDs, which saves huge time taken in reading and writing operations. So it can be 100 times, or you can say 10 to 100 times faster than Hadoop. When we say in-memory computing, here I would like to make a note that there is a difference between caching and in-memory computing. Think about it. Caching is mainly to support read-ahead mechanism where you have your data preloaded so that it can benefit further queries. However, when we say in-memory computing, we are talking about lazy evaluation. We are talking about data being loaded into memory only and only when a specific kind of action is invoked. So data is stored in RAM. So here we can say RAM is not only used for processing, but it can also be used for storage. And we can again decide whether we would want that RAM to be used for persistence or just for computing. So it can access the data quickly and accelerate the speed of analytics. Now, Spark is quite flexible. It supports multiple languages, as I already mentioned, and it allows the developers to write applications in Java, Scala, R, or Python. It's quite fault tolerance. So Spark contains these RDDs, or you could say execution logic, or you could say temporary data sets, which initially do not have any data loaded, and the data will be loaded into RDDs only when execution is happening. So these can be fault tolerant as these RDDs are distributed across multiple nodes. So failure of one worker node in the cluster will really not affect the RDDs because that portion can be recomputed. So it ensures loss of data. It ensures that there is no data loss, and it is absolutely fault tolerant. It is for better analytics. So Spark has rich set of SQL queries, machine learning algorithms, complex analytics, all of this supported by various Spark components, which we will learn in coming slides. With all these functionalities, analytics can be performed better in terms of Spark. So these are some of the key features of Spark. However, there are many more features which are related to different components of Spark, and we will learn about them. So what are these components of Spark which I'm talking about? Spark Core. So this is the core component, which basically has RDDs, which has a core engine, which takes care of your processing. Now you also have Spark SQL. So people who would be interested in working on structured data or data which can be structurized would want to prefer using Spark SQL. And Spark SQL internally has components or features like data frames and data sets, which can be used to process your structured data in a much faster way. You have Spark Streaming. Now that's again an important component of Spark, which allows you to create your Spark streaming applications, which not only works on data which is being streamed in or data which is constantly getting generated, but you could also transform the data. You could analyze or process the data as it comes in smaller chunks. You have Spark's MLlib. Now this is basically a set of libraries which allows developers or data scientists to build their machine learning algorithms so that they can do predictive analytics or prescriptive, descriptive, preemptive analytics, or they could build their recommendation systems or bigger, smarter machine learning algorithms using these libraries. And then you have graphics. So think about organizations like LinkedIn or say Twitter, where you have data which naturally has a network kind of flow. So data which could be represented in the form of graphs. Now here when I talk about graphs, I'm not talking about pie charts or bar charts, but I'm talking about network related data. That is data which can be networked together, which can have some kind of relationship. Think about Facebook, think about LinkedIn, where you have one person connected to other person or one company connected to other company. So if we have our data which can be represented in the form of network graphs, then Spark has a component called GraphX, which allows you to do graph-based processing. So these are some of the components of Apache Spark: Spark Core, Spark SQL, Spark Streaming, Spark MLlib, and graphics. So to learn more about components of Spark, let's learn here about Spark Core. Now this is the base engine, and this is used for large-scale parallel and distributed data processing. So when you work with Spark, at least and the minimum you would work with is Spark Core, which has RDDs as the building blocks of your Spark. So it is responsible for your memory management, your fault recovery, scheduling, distributing, and monitoring jobs on a cluster, and interacting with storage systems. So here I would like to make a key point that Spark by itself does not have its own storage. It relies on storage. Now that storage could be your SDFS, that is Hadoop's distributed file system. It could be a database like NoSQL database such as HBase, or it could be any other database, say RDBMS, from where you could connect your Spark and then fetch the data, extract the data, process it, analyze it. So let's learn a little bit about your RDDs, resilient distributed datasets. Now Spark Core, which is the base engine or the core engine, is embedded with the building blocks of Spark, which is nothing but your resilient distributed dataset. So as the name says, it is resilient. So it is existing for a shorter period of time, distributed. So it is distributed across nodes. And it is a data set where the data will be loaded or where the data will be existing for processing. So it is immutable, fault tolerant, distributed collection of objects. So that's what your RDD is. And there are mainly two operations which can be performed on an RDD. Now to take an example of this, say I want to process a particular file. Now here I could write a simple code in Scala, and that would basically mean something like this. So if I say val, which is to declare a variable, I would say val x, and then I could use what we call as Spark Context, which is basically the most important entry point of your application. So then I could use a method of Spark Context, for example, that is text file, and then I could point it to a particular file. So this is just a method of your Spark Context, and Spark Context is the entry point of your application. Now here I could just give a path in this method. So what does this step do? It does not do any evaluation. So when I say val x, I'm creating an immutable variable, and to that variable I'm assigning a file. Now what this step does is it actually creates a RDD, resilient distributed dataset. So we can imagine this as a simple execution logic, a empty dataset which is created in memory of your node. So if I would say I have multiple nodes in which my data is split and stored, imagining that your Spark is working with Hadoop. So I have Hadoop which is using say 2 nodes, and this is my distributed file system SDFS, which basically means my file is written to HDFS, and it also means that the file related blocks are stored in the underlying disk of these machines. So when I say val x equals sc.text file, that is using a method of Spark Context. Now there are various other methods like whole text files, parallelize, and so on. This step will create an RDD. So you can imagine this as a logical data set which is created in memory across these nodes, because these nodes have the data. However, no data is loaded here. So this is the first RDD, and I can say first step in what we call as a DAG. A DAG which will have series of steps which will get executed at later stage. Now later I could do further processing on this. I could say val y, and then I could do something on x. So I could say x dot map, and I would want to apply a function to every record or every element in this file, and I could give a logic here, x.map. Now this second step is again creating an RDD, a resilient distributed data set. You can say second step in my DAG, okay? And here you have a external RDD, one more RDD created, which depends on the first RDD. So my first RDD becomes the base RDD or parent RDD, and the resultant RDD becomes the child RDD. Then we can go further, and we could say val z, and I would say, okay, now I would want to do some filter on y. So this filter which I am doing here, and then I could give a logic. Might be I'm searching for a word, I'm searching for some pattern. So I could say val z equals y.filter, which again creates one more RDD, a resilient distributed data set in memory. And a, you can say this is nothing but one more step in the DAG. So this is my DAG, which is a series of steps which will be executed. Now here, when does the execution happen? When will the data get loaded into these RDDs? So all of this, that is using a method, using a transformation like map, using a transformation like filter or flat map or anything else, these are your transformations. So the operations such as map, filter, join, union, and many others will only create RDDs, which basically means it is only creating execution logic. No data is evaluated, no operation is happening right now. Only and only when you invoke an action, that is, might be you want to print some result, might be you want to take some elements and see that, might be you want to do a count. So those are actions which will actually trigger the execution of this DAG right from the beginning. So if I here say z dot count, where I would want to just count the number of words which I'm filtering, this is an action which is invoked, and this will trigger the execution of DAG right from the beginning. So this is what happens in a Spark. Now if I do a z.count again, it will start the whole execution of DAG again right from the beginning. So my z.count, second time an action is invoked, again the data will be loaded in the first RDD, then you will have map, then you will have filter, and finally you will have result. So this is the core concept of your RDDs, and this is how RDD works. So mainly in Spark, there are two kinds of operations. One is your transformations and one is your actions. Transformations, or using a method of Spark context, will always and always create an RDD, or you could say a step in the DAG. Actions are something which will invoke the execution, from the first RDD till the last RDD where you can get your result. So this is how your RDDs work. Now, when we talk about components of Spark, let's learn a little bit about Spark SQL. So Spark SQL is a component, a processing framework, which is used for structured and semi-structured data processing. So usually people might have their structured data stored in RDBMS or in files where data is structured with particular delimiters and has a pattern. And if one wants to process this structured data, if one wants to use Spark to do in-memory processing and work on this structured data, they would prefer to use Spark SQL. So you can work on different data formats, say CSV, JSON. You can even work on smarter formats like Avro, Parquet, even your binary files or sequence files. You could have your data coming in from an RDBMS, which can then be extracted using a JDBC connection. So at the bottom level, when you talk about Spark SQL, it has a data source API, which basically allows you to get the data in whichever format it is. Now, Spark SQL has something called as data frame API. So what are data frames? Data frames, in short, you can visualize or imagine as rows and columns, or if your data can be represented in the form of rows and columns with some column headings. So data frame API allows you to create data frames. So like my previous example, when you work on a file, when you want to process it, you would convert that into an RDD using a method of Spark context or by doing some transformations. So in the similar way, when you use data frames or when you want to use Spark SQL, you would use Spark's context, which is SQL context or Hive context or Spark, which allows you to work with data frames. So like in my earlier example, we were saying val x equals sc.text file. Now in case of data frames, instead of sc, you would be using, say, Spark dot something. So Spark context is available for your data frames API to be used. In older versions like Spark 1.6 and so on, we were using Hive context or SQL context. So if you were working with Spark 1.6, you would be saying val x equals SQL context dot. Here we would be using Spark dot. So data frame API basically allows you to create data frames out of your structured data, which also lets Spark know that data is already in a particular structure. It follows a format, and based on that, your Spark's backend DAG scheduler, right? So when I say about DAG, I talk about your sequence of steps. So Spark is already aware of what are the different steps involved in your application. So your data frame API basically allows you to create data frames out of your data. And data frames, when I say, I'm talking about rows and columns with some headings. And then you have your data frame DSL language, or you can use Spark SQL or Hive query language. Any of these options can be used to work with your data frames. So to learn more about data frames, follow in the next sessions. When you talk about Spark streaming, now this is very interesting for organizations who would want to work on streaming data. Imagine a store like Macy's, where they would want to have machine learning algorithms. Now, what would these machine learning algorithms do? Suppose you have a lot of customers walking in the store and they are searching for particular product or particular item. So there could be cameras placed in the store, and this is being already done. There are cameras placed in the store which will keep monitoring in which corner of the store there are more customers. Now, once camera captures this information can be streamed in to be processed by algorithms, and those algorithms will see which product or which series of product customers might be interested in. And if this algorithm in real time can process based on the number of customers, based on the available product in the store, it can come up with a attractive alternative price, so that which the price can be displayed on the screen and probably customers would buy the product. Now this is a real-time processing where the data comes in, algorithms work on it, do some computation and give out some result, and which can then result in customers buying a particular product. So the whole essence of this machine learning and real-time processing will really hold good if and when customers are in the store. Or this could relate to even an online shopping portal where there might be machine learning algorithms which might be doing real-time processing based on the clicks which customer is doing. Based on the clicks, based on customer history, based on customer behavior, algorithms can come up with recommendation of products or better altered price so that the sale happens. Now, in this case, we would be seeing the essence of real-time processing only in a fixed or in a particular duration of time. And this also means that you should have something which can process the data as it comes in. So Spark Streaming is a lightweight API that allows developers to perform batch processing and also real-time streaming and processing of data. So it provides secure, reliable, fast processing of live data streams. So what happens here in Spark Streaming in brief? So you have an input data stream. Now that data stream could be a file which is constantly getting appended. It could be some kind of metrics. It could be some kind of events based on the clicks which customers are doing or based on the products which they are choosing in a store. This input data stream is then pushed in through a Spark Streaming application. Now Spark Streaming application will break this content into smaller streams, what we call as discretized streams, or batches of smaller data on which processing can happen in frames. So you could say, process my file every 5 seconds for the latest data which has come in. Now there are also some Windows based options. Like when I say Windows, I mean a window of past 3 events. Window of past 3 events, each event being of 5 seconds. So your batches of smaller data is processed by Spark engine, and this processed data can then be stored or can be used for further processing. So that's what Spark Streaming does. When you talk about MLlib, it's a low-level machine learning library that is simple to use, scalable, and compatible with various programming languages. Now, Hadoop also has some libraries, like you have Apache Mahout, which can be used for machine learning algorithms. However, in terms of Spark, we are talking about machine learning algorithms which can be built using MLlib's libraries, and then Spark can be used for processing. So MLlib eases the deployment and development of scalable machine learning algorithms. I mean, think about your clustering techniques. So think about your classification, where you would want to classify the data, where you would want to do supervised or unsupervised learning. Think about collaborative filtering and many other data science related techniques or techniques which are required to build your recommendation engines or machine learning algorithms can be built using Spark's MLlib. GraphX is Spark's own graph computation engine. So this is mainly if you are interested in doing a graph-based processing. Think about Facebook, think about LinkedIn, where you can have your data which can be stored, and that data has some kind of network connections, or you could say it is well networked. I could say X is connected to Y, Y is connected to Z, Z is connected to A. So X, Y, Z, A, all of these are, in terms of graph terminologies, we call as vertices or vertex, which are basically being connected. And the connection between these are called edges. So I could say A is friend to B. So A and B are vertices, and friend, a relation between them, is the edge. Now, if I have my data which can be represented in the form of graphs, if I would want to do a processing in such way, this could be not only for social media, it could be for your network devices, it could be a cloud platform, it could be about different applications which are connected in a particular environment. So if you have data which can be represented in the form of graph, then GraphX can be used to do ETL, that is extraction, transformation, load, to do your data analysis, and also do interactive graph computation. So GraphX is quite powerful. Now, when you talk about Spark, your Spark can work with your different clustering technologies. So it can work with Apache Mesos. That's how Spark came in, where it was initially to prove the credibility of Apache Mesos. Spark can work with Yarn, which is usually you will see in different working environments. Spark can also work as standalone. That means without Hadoop, Spark can have its own setup with master and worker processes. So usually, or you can say technically, Spark uses a master-slave architecture. Now that consists of a driver program that can run on a master node. It can also run on a client node. It depends on how you have configured or what your application is. And then you have multiple executors which can run on worker nodes. So your master node has a driver program, and this driver program internally has the Spark context. So your Spark, every Spark application will have a driver program, and that driver program has a inbuilt or internally used Spark context, which is basically your entry point of application for any Spark functionality. So your driver or your driver program interacts with your cluster manager. Now, when I say interacts with cluster manager, so you have your Spark context, which is the entry point that takes your application request to the cluster manager. Now, as I said, your cluster manager could be, say, Apache Mesos, it could be Yarn, it could be Spark standalone master itself. So your cluster manager in terms of Yarn is your resource manager. So your Spark application internally runs as series or set of tasks and processes. Your driver program, wherever that is run, will have a Spark context, and Spark context will take care of your application execution. How does that do it? Spark context will talk to cluster manager. So your cluster manager could be Yarn, and in terms of when I say cluster manager for Yarn would be resource manager. So at high level, we can say a job is split into multiple tasks, and those tasks will be distributed over the slave nodes or worker nodes. So whenever you do some kind of transformation or you use a method of Spark context, an RDD is created, and this RDD is distributed across multiple nodes. As I explained earlier, worker nodes are the slaves that run different tasks. So this is how a Spark architecture looks like. Now we can learn more about Spark architecture and its interaction with Yarn. So usually what happens when your Spark context interacts with the cluster manager. So in terms of Yarn, I could say resource manager. Now we already know about Yarn. So you would have, say, node managers running on multiple machines, and each machine has some RAM and CPU cores allocated for your node manager. On the same machine, you have the data nodes running, which obviously are there to have the Hadoop related data. So whenever an application wants to process the data, your application via Spark context contacts the cluster managers, that is resource manager. Now what does resource manager do? Resource manager makes a request. So resource manager makes requests to the node manager of the machines wherever the relevant data resides, asking for containers. So your resource manager is negotiating or asking for containers from node manager, saying, hey, can I have a container of 1 GB RAM and 1 CPU core? Can I have a container of 1 GB RAM and 1 CPU core? And your node manager, based on the kind of processing it is doing, will approve or deny it. So node manager would say, fine, I can give you the container. And once this container is allocated or approved by node manager, resource manager will basically start an extra piece of code called app master. So app master is responsible for execution of your applications, whether those are Spark applications or MapReduce. So your application master, which is a piece of code, will run in one of the containers. That is, it will use the RAM and CPU core, and then it will use the other containers which were allocated by node manager to run the tasks. So it is within this container which can take care of execution. So what is a container? A combination of RAM and CPU core. So it is within this container we will have a executor process which would run, and this executor process is taking care of your application related tasks. So that's how overall Spark works in integration with Yarn. Now let's learn about this Spark cluster managers. As I said, Spark can work in a standalone mode, so that is without Hadoop. So by default, applications submitted to Spark standalone mode cluster will run in FIFO order, and each application will try to use all the available nodes. So you could have a Spark standalone cluster, which basically means you could have multiple nodes. On one of the nodes, you would have the master process running, and on the other nodes you would have the Spark worker processes running. So here we would not have any distributed file system because Spark is standalone and it will rely on an external storage to get the data, or probably the file system of the nodes where the data is stored, and processing will happen across the nodes where your worker processes are running. You could have Spark working with Apache Mesos. Now, as I said, Apache Mesos is an open source project to manage your computer clusters. and can also run Hadoop applications. Apache Mesos was introduced earlier, and Spark came in and has existence to prove the credibility of Apache Mesos. You can have Spark working with Hadoop's Yarn. This is something which widely you will see in different working environments. So Yarn, which takes care of your processing and can take care of different processing frameworks, also supports Spark. You could have Kubernetes. Now that is something which is making a lot of news in today's world. It is an open source system for automating deployment, scaling, and management of containerized applications. So where you could have multiple Docker-based images which can be connecting to each other. So Spark also works with Kubernetes. Now let's look at some applications of Spark. So JP Morgan Chase and company uses Spark to detect fraudulent transactions, analyze the business spends of an individual to suggest offers, and identify patterns to decide how much to invest and where to invest. So this is one of the examples of banking. A lot of banking environments are using Spark due to its real-time processing capabilities and in-memory faster processing, where they could be working on fraud detection or credit analysis or pattern identification and many other use cases. Alibaba Group that uses also Spark to analyze large data sets of data such as real-time transaction details. Now that might be based online or in the stores. Looking at the browsing history in the form of Spark jobs, and then provides recommendations to its users. So Alibaba Group is using Spark in its e-commerce domain. You have IQVIA. Now this is a leading healthcare company that uses Spark to analyze patients' data, identify possible health issues, and diagnose it based on their medical history. So there is a lot of work happening in healthcare industry where real-time processing is finding a lot of importance, and real-time and faster processing is what is required. So healthcare industry and IQVIA is also using Spark. You have Netflix, which is known, and you have Riot Games. So entertainment and gaming companies like Netflix and Riot Games use Apache Spark to showcase relevant advertisements to their users based on the videos that they have watched, shared, or liked. So these are few domains which find use cases of Spark, that is banking, e-commerce, healthcare, entertainment, and then there are many more which are using Spark in their day-to-day activities for real-time, in-memory, faster processing. Now, let's discuss about Spark's use case, and let's talk about Conviva, which is world's leading video streaming companies. So video streaming is a challenge. Now, if you talk about YouTube, which has data, you could always read about it. So YouTube has data which is worth watching 10 years. So there is huge amount of data where people are uploading their videos or companies are doing advertisements, and this videos are streamed in or can be watched by users. So video streaming is a challenge, and especially with increasing demand for high quality streaming experiences. Conviva collects data about video streaming quality to give their customers visibility into the end user experience they are delivering. Now, how do they do it? Apache Spark again. Using Apache Spark, Conviva delivers a better quality of service to its customers by removing the screen buffering and learning in detail about network conditions in real time. This information is then stored in the video player to manage live video traffic coming in from 4 billion video feeds every month to ensure maximum retention. Now, using Apache Spark, Conviva has created an auto diagnostics alert. It automatically detects anomalies along the video streaming pipeline and diagnoses the root cause of the issue. Now, this really makes it one of the leading video streaming companies based on auto diagnostic alerts. It reduces waiting time before the video starts. It avoids buffering and recovers the video from a technical error. And the whole goal is to maximize the viewer engagement. So this is Spark's use case where Conviva is using Spark in different ways to stay ahead in video streaming related deliveries. If we have understood and learned about your Spark components, your Spark Architecture, we can also see running a Spark application. Now, a Spark application can run in a standalone mode. That is, you could set up your IDE such as Eclipse with a Scala plugin, and then you could have your coded application which is written in Eclipse to be run in local mode. Now here I have an example of application which can be run in a local mode or on a cluster. So this application is importing some packages, that is Spark Context, Spark Conf. I have created an object which is first app. It is the main class of your project, and other classes can just be extending app rather than having main. Here we declare a variable called x, which is pointing to a file in my project directory. It looks for a file which is abc1.txt, and this file basically has some content. What are we doing in the application? So we create a variable where we assign the file. Then we define or initialize our Spark context. So remember, whenever you work with IDE, you don't have Spark context or Spark available implicitly. That has to be defined. So here we create a configuration object. We set our application name. We set the master as local if you want to run it in a local mode. If you want to run it, say, on your Windows machine, or if you would want to run on a Spark standalone cluster. If I would be running it on Yarn, then I would remove this property that is set master. Now, once you have defined your configuration object, you can be basically using Spark context. You can use method of it, which will result in RDD. That is what is happening in line 13, val y. And then finally, I can create a variable where I would want to do a flat map transformation on y, which would result in an internal RDD, followed by a map transformation, which would again result in an RDD, and finally reduce by key, which is doing an aggregation. Once all these steps are done, I can decide to display the result on the screen, or I can even use save as text file, point it to a particular location, and then have my application run. Now, this is my Eclipse. Refer to other sessions where I've explained how you can set up IDE on Windows with different environment variables, and then you can run your applications on a particular cluster. If I would want to run this application on a cluster, then I will have to give a particular path. So here in this case, I can say, let's do this, and I will say my file is abc1.txt. Let's save it, and I'll also say my output will be getting stored in a default location. As I intend to run it, I intend to run this application on a cluster. Now in that case, the cluster would usually be set up on Linux machines, would have a Hadoop cluster where you can run this application. So if I would want to run this application on a cluster but not locally on the machine, I can just delete this part. I can keep my application. Now if you see, my application already compiles and does not show any error message, and that is because in my project's build path, I have added all the Spark related jars. All the Spark related jars you can get from your Spark directory, or you can be getting in manually all the dependencies. Some people would prefer to use Maven or say SBT for packaging your application as jar, and that can also be done. So here my code compiles, code is fine, it is pointing to a file, and then it is also creating an output which will have word count. Now what I can do is, since I have my code already written, I know that I have SBT installed on this machine because I would want to package this code as jar and run it on a cluster. So for that, we can look in our command prompt, and here I can go into workspace. I can go into my Scala project, and if you see here, we have your build.sbt file, you have your binaries, and you have your source. So you might not have these Spark related directories. Now these exist in my case because I have been using Spark and I've done some previous runs. Now this is what we have within my Spark apps. So to build my package, I need a build.sbt file. We can see what does that contain. So your build.sbt contains your name, version of your package jar, Scala version, Spark version, and then repository which Spark will refer to when it wants to have the dependencies for all of your components such as Spark Core, Spark SQL, MLlib, and so on. So this is my build.sbt file which exists in the project folder. And if you are intending to use SBT to package your code as jar and then run it on the cluster. In that case, I can even skip adding Spark related jars to the build path. So that is only done to make sure that your code compiles. Now, once I have my code written, I have SBT installed, I have made the file path changes, I can just go to the command line within my project folder and I can say SBT package. Now this will basically resolve all the dependencies based on whatever you have given in the code. It will create a jar file and place it in a particular location, and then we can use the same jar file to run on a particular cluster. So SBT package is busy in creating the jar. Now meanwhile, what I can do is I can open up a lab content, and what I can do is I can just say, for example, Simplilearn. And here I already have a lab setup, so you could have your own Spark standalone cluster where you could also run this jar file. You could have Spark with Hadoop, which is what I have here, and I will use that to submit an application on the Yarn cluster. And let's go to the web console. Let me copy my link. I'll close this. I'll say launch lab, and then I can log in here. I can just paste my password and I'm logged in. So I can just say Spark 2 shell. Now that's how it has been configured here to work with your Spark version 2. So this is an interactive way of bringing your Spark shell and running your application. But what we are interested in is running the application as a jar file. So let's go and see here where we have our code, and let's see if SBT has done the packaging. Yes, it has done, and it has created a jar file in this location. So what I can do is I need to get this jar file from this location onto my cluster. So what I can do is I can come in here, I can do a FTP. So this basically allows me to push whatever jars I have on my web console. So I'll go in here, I'll say connect. Now I'll search if there is already existing jar file which might create a conflict. So I have something here. So I can for now just delete it. It's done. I will say upload file, and I'm interested in getting the jar file. So here we can click on users, Win10. I have my workspace project. I can get into target, Scala 2.11, and take my jar file and say open. So this will upload my jar file on the web console or the terminal, wherein I can connect to my cluster. Now let's go in here. Let's quit from Spark Shell as we want to run an application on the cluster. How do I do it? So I can search if I have my jar file existing. It's here. So I'll say Spark to submit, and then I will point to my jar file, and then I can simply say class, and I know my code has a package and a class name. So this is package and this is my object or class name. So I can say main.scala.first_app. Now it will be good if we check if the file exists, which our code points to. So I'll just for now comment it out. I will check in my HDFS ls in my default user directory. This is where it will search for a file, and here we can search if I have a file called ABC. So I don't see anything here. So let's do this. What I can do is I can again go to FTP, and basically I can do a upload file like what we did earlier, and this time I'll pick up this existing ABC1 file which I showed you and upload it. Once this is done, I can put it on my cluster by just saying HDFS DFS put. Let's take the ABC1 file and let's put it in my directory. So this will be my input. So I'm putting in a file there, and now I can do a Spark submit to submit the application on the cluster. So if you see here, it has basically started the application. It contacts the resource manager. It gets an application ID, and now it is doing the processing of my file where I would want to get. Once this is done, it will be completed and the temporary directory will be deleted. So this is how I run a Spark application on a cluster. Now once this is done, I can also go to Spark's history server by saying this is the path for my Spark history server. It shows an application which was run today, which was doing a word count. You can click on the application. It says it ended with save as text file. You can click on this and then it shows you the DAG visualization. It says we started with text file. We did a flat map, we did a map, and then there was some shuffling because we wanted to do reduce by key. So as I said, every RDD by default has two partitions. And if you want to do some aggregate or wider transformations like reduce by key, sort by key, group by key, count by key, and so on, in that case, similar key related data has to be shuffled and brought into one partition. That's where we see shuffling happening here, and it also tells what are the number of tasks which have run per partition. So here we ran a Spark application by packaging it as jar using your SBT. So SBT created the jar file, and then basically we brought our jar file onto the cluster and then submitted it using Spark Submit. So this is how a Spark application runs on the cluster. So as I said, your application has a driver program. Now your Spark applications run as independent processes and they can run on a cluster across the nodes. So we just saw how we can run a Spark application on a cluster. Now we can always look at Spark application's progress or after it has completed by looking into the Spark UI. Your Spark application, as I mentioned, has a driver program, and when you run your application on the cluster, you can always specify where would you want your driver program to run. So in our case, when we ran our Spark application here, we basically just did a simple Spark submit and we gave our jar and the class name. I could also say master, and then I could specify if I would want my application to run in a local mode, or I could say yarn, but that is default. Or if it was a Spark standalone cluster, then I could be giving something like this, your host name, and then your port. So you could do all of these options by specifying minus master. I could also specify how many executors I need, how much memory per executor, how much cores per executor I need. And I could also say deploy mode as client, which basically means my driver will run on this machine. However, my execution of application will happen on cluster nodes. I can also say deploy mode as cluster, which basically means my driver will run on one of the nodes of the cluster. You could submit your application, and then based on whatever arguments you have given, your application will be submitted on the cluster and it will run. So you can have your application running. So as I said, you have an application which has a driver and it also has either Spark session or Spark context, which takes your application request to the resource manager. Now, if your application is completed, you can always come back and look into the Spark history server or Spark UI. If I choose this as my application, which I have run, I can go to executors, and that shows me that there was one for your driver. Now that was running on this particular node, which is my client node. Then I have my executors on my other nodes, which are nodes of my cluster, which used one core, which ran 2 tasks for the partitions which they were working on. And there was some shuffling involved as we were doing a word count, which uses reduce by key. So when you run your application, your yarn or your cluster manager, such as resource manager, negotiates the resources to the slave processes. Your worker node basically will have the resources available for any kind of execution. Now, as I said, your resource manager will request for containers. Your worker nodes will approve those containers. And then within those containers, you will have the executor which will run, which will take care of the task to process the data. So what is a task? It is a unit of work for the data set which has to be worked upon. So your RDDs which get created have partitions, and for every partition you have a task which is taken care by the executor. So the data is loaded into the RDD when an action is invoked, and then your task is worked upon by the executor. So what does it do? It basically gets the data into the partition of RDD and then does the execution as a task on that particular partition. Results are then sent back to the driver, and you can also have your output saved on the disk. So this is how your application runs. Whenever you run a particular application, you can always go to your web console and scroll or look into the logs for more information. So here our application was run, and we can see right from the beginning here when we talk about Spark Submit, which is done here. It says running Spark version 2.2. It basically then will see that there will be a driver which will be started. You can further see that it does some memory calculations. It then starts a Spark UI. And here we can see that requesting a new application from cluster with 4 node managers, verify our application has not requested more than maximum memory capability of the cluster. So the container sizing at the cluster level is 3 GB per container, and your application should not be requesting for a container bigger than that. It starts a application master container with specific amount of memory, and then finally your execution starts. If we scroll down and look into the logs, we will see where my driver runs. It will also show you how much memory was utilized, and it will talk about DAG scheduler, which is taking care of execution of your DAG, that is series of your RDDs. And finally, you will see the result getting generated or saved. So this is how you run your Spark application. This is how you can see your Spark applications in History Server or Spark UI. And this is how overall Apache Spark works, utilizing your cluster manager help, getting the resources from the worker processes, and then running the executors within those. So let's have a quick demo on setting up Spark on Windows and trying out the Spark's interactive way of working. For this, first thing is you will have to download Spark. Now you can just go to Google and type Spark download, and once you click on this link, it shows you a Spark release, a package type which says pre-built. So we will have to get a pre-built Apache Hadoop related Spark. So here I will choose say Spark 2.4.3, and I will choose pre-built for Apache 2.6, and then I can just click and download on this Spark 2.4.3 bin Hadoop 2.6 tar file. Once you click on this link, takes you to the mirror site, and you can just click on this link and download Spark 2.4.3. Once this is done, which I have already downloaded, here I can go to my downloads and it shows that I have a tar file. Now we will have to untar it or unzip it. So I can click on this link, and I already have WinZip, which allows me to unzip Spark 2.4.3. I can choose a location, so I can say unzip, click on unzip, choose local, and then I can choose one of my folders. So I have already unzipped it here, and that's how my Spark 2.4.4 directory exists here, 2.4.3, I'm sorry. Now let's go and look into this directory and what it contains. So I can click on C drive and then Spark 2.4.3, and this has the folders which are required for us to use Spark. If you look in bin, we have different applications and commands which we can use. And if you also see, I would have added one of the utilities here. Either we can have the Win utils, because Spark will need Hadoop and we are planning to use Spark on Windows. So what we need is this. So I have in my desktop a Hadoop directory which has a bin folder, and here I have downloaded a Win utils executable file, which you can always search on internet, and you can say download Win utils.exe for Spark 64-bit, and then you can find the link from where you can download this. For example, we can click on this, and here we can search for WinUtils. So here we have the link. I can open this link in a different tab, and this basically shows me WinUtils for Hadoop 2.7.1. Similarly, you can search for Hadoop 2.6 and you can download. However, 2.7 will also work fine. Now I have downloaded winutils.exe, and that's in this Hadoop folder. Within bin, I have this. So we need two things here. One is Spark which is untarred and in a particular location, and then your Hadoop, which has bin, and this has bin utils. Now, once you have these things, you can set your environment variables by just type in envir, go to your edit system environment variables, click on environment variables, and here if you see, I have added 2 variables. So you can just click on new, and then you can give your variable name as Hadoop_home, and then you can give the path where you have your Hadoop directory that contains bin and that contains winutil.exe. I also have added Spark home, which points to my Spark directory. Now, once you have this, you are ready to use your Spark on Windows in local mode. Once this is done, I can open up my command prompt, and here I need to go to my Spark directory. I can just say cd spark 2.4.3, and then I can do a dir/p, which shows me the folders where we have bin. So to execute Spark, we can look into what our bin has, and it has different programs, such as you have Spark Shell to work with Scala and in an interactive way of working with Spark. You can also use PySpark, which allows you to use Python to work with Spark. And you also have Spark Submit if you have packaged your application in a jar file to submit it on a cluster. So in this case, we would be using Spark in a local mode. So let's use Spark Shell and test it. So I can just say Spark Shell in this way to start my Spark in an interactive way. Now, based on the path which you have set for your winutils.exe and Spark Shell, you should be able to use Spark. So it says, welcome to Spark version 2.4.3. It also shows that Spark Context, which is the entry point of your application, is available as SC, wherein it is connecting to master as local and it has an application ID. It also shows you a Spark UI, which you can look at, and it says Spark Session is available as Spark. So if you're interested in working with Spark Core, that is with RDDs, we would be using Spark Context. And if you're interested in working with Spark SQL, that is data frames and data sets, then we can be using Spark Session. So let's try it out. So we can declare a variable that is an immutable variable. And now I will use Spark Context with a method of Spark Context. So I could just do a tab to see what are the available options within your Spark Context. And here we can use one of them to read a file. So I will use sc.text file, and then I need to point to a file. So I already know that in my Spark directory, I have a file called readme.rd, and this is the method of Spark Context. If I enter, it will create a RDD. Now, as I've explained about RDDs, these are resilient distributed data sets. There is no evaluation happening right now. So even if this file does not exist, I would still have an RDD created. Now I can go further and do some more transformations on this. So I could say val y, and then I could say take x. I would like to do a map transformation on it, and I would use to uppercase. Now this is an inbuilt function where I would want to convert the content of this file into uppercase. When I hit on enter, it again creates an RDD, and this RDD is basically a child RDD of the parent RDD created by text file. Remember, here we don't have any evaluation happening or any execution happening. It is just transformations which will lead to creation of further RDDs. Now we can invoke an action to see the result, and whenever you invoke an action, it will trigger the execution of your DAG starting from your first RDD till the last transformation you did before invoking an action. So I could just say count to see how many lines it has, and once I do this, it says input path does not exist. It is not able to find a file in this location. So this clearly explains that there was no evaluation happening when we did this, when we tried to read a file, and neither when we did a map transformation. Only and only when we invoked an action, it tried to search for file in this location. So let's quit this and check if the file exists. To quit, you can just do a Control D, or you could do a :quit. Now here, if you see some messages like this which says unable to delete temporary file, so that's a known issue. We can fix that, but my Spark is working fine. Now let's go and check if the file exists. So I will go in here and then I will look in my Spark directory to see if the file exists. So this is the file readme.md. However, I had done readme.rd. So let's do it again and let's test if our Spark shell works fine. So we can go into the Spark directory by just doing this. And then either I could be going into bin directory and then start Spark shell, or some people prefer to do it this way, wherein you can say bin Spark shell, and that should start your Spark shell, but there was an error in the slash. So let's do it this way, and this will start your Spark shell, an interactive way of working with your Spark and using Spark context or Spark. Now once we have done this, I can again say val x and I can say sc, which is Spark context, which is already initialized when you start your Spark shell. I can say text file, and I would want to read a file which is readme.md. Now we know that this file exists. However, the checking of the file existing or not, that means an evaluation, does not happen when you do a transformation or when you use a method of Spark context. It just creates an RDD. Click on this and this has created an RDD of string. Now we can do further transformation on X by saying map, and then I can say I would want to convert the content into uppercase, and that's also done. Now finally, let's invoke an action which will trigger the execution of my tag which contains these RDDs. So I could just say Y and I could say take 10 and I could say for each print ln, and this should be able to invoke an action and it shows me the result from the file which is converted into uppercase. Remember, if I do a y.count, which is another action, it will trigger the execution of DAG right from the beginning where the first RTD was created. The transformation will be done and then it will show me the count of lines which exist as a result of this. So we can do this, and this says me that there are 105 lines. This is a simple example of using Spark shell and using Spark in an interactive way on your Windows machine. Now to quit, we can always do a :quit, or we could do a Control D, and that basically takes you out of your Spark shell. Similarly, we can work on PySpark by just saying ./bin/PySpark, and that's Python's way of working with Spark, which brings your Python shell. It starts the Spark context, which is available as SC. And if you are interested in working on data frames or data sets using Spark SQL, then we would be using Spark. Now here, I can just declare a variable X and I can just do sc.text file like what we did using Scala. We can be referring to the same file readme.md, and this has created an RDD. You can just type in X and that shows the RDD which was created. You can then further do some transformation on it using x.map, and then I could say I would want to convert this to uppercase. Now in case of Python, you would normally use lambda if you would want to do any kind of transformation. So I would say lambda x, and then I would want to convert this to uppercase. So here we can check if my RDD was correctly created, and as I was saying, we can then do some transformation on it. So I can say again y equals, and then I would want to do some transformation on X. I would say x.map. So in case of Python, as I explained, whenever we want to use an anonymous function or we want to do some transformation, then we can pass in the function to the transformation. So here I can say lambda, and then I can just say line, or I could say X or A, whatever that is, and I could say line. I would use an inbuilt function that is upper, which should convert the content of X to uppercase. Now remember, we are just doing some transformations here. So if I click on Y again and enter, if I enter Y, it will show me that that has created an RDD. To see the content, I can just say y.collect, and that should show me the content of first few lines, which is converted in uppercase. So this clearly shows that we can even use Python to work with Spark by using PySpark. Now to quit this, we can just say quit, and that should take you out of your PySpark shell. So this is how you work on Spark shell or PySpark on your Windows machine. So this has a local Spark setup, or basically Spark running in a local mode, and you could be using the interactive way of working with Spark. Now if we have packaged our application in a jar file, then I could be using Spark Submit to submit my application. How do we do that? For this, we can basically bring up one of our IDEs. So in my case, I'm using Eclipse, and I can get into my Eclipse. Now there are two options here. One, we can be writing code in your IDE, that is Eclipse. We can be compiling the code based on the Spark related jars, and then we can run our application from IDE, which would interact with your Spark. That's one way. The second way is we can use packaging tools like SBT to package our application as jar and then push the jar to your local Spark or a Hadoop based Spark and then run it using Spark Submit. Now this is a simple sample application for which I have set up certain things here. The first thing is, when you have downloaded Eclipse, for all the people who are new, they might have to add the Scala plugin. Now if you see here in my Eclipse, it shows up Java perspective and it shows Scala perspective. Now how did I get this? You can click on help and you can say install new software, and here you can say add, you can say Scala IDE, and then you will have to give a link from where you can get the Scala IDE. How do I get that? So I can go to my browser and I can say scalaide.org, and once you go to this link, just scroll down, click on stable, and that shows you different releases for your different IDEs. Now for Eclipse, although this shows for Oxygen and I have Eclipse Neon, but that works fine. You can just copy this link, and here once you have copied the link, give the location here and you can say OK. Now once you do that, it shows you different options from where you can choose Scala IDE for Eclipse. Now in my case it is already installed, so these options don't show up. However, if you do not have this option, for example, let's choose something else. Say I will say Scala search, and once I do this, next gets activated. So Scala ID is already installed in my case, so I can click on next, and this should basically get Scala search plugin also, which can be added to my Eclipse. Now once this is done, you will be prompted to restart your Eclipse, and then you should have your Scala perspective. So for now, I'll just cancel this because I already have my Scala IDE.eclipse. So this is done. I'll just do a cancel here. Now once you have your Scala IDE or Scala plugin added to your IDE, you can always click on this icon here, and here you can just double click on Scala. That will open up Scala perspective. So that's the first thing. Then you can always click on File, New, and create a Scala project. For example, I could say My Test Apps, and then I can just say finish. So it has added a project. Now what we need to do is we need to make sure that our setup is fine. So first thing I would suggest is click on this, go to your build path, and here click on configure build path. So where it says Scala compiler, it would be good to choose for your project settings, instead of 2.12, go for 2.11. So sometimes you might have problems with Scala 2.12, which might not be able to compile for your Scala 2.11. So use latest 2.11 bundle, and then you can say apply. It says compiler settings have changed. A full rebuild is required for changes to take effect. Shall all projects be clean now? We can say OK, and we can say OK. So this will build your workspace to use Scala 2.11 bundle. Now once that is done, second thing what we need is we would want to write our code and we would want our code to compile. For that, as I said, if we want to write our code using an IDE and then run it from our IDE rather than using a build tool like Maven or SVT, I can just add the Spark related jars to my build path. So I can right click here, I can say build path, and I can click on configure build path, and here where it says libraries, I can say add external jars. Now this needs my Spark related jars. Now where do I find it? So remember, we have downloaded Spark, so you can even find it there. So you can click on wherever your Spark is, and then you can click for jars, which shows you all Spark related jars. You can just do a Control A and just add it to your build path, say apply, and then just say OK. So once this is done, you have already added the Spark related jars, which might be good enough for you to write an application. Once this is done, we need to basically go ahead and write our code. Now, how do I do that? I can just click on source and I can say new, and then I can say package. And here you can say main.scala, click on finish, and that has created main.scala. So that would be source/main/scala in the folders. We can always check that. So I can go to C drive, I can look in users, Win10, and then look in my workspace for my project. And if you see in source, we have main and we have Scala. Now this is where we will be writing our code. So for this, then I can just right click and I can say new, and I can just create an object and I can give it a name. So we can say test app, and then we can say finish. So in case of Scala and Spark, we need to create an object and then we need to define main class here. Once that is done, we also need to import some packages and we need to initialize the Spark context. Now for that, you can take an example here. So I have already written the code and I can look in source, main Scala, and I have created an app called firstapp.scala. Now here we have the package name. We are importing some packages which are required for us to initialize Spark context and Spark configuration. So it is Spark context, Spark conf, and here is my object. And for a particular project, at least one of your object or one of your application needs to be the main. So we define the main here by saying def main args and array of string. Then we need to basically define our Spark context. So I'm creating a configuration object here, and then I say new Spark conf. I'm setting my application name to Hello Spark. And then this is very important. If you intend to run your Spark application either using Spark Submit or from your IDE, you need to specify your master as local. Now that could be given with one thread or multiple threads. So this is my configuration, and then I initialize my Spark context pointing to my configuration. So this is the most important part here. Now, if you see, this is something which I showed you in the command line. So I'm doing a val x and I'm pointing it to a file in my project directory, which is abc1.txt. So this is just to make sure that you are giving a Windows path and you're giving the right escape characters. Now, if you intend to run this application on a Hadoop based cluster, then you will have to give the path of the file accordingly, which we can see later. So here I have val x, I'm pointing it to a file which I have created here, and this just contains 3 lines. This is my sample file which I want to test. This is a new file. Now here I've created a variable called x. Further, I would say val y, and I would use Spark context method text file like what we did in an interactive way, and I'm pointing it to x. I'm also using some extra features like caching so that I can cache the RDD which gets created. Further, I create a variable called counts, and then I do a flat map transformation on y, where I would split the content based on space. I would do a map transformation where I would get every word from the file and map it with number 1. And finally, I do a reduce by key operation. Once this is done, I do a saves as text file. Now I could do a collect, I could do a take, I could do a count, and I could also do a save as text file where I would want my output to be saved in this location. Plus I'm using a Java utility to append a random number to my output directory. Finally, I do a Spark context stop. So this is my application, and if you see here, my application completely compiles because I've already added the relevant jar files in the build path. Now, once this application is done, we need to run this. But before doing that, we need to look into our run configurations. So you can click on run configurations, and here I'm giving my project name. I'm specifying my main class, which is first app. Then you can straight away go to environment, and here I have added two variables. One is spark underscore local underscore IP, which points to this machine's local host. And then I've said Hadoop underscore home because Spark, even when you're running locally, would want if Hadoop is existing. So we can just set Hadoop underscore home, and I'm pointing it to my desktop Hadoop directory, which contains bin folder, and that bin folder contains a winutils.exe. Once this is done, we are fine, and then I can test my application by just clicking on run. Now this should trigger my application on my Windows machine using my IDE. I didn't have to package this as jar, and here my application is completed, which should have created one additional directory here. So I can click on this, I can right click, and I can try doing a refresh. And here you see a new output is created. We can look into this. It has a part file which shows my word count. So this is a simple example of setting up your IDE and running your applications from IDE on a local Spark. Now what you also see is a build file here. What is that for? So in case you would want to create a project and you would want to package the application as a jar file and then run it on the cluster using Spark Submit. Now in that case, we can avoid adding the jars to my build path. But what I would need is, I would need build.sbt file within my project folder. Remember, if you intend to package your application as a jar and then run it on a cluster or on a local setup, you would not need the build related jars. However, the build related jars which are already here will not cause any harm. Let them be there. Now we have a build.sbt file also, which is existing in my project folder. Now just for this run, I can in fact delete this target directory. It will be anyways recreated. And if you would want, we can also clean up these just to avoid the confusion. I will delete these. Now I just have my project folder and I have the libraries. I have abc1.txt and I have a build.sbt file. What does that contain? So this basically has a name. I'm giving a version which will be appended to my jar. I'm saying the Scala version which I'm using, which is 2.11.8, and I'm saying Spark version which is 2.2.0. You can replace these with the version which you intend to use. Other than that, we are pointing to the different Spark components and the relevant dependency related jars which your SBT can get for you. So I've given Spark Core, Spark SQL, MLlib, Spark Streaming, and Spark Hive, which will be then fetched from the repository. So this is my build.sbt file, which exists in my project folder. We have our code written. We have our build.sbt file, which is already existing in my project folder. My code is already fine. Now we need to use SBT to package my applications into jar, for which you will have to download SBT. So you can just say download SBT Windows, and that should take you to the installing SBT on Windows page. Now here you can just download the MSI installer and run through the installer, which will basically install SBT on your machine. Now I have already done that. So my build file is ready, my code is ready. All I need to do is now use SBT. So what I can do is, from my command line, I can just say cd and I will go into users. I'll go into Win10 and I'll go into my workspace. Now here I can see for my projects, and I can go into my Spark apps. Now, once I'm in my project folder, we can double check that it has a build.sbt, which is fine. SBT is already installed on this machine, and I can just say SBT. If you would want to check, you can always do SBT version to check if you have SBT. And this command is also done once you install SBT for the first time. You can always do SBT version, and before displaying SBT's version, it will try to fix all your dependencies. It will try to get all the relevant dependencies. So this is just to check that SBT is installed on my machine. As I said, my code is already ready. I have a build.sbt file, and I can just say SBT package, which then will refer to build.sbt, will look for your code in source main Scala, and then if everything is fine, it will package it as jar, and it will create folders within your project folder. We can click on this. We can try doing a refresh to see. Now, if you see here, the project was again created. A target folder is created. Within Scala 2.11, I will have my jar created. So we can see that my SBT was fine. It has packaged the code, and it has created a jar file as simple project 2.11-1, which can be used to run on the cluster or in a local mode. Let's check in Eclipse. I'll click on this and I'll just do a refresh, and I see my jar is already existing, which basically means then we can do a Spark submit. So this is where we see that I am already running a Spark submit command. Now this might show up some error messages, but we can see how we did this. So if you see here, once my packaging was done, I went into my Spark folder. I did a bin/Spark submit. I mentioned my jar file, and then I said my class main.scala.firstApp. So this is my app, and this is how I'm using Spark Submit to submit an application which is running in local mode. So we can see further if it starts processing. So here it says created local directory, then it starts an executor on local host. It goes for execution, and then if we see further, we could also see it will add our jar to the class path, and then finally it should be doing the execution. Now, if there is any error message that might be related to your file not being deleted, or if there is any problem with executor, so we can basically come back and check here if there was any specific error. So the error was that it tries to delete a temp directory, but it does not have the permissions, so we have not done that. But as per my application, it should be creating a output in this folder as Spark out. So let's click on this and see. I'll do a refresh, right? And if you see, a new Spark output has been created. Previous sessions, we have seen how we can set up Spark on Windows or set up our Spark related IDE so that we can run our applications on Windows. Now here we have a quick demo on setting up Spark as a standalone cluster on Ubuntu machines, and then trying out Spark way of working, for which we need at least 2 machines. And here I have Ubuntu machines set up, UM1 and UM2, just to give insights on how my machines look. So if I look in my etc hosts, I have the IP address of multiple machines, so I can ping one machine to other machine by just doing a ping UM2, and that should work fine. Similarly, I have also set up SSH access for these machines. Both of the machines have HDU as the user, and I can just do a SSH UM2, and that logs me into the second machine without a password. Similarly, I can check the same thing from my second machine by doing a SSH UM1, and that works fine too. So we need 2 machines which can ping each other, firewall disabled, able to SSH each other, so that we can set up a standalone cluster of Spark. How do we do it? So first thing is we will have to download the Spark related tar file. Now I can just go to Google and I can type in Spark 2.11 2.1 download. Now that's what I'm interested in, and this takes you to Spark release 2.2.1. However, here it shows you the latest release is 2.4 and then 2.4.2. So what we can do is we can go to archives. So I can basically look at existing versions. Now here I can click on download, and this shows me a Spark release and also pre-built for Apache Hadoop. Now what we can also do is we can go to release archives for an older stable version. I click on this, and here I have Spark 2.2.1. Now I can click on this, and we can either install something which is not already built, or we can download this one, which is Spark 2.2.1 bin Hadoop 2.6.tgz. So you click on this link and then save this file, which I have already done. And here, if you see in my machine, I have home HDU downloads, which has my different packages which I've downloaded. Also, if you notice, I have downloaded JDK 8, so you can check on my machines. So apart from machines being able to ping each other and being able to do a SSH, we also need machines to have Java, which is already installed. Once this is done, now I have my Spark related package. So I go into user local directory, and then you can give a command here, that is sudo tar xvf home hdu downloads, and then give your Spark package. Now once you do this, this will untar the Spark directory and create a directory in my user local location. If you see here, this is the directory which is created, but you also see that there is a Spark link which is pointing to Spark. Now that is because if you would want to work on a newer version of Spark, you could just do the same thing for newer version and then make your link pointing to the newer version of Spark. How do you create a link? You can just say sudo ln -s, you can give your Spark directory, and then you can create a link. So I've already created a link, and my Spark path will then become this. Now what do we do with this? Once we have done this, once we have created a link, we can go into the bash file of my user. And if you carefully see here, I have given my Java path so that I can execute Java related commands. And I have also added my Spark related path here, which says user local Spark. So in case you would be changing your Spark version to a latest one, you will not have to change things in your bash file. Only thing you will have to do is unlink the existing Spark link and create a new link to your newer version. So this is done on this machine, and now I can basically be using Spark. Now before doing that, we can go into user local Spark, and this has different directories. So if you look in bin, these has the binaries programs like your PySpark, your Spark Shell, Spark SQL, and Spark Submit, which we will see how we can use here. If you look in sbin, it has other startup scripts to start your history server or to start your master or worker processes. If you look in conf, this has your config directories. Now here by default you might see spark -default.conf.template. I have renamed that to .conf. Slaves template has been renamed to slaves. So let's look into this. So I can go into conf, and then I will look in spark default conf. Now here, based on our setup, now here we intend to set up a Spark standalone cluster that is without Hadoop, but I would want to have a Spark standalone distributed cluster. So I have uncommented this property which says spark.master, and I say Spark, and I also mentioned that my master will run on this machine, which is UM1. Spark event log.enabled is true because we would want to track the events. I have mentioned a directory. So this is a local directory in user local Spark, and we will have to create it. It talks about the default serializer. It talks about the driver memory, which was by default 5 GB. I have reduced it to 2 GB based on my machine configuration. You have Java options. And then if you intend to run a history server so that whenever your Spark application is complete, you will have your application stored in history server, I have given the log directory, which is user local Spark, and then application history, and this also needs to be created. we have Spark History Provider for the class, which takes care of history server, and the update interval of looking for your applications. So this is what we have in our Spark default. And if you look in slaves, I have given the machines where I would want my worker processes to run. So that is UM1 and UM2. Now, once you have made your changes in your Spark default conf and slaves file, what you can simply do is SCP, assuming that whatever was done on this machine, that is untarring your Spark directory, creating a link, updating your bash RC, and renaming your config files, same steps need to be done on the second machine, and your second machine would also be prepared to be used for your Spark cluster. So once you have both the machines which can ping each other, which can SSH each other, both of the machines have Java, both of the machines have the same Spark version downloaded, and the basic setup done, I can just easily copy the Spark related config from here into my other machine, that is SDU UM2, and then I can give a path which is user local spark conf, and in this way I don't need to edit my config files again, and similarly I can even copy the slaves file. This is all we need to basically have our Spark standalone cluster. Now, since we have updated our bash RC, we can give our Spark command from anywhere. We have set up our config files, so I can just do a start -all.sh, and that based on my config files, based on the directories which are mentioned, it will start my master process and my worker process on both the machines. So here we have a Spark standalone cluster which has 2 workers and 1 master. Now we can always go to the browser interface and we can check for the Spark UI, which should be available by typing in http://mymaster, and then the port is 8080. So this shows that I have a Spark master running. I have 2 worker processes. Right now there are no applications which are running, but my Spark UI is already available. When we start using Spark, either by Spark Shell or PySpark or even Spark Submit, we will see our applications getting populated here. Additionally, we can also start the start history server by just saying start history server.sh, and that will start my history server. Once this is done, we have a history server also running, and we can go back and then we can again pull out the history server user interface by giving in the port which is default 18080. So I have a Spark standalone cluster with 1 master, 2 workers, and also a history server which is running. Once we have this, we can try working with Spark, either with Spark Shell or PySpark, or if you have packaged your application as a jar using SBT or Maven, you could also use Spark Submit. Additionally, you could also use Spark SQL. So to work with Spark, I would just say Spark Shell on one of my machines. Both my machines which have worker processes running, we can start our Spark Shell on any of these machines. Remember, here our Spark will rely on the storage of these machines, that is the file system, because it does not have any Hadoop or distributed file system. We have started our Spark Shell, and that shows Spark Context, which is available as SC. Spark Session is available as Spark. So to work with Spark Core and RDDs, we would be using Spark Context, and if you intend to work with Spark SQL, that is data frames and data sets, you can be using Spark. Let's try a quick simple example. So I'll say val x sc.text file, and now I would want to point it to a file. So I will say the complete path. Remember, I'm giving the Spark command from my home directory. So I will have to say user local spark, and then I can point to a file which is existing here. And this is what I would want to use to do some processing. We are using the first step here, wherein we are using a method of Spark Context which will not relate in any evaluation, and it will just create an RDD. Now we are using the Scala's way, so let's create one more variable, and then we can do some transformation on it by saying to uppercase. I would just want to convert the content into uppercase, and this is again a transformation, so that will just create an RDT. Once this is done, we can invoke an action to basically see some results. So I could just simply do a collect, which is an action, and this action will trigger the execution of DAG, which starts from the farthest RDT. That is the first step where your file is loaded into RDT. Now, once we do this, we should be able to see our result, and that basically is execution of DAG. So from the time we have used a text file, which is a method of Spark context, to we did a transformation, and till we invoked an action becomes my one job. Now, if I would do y.count, which is again a different action, this will trigger the execution of DAG right from the beginning. That is sc.text file, where the data will again be loaded in RDT. A map transformation will happen, and then you will have a count. Now we can always see this in the Spark UI by just going in here and just doing a refresh. So that will show me that there is an application which is running via Spark Shell. It has utilized 3 cores. It has utilized memory per executor 1 GB, and we can click on this application, which shows that it used both the workers, 1 core and 1 GB on this worker, and 2 cores and memory on this worker. I can click on application detail UI, wherein I can see what are the actions I invoked. We also see the number of tasks which are run, and that is because every RDT which is created by default is having 2 partitions. And for each partition, you would have 1 task. Well, we can change the partitions and many more things can be done, but that you can learn in later sessions. Here we have 2 jobs. One ended with collect and one ended with count. Now I can click on collect, and I can see the DAG visualization, which tells me we started with a text file, we did a map, and finally we did a collect. It shows that everything was done in stage 0. That is just one stage. I can click on count, and that again shows me the DAG visualization, which is a different stage, a different job ID, which started with text file, map, and then we did a count. If you would want to see more details, you can always use these tabs to look at different stages within your application. If you were doing some caching, looking at environment variables, and also to see how many executors were used, including the one for the driver, on which nodes these executor ran, how many cores, how many tasks were run, was there any shuffling involved, and so on. So this is how I have used Spark Shell. That is an interactive way of running my application. And since we have a Spark UI, we can always look at applications when they have run, and we can always drill down and know more details. Now, since my application is completed, I can do a refresh on history server, but that does not show anything because when we started a Spark Shell, it started an application, and that application is still in running status, if you see here under running applications. So this is how we use Spark Shell on a standalone Spark cluster. Now we can just do a :quit, and that takes me out of Spark Shell. Similarly, if I would want to work on PySpark, that is Python's way of working with Spark, I can just type in PySpark, which should bring my Python shell, and then I can continue working with Spark and again go back and look at my UI. While my PySpark comes up, I can go here. Since I quit my Spark Shell, I can just do a refresh to see if my application is yet coming up in history server. It might take some time, and you can always go back and look at incomplete applications or wait till your application is populated in history server. Now, if I do a refresh here on Spark UI, it says this application was completed. It says finished. And then now we have started PySpark. So it has started a new application, PySpark Shell, and that is in running status. We can come back here, and now we have our Python's way. So I can do the same thing which I did in Scala using sc.text file. I will point it to a file which exists in user local spark readme.md. So that's the file which I'm interested in. Now this would have created an RDT, which we can confirm by just typing in X. Now I can create a different variable and I can say I would want to do a transformation of map. Now in case of Python, when you use anonymous functions or when you want to apply some functions to your transformations, you use lambda functions. So we say lambda line, and then I would say what I want to do to the line. I will say I will use a inbuilt uppercase upper function which should convert my content into uppercase, but as of now this is a transformation, so it only creates an RTT. To see the result, I can do a y.collect and that should bring up my result. Now in case if it says the file does not exist, that is because there was a typo here, and we can repeat this step. So let's bring up here again X, and I can give the right name of the file. I can do a transformation, and finally I can see the result. So this is using PySpark on a standalone Spark cluster, which is working without Hadoop, which has 2 worker nodes and 1 master node. We can always come and do a refresh here to look at more details. So we have our application. We can click on this. Again, similarly, like we did for Scala application detail UI, I see my application ended at collect, it ran 2 tasks, and I can look at my DAG. So this is how we can use Spark Shell or PySpark. Apache Spark Streaming, and here we will learn on what is Spark Streaming, Spark Streaming data sources, features of Spark Streaming, working of Spark Streaming, discretized streams, caching or persistence as we call, checkpointing in Spark Streaming, and we will then have a demo on Spark Streaming. So let's learn on what is Spark Streaming and what it is capable of. So it's an extension of core Spark API that basically enables scalable, high throughput, fault tolerant stream processing of live data streams. Now data can be ingested from different sources like Kafka, Flume, Kinesis, or TCP sockets, and then it can be processed using complex algorithms expressed with different kind of functions such as map, reduce, join, and window. And when we have the data processed, that data can be pushed out to your file systems, databases, and live dashboards. So if we look on this image, we can clearly see that we would be working on a input data stream which goes into Spark Streaming component of Spark, which gives us batches of input data, or you could say the streaming data is broken down into smaller batches which would then be worked upon by Spark core engine, and you have finally batches of processed data. Now when we talk about Spark Streaming and the data sources, you could have streaming data sources coming in from Kafka or Flume or say Twitter API, or also with different formats such as Parquet. You could also have static data sources coming in from MongoDB, HBase, MySQL, and Postgres. So when we talk about Spark Streaming, it receives the input data streams, divides the data into batches, which can then be processed by Spark engine to generate your final stream of results again in batches. So your Spark Streaming actually provides a high-level abstraction called Discretized Stream, and we will learn about that, or what we call as D-stream, which represents a continuous stream of data. Now when we look at your different data sources from where the data can come in, Spark Streaming would take in this input, and then you could have even your MLlib component which could be used. That is Spark's component to build machine learning algorithms, wherein you can train your models with live data, and you can even use your trained model. You could be also going for structured processing or processing the data which is structurized, and that could be done by using Spark's components, that is Spark SQL, which has data frames and data sets. So you could process your data with data frames, interactively query with SQL when Spark Streaming is working on the data which is constantly flowing in. Finally, the data which is processed can be stored in your distributed file systems such as SDFS or any other NoSQL or SQL based database. Now when we talk about Spark Streaming, it is good to know some of the features of Spark Streaming, and here you have some of the features. So it enables fast recovery from failures. while it is working on streaming data, you have better load balancing and resource usage. And you can also combine the streaming data with static data sets and perform interactive queries. Now, your Spark Streaming also supports native integration with advanced processing libraries, and that is one of the benefits users can have when they are using Spark Streaming. Let's learn about working of Spark Streaming. So, as I mentioned earlier, at one end, you have your data streams. Now, those data streams are then caught or received by your receivers, which we have to enable in our application. Your data streams or streaming data, which is constantly getting generated and flowing in, is broken down into smaller batches, which will then be processed by Spark. So you would have your final processed results. Now, if we look at the bigger picture here, we will talk about live input data streams that could be divided into smaller batches. And when we say batches, these are batches of input data as RDDs. So Spark Streaming performs computation expressed using these streams. It generates RDD transformations. So you would have your Spark batch jobs to execute RDD transformations, which would give you your final processed result. Now, there are various examples, and we'll look at examples later. So once your Spark Streaming works on breaking the input into smaller streams, it can then process the data, finally giving you batches of your result. And that is again on the streaming data. Now, what is these D streams? Let's understand about D streams or discretized streams. So that's the basic abstraction provided by Spark Streaming. Now, it represents a continuous stream of data, either the input data stream received from the source or the process data stream generated by transforming the input stream. Now here, if we look at the D stream, we would say you would have series of RDDs or series of transformations applied on the data which is flowing in for a particular time frame. Now here we say data from time 0 to 1, and that would result in some of the transformations which you would perform on the data when it has come in between this time zone or time frame. You would have again data from time 1 to 2 and so on. So that's how your Spark Streaming works. So if we look at your different transformations, now there could be various transformations which could be applied on your data. So this is something like your streaming data which comes in. You would want to say have a receiver which monitors a particular socket or a particular port and looks for data coming in. We would also define the time interval, and for that time interval the data is taken. So that's a smaller batch or a D stream on which you could have your processing done. Now within your application you would have series of steps which are nothing but transformations which would be performed on this data within this time frame, giving you a result which could be stored, which could be seen on your console, or which could just be pushed further for processing. And this keeps happening at regular time intervals, whatever you have specified, till the Spark Streaming application continues. Now, when we talk about Spark, we already know that there are different kind of transformations which can be applied. So you have map transformation, wherein you have map and then you pass in a function which basically says you would want to perform a function on every element. So when we say map function, that would return a new D stream by passing each element of the source D stream through a function which is passed. Similarly, it is for flat map, where you would be passing in a function. You would want to perform a flat map transformation on the data stream or D stream which comes in. So each input item can be mapped to 0 or more output elements. You could be doing a filter, wherein you return a D stream by selecting only the records of the source D stream on which the function returns true. So filtering is used when you want to run a transformation where you would want to look at the input data for a particular time interval, as I mentioned earlier, and you would want to filter that data as per whatever your function is applied. Now you could be doing a union, where you could basically be having a union of multiple D streams. So this would return a new D stream that contains union of elements in the source D stream and a other D stream. You could be doing a transform function that contains the union of elements. You could be doing a count. You could be doing a join. So these are some of the transformations which can be performed on your D streams. Now there is also a concept of windowing, and that is basically to process the data for a series of time intervals. So when I mention windowed stream processing, I'm saying Spark streaming would allow you to apply transformations over a sliding window of data. Now this operation is called as windowed computation. Let's see how it looks like. So if you have your original D stream, which is basically your data coming in, now that would be looked upon for specific time intervals such as time 1, time 2, and then you could be doing a windowed computation, which could basically mean that I could have a window which is a series of these time intervals on which you would want to perform series of your RDD transformations. So you have a windowed D stream at time 1, then at time 2 and time 3. So that could be one window wherein you would want to get an output. So here we see window at time 3. Now you could also have another sliding window which would take your time series, and we have time 3, time 4 and time 5 where you could be performing the series of transformations. So this is usually helpful where you would not only want to process the data at particular time interval, but you would want a consolidated processing for series of intervals. And that's what we mean by windowed computation. Now, before we understand about caching and persistence, we can talk a little bit more on windowing. So if one would want to understand the window stream processing, or as we say, Spark streaming's feature of windowed computations, we need to think it as applying transformations over a sliding window of data. Now, as we see here, every time the window slides over a source D stream, the source RDDs that fall within the window are combined and operated upon to produce the RDDs of windowed stream. Now, in this specific case, we can say the operation is applied over last 3 time units of data and slides by 2 time units. This shows that any window operation needs to specify 2 parameters. One is the window length, which is basically the duration of window. So for example, we can say 3 as we see in the figure here, and then you have a sliding interval, which is basically the interval at which window operation is performed. So these 2 parameters must be multiples of the batch interval of source D stream. So that's what we do when we talk about window. Now there are various other transformations which can be applied, or window based operations which can be done on your D streams. Here to talk a little bit more on D streams, which is, as I said, it's a basic abstraction provided by Spark streaming. It represents just remember it as a continuous stream of data. Now either the input data stream received from source or the processed data stream, which is generated by transforming the input stream. So a D stream is represented by, you could say, a continuous series of RDDs, which is Spark's abstraction of an immutable distributed data set. So any operation applied on a D stream, it is basically translating to operations on the underlying RDDs. Now, for example, we can say converting a stream of lines to word, the flat map operation is applied on each RDD in the lines. Now D stream to generate the RDDs of your words D stream. So when we talk about your discretized streams, understand that you would have a series of transformations which would be applied for this time interval, whatever has been specified. Now when you talk about your streaming or Spark streaming architecture, as I mentioned here, that is your receivers. Now that plays a very important role here. So your input D streams or data streams are representing the stream of input data that is received from your streaming sources. Now we could have different kind of data and we could be doing different kind of transformations. So your receiver is basically an object which receives the data from a source and stores it in Spark's memory for processing. And that's the main role of your receiver. Now Spark streaming provides 2 categories of built-in streaming sources. So you have basic sources, that is sources directly available in streaming context, which is a class, we learn about it, such as your file systems or socket connections. So those could be your basic sources from where the data is coming in. You could have advanced sources like your Kafka, Flume, Kinesis, etc. And they would be available through extra utility classes. So your receiver is going to be looking into the data which is constantly getting generated and then basically forwarding it for processing by your Spark streaming. When we talk about your Spark streaming, one more important aspect is basically understanding the caching and persistence. Now, as we know from the Spark core engine, or as you should know, that RDDs are, say, your logical steps, or RDDs are created when you perform some transformations. And these transformations or these computations or these RDDs can be cached so that it can improve the performance of your application. So the computed RDDs, or the RDDs which are result of performing some transformations, they can be cached so that they can be reutilized down your application for your further processing. So when we talk about your caching and persistence, DStreams also allows developers to persist the stream data in memory. So similar to your concept of RDDs, DStreams can allow you to persist the particular streams data in memory. Now that is by doing or using your persist method on a DStream, which will automatically persist every RDD of that DStream in memory. It could be every RDD or it could be specifically chosen RDDs. Now this is really useful if the data in DStream has to be or would be computed multiple times, say in your application. So for example, if we say window-based operations like reduce by window, reduce by key and window, wherein you have group of operations being done, or you could have state-based operations like update state by key. Now in any of these cases, your DStreams generated by, say, window-based operations are automatically persisted in memory without the developer calling for the persist method. Now for input streams that receive data over networks such as Kafka, Flume, sockets, etc., the default persistence level is set to replicate the data to 2 nodes for fault tolerance. Now, one thing which we should remember is, unlike your RDDs, the default persistence level of DStreams keeps the data serialized in memory. And that we can discuss again further about your serializations or deserialization. Now, one important aspect which takes care of your fault recovery is checkpointing mechanism in Spark streaming. Now, when I say checkpointing, a streaming application, as in real scenario we would want, must operate 24/7, and if the streaming application is constantly running, then there has to be a mechanism which can make your streaming application resilient to failures, which can be unrelated to your application logic. So Spark streaming needs to do the checkpointing. It needs to checkpoint enough information to a fault-tolerant underlying storage system such that it can recover from failures. So your checkpointing is the process to make streaming applications more fault tolerant or resilient to your failures. Now this is usually used when you would want to recover from failure of a node running the driver of streaming application. Now we know driver is existing for every application, and it is basically one which knows the flow of your application. Driver also has the context. In case of streaming application, we would have, say, the Spark streaming context, which is the entry point of your application. Now, when we talk about your checkpointing to ensure your streaming application is more fault tolerant, you have 2 kinds of checkpointing here. So you could have a metadata checkpointing and you could have data checkpointing. Now, when we talk about metadata, what does that include? So metadata includes configuration, DStream operations, or even incomplete batches. So when we talk about metadata, it has configuration. So configuration that was used to create the streaming application. You could have DStream operations, that is set of DStream operations that define the streaming application, that is your series of RDDs. And then you have incomplete batches, or batches whose jobs are queued but not have completed. So this would have to be checkpointed. So metadata checkpointing is used for recovering from a node failure running the streaming application driver. Now, your metadata, which has your configuration, incomplete batches, and DStream operations, need to be saved in an underlying storage system. Now, when you talk about data checkpointing, it is mainly about saving the generated RDDs to reliable storage. That is, whatever RDDs are computed. So, saving the information, which is saving the computations to a storage like SDFS. Now, that is used in stateful transformations, combining data across various batches. So when we we talk about transformations, whatever RDDs are generated, that depend on RDDs of previous batches if we are talking about stateful. And that can cause the length of dependency chain to increase or keep increasing with time. Now, to avoid any kind of increase in the recovery time, intermediate RDDs can be periodically checkpointed. And that could be done to a reliable storage to basically cut off the growing dependency changes. So if we would want to summarize, we would say metadata checkpointing is primarily needed for recovery from driver failures, whereas data or RDD checkpointing is necessary even for basic functioning if stateful transformations are used. And we should remember we are talking about stateful transformations here. So when we talk about checkpointing, now the question is, when would you enable checkpointing, or what would you do to enable checkpointing? So checkpointing must be enabled for applications with different kind of requirements. So for example, if you are using stateful transformations where one series of RDDs depend on the result of your previous batches, so something like update state by key or reduce by key and window. Now, if these kind of operations are used in your application, then checkpoint directory must be provided to allow for periodic RDD checkpointing. When we say about requirements, then recovering from failures of the driver, which is taking care of your application, metadata checkpoints should be used. When we talk about simple streaming applications without the stateful transformations, they could be run without enabling checkpointing because your one batch of RDDs really does not depend on the previous set of RDDs which were done in the previous time frame. Now, recovery from driver failures will also be partial in that case when you talk about your stateless. So some might be received and your unprocessed data might be lost. But then that's pretty much acceptable when you talk about Spark streaming applications. So here we look at your checkpointing. So we say start. Now you have a checkpointing. Now whenever your application is creating a streaming context, it would set a checkpoint path, and then you would define your D stream, which is nothing but series of your RDD transformations. Your streaming context starts, which is basically your application entry point into the cluster for processing. And at any point of time, if there is any failure, you could always recover using the checkpoint which was created. In case of Spark streaming, one more thing we need to remember is that your checkpointing can be enabled by setting a directory in a fault-tolerant, reliable file system such as SDFS, wherein the checkpointing information will be saved. So we will have to add some methods within your application like streaming context with a checkpoint and then pointing into a checkpoint directory. And in that way, we can have our stateful transformations or metadata information stored in the underlying storage, whichever we have chosen. Now that we have discussed about Spark streaming, some basics of Spark streaming, let's also understand about shared variables, or what we call as accumulator and broadcast variables. So normally when you talk about your Spark operations, such as your map or reduce, these are executed on one of the node of your cluster. And what happens is when you talk about your operations, they work on separate copies of all variables used in the function. Now, in this case, variables are copied to each machine and no updates to the variables on remote machines are propagated back to the driver program. Now, when we talk about read-write shared variables across tasks, that would be inefficient. So Spark actually provides two limited types of shared variables for common usage patterns, and those are your broadcast variables and your accumulators. Now, when you talk about your accumulators, these are variables that are only added through an associative or commutative operation. So Spark natively supports accumulators of numeric types, and programmers can add support for your new types. So when we talk about accumulators, they can be used to implement counters such as your map reduce or sums. So as a user, you can create named or unnamed accumulators. Now, as we see in the image here, a named accumulator in this instance counter will display in web UI for the stage that modifies that accumulator. Spark displays the value for each accumulator modified by a task in the tasks table. Now, tracking accumulators in the UI can be useful for understanding the progress of your running stages, but we should remember that as of now, this is not supported in Python. Might be in future, the support for Python will also be added. Now, when you talk about your accumulators, you can have, say, a numeric accumulator created by calling a Spark context and its method, such as long accumulator, or you could have double accumulator to accumulate values of type long or double respectively. So tasks running on a cluster can then add to it using the add method. Now we cannot, in this case, the value cannot be read, but driver program can read the accumulator's value using its value method. We can look at some examples to understand this later. Now, when you talk about your broadcast variables, that is one more type of variables, which allows the programmers to keep a read-only variable cached on each machine rather than shipping a copy of it with tasks. Now, what we know is sometimes you might be doing very costlier operations like joins, where you might be working on multiple RDDs, they need to be joined, and these RDDs could also be pair RDDs, which could be key value pairs. Now, whenever you're performing a join, there would be kind of two levels of shuffling. One, within a particular RDD. So if you're joining two RDDs, the first RDD, which might have data in the form of key value pairs, that RDD would have to have some shuffling where all the similar keys can be brought into one partition. And this would happen on the second RDD also, which has again key value pairs. And then if you're doing a join, these RDDs will be shipped to the node, or basically the data would be loaded in the memory, and then basically your transformations will happen. This can be a costlier affair. So what can be done is you could create broadcast variables. So for example, if we have two RDDs and we want to perform a join operation, and if one RDD is known to be smaller, then we can create a broadcast variable of the smaller RDD so that this variable itself can be shipped to each machine, and then this variable can be used for your join operations with the other RDD, which is existing in the memory of those nodes. So that saves time and that improves your performance. So Spark basically attempts to distribute the broadcast variable using efficient broadcast algorithms to reduce the communication cost. Now, if, for example, you have multiple nodes in a cluster, and if you would want to give every node a copy of large input data set in an efficient manner, so Spark actions are executed through a set of stages. Now we know that. And stages are separated by your shuffle operations. So whenever we talk about narrow dependencies such as map, flat map, filter, you would not have any shuffling involved. But if you go for group by key, reduce by key, and such operations to bring the similar keys together, there would be shuffling involved. And also this applies when you're doing some join operations. So in that case, broadcast variables could be a really plus, where one set of data or RDD, which is already computed, that could be broadcasted to other nodes. So the data broadcasted will be cached in serialized form and deserialized before running each task. This means that explicitly creating broadcast variables can be useful when tasks across multiple stages need the same data, or when caching the data in deserialized form is important. So we can create broadcast variables using Spark context and its method called broadcast. And your broadcast variable can then be shipped to other nodes, which can be used for your other operations. Now, when you talk about Spark streaming, it is used in various use cases. You could talk about speech recognition, you could talk about sentiment analysis, you could talk about streaming applications which would be performing some kind of analytics on the data which is coming in. It is also used widely in retail chain companies. Now, if we look at the example here, so big retail chain companies would want to build real-time dashboards so that they can keep a track of their inventory and operations. And for this, they would need one, streaming data, or data which is constantly getting generated at source, which needs to be processed on, and this information can then be populating your dashboards to give you a real-time scenario or real-time information of what is happening. So in case of an inventory dashboard, you could use then these interactive dashboards wherein you could draw insights about the business, and that's what retail companies are doing. So how many products are being purchased, or products that have been shipped, or how many products have been delivered to customers, and this kind of information would be good to capture in real time. So when the streaming data is basically being processed. So at one end, you have your data which is getting generated. That might be based on the sales which are happening. That might be based on the products which are being shipped, or that might be based on the acknowledgement that the products have been received. Now, while this data is getting generated at various sources, it can be subjected to a Spark streaming application, which will look into the streaming data, perform series of transformations which you would want to process the data at regular time intervals, and then pushing it to your dashboards or to your storage layer, wherein it could then be used to answer such questions. So when we talk about Spark streaming, it's an ideal choice to process this kind of data in real time, and there are various use cases. So at one end, if you see, you have an input stream which shows the product status. That is how many products were purchased or shipped or delivered. Now this would be then handled by your Spark streaming and also your Spark core engine, which would then process the data to give you an output stream, which gives you a status, such as what was the total count of products which were purchased, products which were shipped, and products which were delivered. So this was a quick and brief introduction to Spark streaming and how it works. Now we can also see how Spark streaming works, or how we create an application. For that, what we can do is we can basically set up our Eclipse to have your Scala based Spark applications. And for that, what you could do is you could have your Eclipse, which can then be having a Scala plugin added to it. Now, if somebody would want to look at the Scala plugin, then you can always go to scala.ide.org, and this is the place where you can scroll towards the bottom. You can click on stable, and that basically also shows you a video how Scala plugin can be added to your Eclipse. It also tells from where you can get the Scala latest release, and this can be added to your Eclipse. So in my case, it has already been added to the Eclipse. I'm bringing it up here, and then you can have your applications built using your IDE. People would prefer to use IntelliJ, and that's also fine. So you could also look for videos on setting up IntelliJ with your Scala plugin. Now there are two ways. One, you can build your application, run it on your Windows machine, wherein you could have some kind of utility like Netcat, which can be used to send in some messages in a streaming fashion. You could have a receiver which looks at a particular socket at a particular port, and you could build a streaming application within your IDE, run it on your Windows machine in a local mode, which would then be looking at your source where the data is getting generated. That's one option. The second option is you could build your application, package it as jar, and then run it on a cluster. Now that could be a Spark standalone cluster or Spark with Yarn, and then you could be packaging your application using tools like SBT, and then use Spark Submit to submit your application. Now I'll show you both the ways in which you can work with streaming applications. So first is get your Eclipse and make sure that Scala plugin is already added. Now in my case, on the right top corner, I see Scala symbol that says I can be using Scala Perspective. Now here I have some projects. So what you can do is you can create a project by saying new Scala project. You can give it a name. So for example, I could say my apps 3, and then you can say finish. So that creates a project. Now within your project, what you can do is you can create a package. So for example, I could say something like main.scala, and then say finish. So that creates your package. Now also one thing to remember is it would be good to change your compiler instead of 2.12 to 2.11. Normally for different environments you might have Spark with different versions and Scala with 2.10 or 2.11. So it would be good to have the compiler change to the bundle 2.11. So we can select this project. I can do a right click. I can go to the build path. I can say configure build path, and then I can click on Scala compiler where I will use project settings and I will choose to 2.11 bundle. So that would make sure that your applications can compile. Just say OK. It might say the compiler settings have changed. A full rebuild is required for changes to take effect. Just hit on OK. So that's the first thing you need to do. The second thing is, for your code to compile, it would be good to have your jars added to your build path. Now we could do that, or as I said, you could be writing your application which might not compile within your IDE, but you could package it using SBT and then run it as jar. So what I'm doing here is, on my machine within my C drive, I already have Spark distribution which I've downloaded. So basically I have downloaded Spark and then untarred it. So Spark 2.4.3, I have unzipped or untarred it. I have kept it in my C, and this basically has my Spark now, within which I have my jars, and this has all my Spark related jars. So technically speaking, I can even use Windows command line and I can start working on Spark in an interactive way, or packaging my application and running it in a local mode. So you could also do this. So basically have your Spark, and then if you see on my desktop, I have a Hadoop folder within which I have a bin folder, and within which I have a winutils.exe, and this will be basically required when you want to try out your Spark based applications, whether that is streaming or data frames, to be tested on your Windows machine. So you can always search and download the winutils.exe, place it in a Hadoop folder within the bin folder on your machine. So once you get your winutils.exe, once you have your jars, what you can do is, for your project, you can just say right click, you can go to the build path and you can say configure build path, and here you had add external jars. So we can select all of these jars here, which I would want to add to my build path so that my code can compile, and I can test it on the Windows machine itself. I can say open and then just basically do apply and OK. So that has created my project with a package. My compiler is changed to 2.11. I have added the external jars, the Spark related jars, and that is good enough for my code. Now what we need is a streaming application which we need to build. So let me show you from my existing project how it looks like. So within your source, the same way I have main package, and here I have a streaming application. So this streaming application is to test or to work on capturing the data which is generated at this particular stream on a particular IP and a particular port, and I would want to do some series of transformations on that. So this gives me an example of doing a word count, and then I would want to print the results. I could also be saving the output in a particular location. So for this application, we need basically to import certain packages, that is, say Spark Streaming, Spark Context, and also you have Spark Conf. So these are the packages which we need to import. Now here I have created an object. I've called this fifth app, and I'm saying extends app. And this is because within my project, I already have an application which has been defined as main. So if your application has been defined as main, one application is already existing, then you can just have your new objects with extending app. So we don't need to define the main method here. Now here I'm saying val conf new spark conf. So I'm creating a configuration object. I'm setting my application name, and to test it on Windows, we will have to set the master as local, and it is advisable to give it more than one thread, because you would be creating a receiver within your application that would utilize one thread. So here I'm saying set master local, and then I'm saying 2 threads. I'm also creating my Spark context, which we need to initialize based on the configuration object we just created in the previous step. Then we need to create a Spark streaming context, and this streaming context depends on Spark context, and I've given a time interval of 10 seconds. So this is the time interval which I'm setting, for which I would want to work on the stream of data which comes in every 10 seconds on a particular socket. Now here we are setting up a receiver. So I say stream RDD, which is basically be Spark streaming context, and then you use your socket text stream. Now there are various methods of Spark streaming context. For example, if I just go here and if I just do a dot, it shows me what are the different options. You have file stream, you have queue stream, you have socket stream, receiver stream, and so on. So I am using socket text stream and I would want to point it to this machine. So I'll say 127.0.0.1. I will also specify port 2222. Okay, and here once I have created my configuration object, my Spark context, my Spark streaming context with a time interval, and I have set my receiver to use the socket text stream method on this particular IP, on this particular port. Now then I'm specifying what I would want to do on the data which gets generated on this machine at this particular port. So I'm saying val word counts. So I would want to work on the stream RTD, that is the D stream. I would want to do a flat map on it to split the data based on space. I would want to map every word to word comma 1, and then I would want to do a reduce by key. Now reduce by key, you can pass in specifically the function you would want to do. I could do a count of this, I could print the result, or I could even save it with an output using the Java method to create a random string attached to the output. Once you're done with this, here I'm mentioning Spark streaming context start. Now this will basically trigger my Spark streaming context to start, and it will run till we terminate this application. Now here, to run this on Windows machine, you can always look into your run configuration. And what I have done is in my environment, I basically want to use, let's say, okay, now let's look at the configuration, what you need to set. So here I have my streaming application, and let's look at the run configuration, which basically shows my application has started and it's running on the environment. So if you see here, I have added Hadoop_home pointing to this Hadoop directory which has bin and win utils X. I have also given Spark local IP, which is 127.0.0.1. So that is my run configuration. Now if you see here, my streaming application has started. My streaming application has not yet started. Probably it is running a different application. So we can come back and check this. So we can go to run as Scala application and let's see what it does. So it tries to connect to 127.0.0.1. So receiver is trying to do that, but it does not find anything on that particular machine, on that particular port. So my receiver is not able to find, it is not able to establish a connection. Now what I can do is I can go to my command line, and here I will go into downloads. So I've already downloaded the netcat utility for Windows, and here we can basically search for something which I have on my machine within downloads, and that is your netcat utility. So what I would do is I will come back here and I would say nc.exe lvp, and then I could say my port which I have specified in my streaming application, and I can just start this netcat utility. Now here it says listening on 222, it says connection to 127.0.0.1, and then if I look in the background, my receiver will now be able to establish a connection with this netcat utility. Now whatever I type here will be taken for processing every 10 seconds, and we would see a word count while my application is running. So let's test this. So I'll say this is a test is being done, and as soon as I pass in this message, we see that there is a word count happening for the stream of data which is coming in. We can say winters are coming, winters will be cold, and once I given these messages, we will see our streaming application which will try to work on the data which is coming in and process it and show us the result. So we can say this is a test of winters, and let's see if it continues to do the processing and shows us the out, right? So my streaming application is running fine. It is looking at the words which we are passing in, and we can say if it is able to process my data, and every 10 seconds the text talk socket stream is looking on this machine at this particular port, doing a series of transformations, and these series of transformations and then are seen within your console. Now in my application, if I had used word counts.save as text file, then I could also have my output getting generated at every 10-second interval, and that would get saved here. I could also decide to have my output saved and stored on a SDFS or any other storage. So this is a simple streaming application what we saw, which is using socket text stream. It is looking at this machine on a particular port where we are running a netcat utility. It does series of your RDT transformations, that is flat map, map, and then you're reduced by key. And finally, we are invoking an action such as print, which basically triggers these RDTs, which work on my streaming data. So this is one example. Now what I could also be doing is, this is particularly my application. Now I already have SBT for Windows installed. So I can be going into my project space. So I could say workspace. I could go into my apps and I'm in my project folder. So I could say SBT package, and this will basically then, based on my build file, which I already have within my project folder. So if you see here, this is my build file, which says name, the version, Scala version, Spark version, and the repository with the Spark to manage the dependencies for all its components like Spark Core, SQL, MLlib, streaming, and Hive. So you need to have this build.sbt file within your project folder, which can be used to package your application as jar. Now we have done the packaging and it shows me that it has created a jar of my applications within this particular folder. Now once I have this, I can basically then import this package into my cluster where I can run it on a cluster using Spark Submit. Now to run the Spark streaming application on a cluster, here I have a 2-node cluster which will then have my Spark standalone cluster. You could look at the previous videos wherein I explain how to set up a Spark standalone cluster. Now here I can go into the Spark directory, and then I could just say sbin start all.sh, which will start my Spark master and worker node. Now I do have Hadoop cluster also set up on this, but right now I'm running a Spark standalone cluster, which shows me I have a master and a worker process on this machine, and I have a worker process on this machine. So my Spark standalone cluster is running. We can always bring up the UI to see how it looks like. So here I can just be giving http://um18080. So that's my Spark standalone cluster with 2 worker nodes. Right now there is no application running. We can come back here and we can check if we have my jar file. So I've already placed my jar here. Now at any point of time, if you have your jar which has been packaged, you can always go and do a jar minus xvf, and you can choose your jar to see what is within your jar, which I've already done on this machine. So if I look in the main folder, I have Scala, and within Scala, if you see, these are the different classes what we have. So my code was packaged as a jar. It has a 5th app class which we would want to run here. So what I can do is I can just be saying Spark Submit, because now I would want my application to run on the cluster. So I can say class main.scala and then my object name. So I will say 5th app. Now that's my class. My jar is this one, and we will also say master, which is going to be Spark, which is running on UM1, and it listens on 7077 port. So that would basically start my streaming application. But what we would also need is, like our Windows, we would also need some utility like netcat. So basically what I can do is I can here use a netcat utility to basically connect or send in some messages for our streaming application. So let's say, let me search if I have already the netcat, which I might have used here. So let's see. So on your Ubuntu machine, you will have to install your netcat utility by saying a apt-get netcat. So here I can say nc -l, and then I can say port, which is 2222. So we can see if this is working. So this is a test, and let's see if it works. So let's start our application. streaming application, which then needs the receiver to establish a connection with the particular machine. And let's see if that is done. So here I could also be canceling this and give it a particular port. So I can say 192.168.0.18. Now the only problem is when we packaged our application, we should be specifically giving the IP and also comment out the local. So when I package this to run on the cluster, I commented out this part, and I obviously would not be giving 127 but the IP where my netcat is running. So right now let's test it. So we will say this is a test, new test for our application, and I'm sending in some messages. So it is already doing the word count as we expected it to do. And if while we are doing it, if you come back here, so you would see your application is now running on the cluster. So it is my application. It is using 4 cores. What is the memory per executor? And you can basically click on your application. Now here you can look at the application detail UI to see what is being done. So for our application, we have a streaming job running receiver, which says this is my application. It says it is running. You can basically click on this, and it says your DAG visualization, which will say the streaming job which is running. You can look at the stages if you would want to see if there are multiple stages, which we don't have because we are not doing any wider transformation. We can look at storage if we have used some persisting or caching. We can look at the executors which are being used. And one of the important things when you talk about your streaming is the streaming tab which gets activated. Now that does not show up when you run your batch applications, but in your streaming applications you have the UI shows you the streaming tab, and that basically says running batches of 10 seconds for 2 minutes 9 seconds already. Now we see the input rate, we see the receivers, we see if there is any delay in scheduling, what is the processing time, how many batches it has completed, and it basically shows me what is the processing time, how many tasks were run, and so on. So my application is running fine, and unless and until we go ahead and cancel this, my application will continue to run. It will keep looking for messages which we keep typing in. So for example, if I would want to just copy this and start again, where I would keep passing in, this is a test 1 is this, where we test streaming application, right? And I can be seeing that my messages are being processed. I'm getting a word count. So we can say winter, summer, old, winter, and you can always look at if your streaming application is doing the word count. So this is a simple way where you can run your streaming application either on a Windows machine in a local mode, or you could be running on a Spark standalone cluster, or you could also deploy your application to run on a yarn-based cluster. Now that we have seen a streaming application which does a word count, it will be interesting to also see the window-based computation or windowing operation which is supported in Spark Streaming, as I explained. And for that, we can look at a different application here which is streaming with a window option. Let's look into this, what this application does. So here I'm importing some packages that is streaming context, your Spark and Spark context, Spark configuration. I'm also using the Spark API Java function. I'm then using Spark Streaming API, and I'm also using storage level because I also intend to have the persistence or caching done. Now here we create an application, say streaming app, extends app. We create our configuration object where we say app name, and then we set master with appropriate number of threads. We create the Spark streaming context, that's we initialize it, and then we have the Spark streaming context which depends on SC, and we have given a time interval of 10 seconds. We then set up a receiver, so we say stream RDD, which will use socket text stream like we did earlier, which will look for this particular machine at this port, wherein I'm also using storage level. So what I would want is that the data stream which would get generated here every 10 seconds should be cached in memory. Now we could use different storage levels. That is, we could use memory only, disk only, memory and disk. You could have memory and disk with replication factor. So you have different storage levels. Now here we are then doing some series of transformations like what we did earlier. But if you see in my previous example, we just had reduce by key, and here I'm using a transformation which is reduce by key and window. Now this one basically takes the function. As I said, the windowing takes associative or commutative functions. So instead of using the shortcut way, we will be specifying our function. So we say it takes A and B, and basically it uses this function. Now here we have to give the interval, that is 30 seconds. That's my window time frame. And then within that, what will be my each interval which we would want to look at. So these are the two main aspects. One is using your window based transformation, and then also specifying your time interval for your windowing, which basically means we would still do a word count, but then here we would basically not only be doing a word count for every 10 seconds for the data which is coming in here, but we would also want to have a consolidated set of computation done every 30 seconds. So that is looking at the last 3 time intervals. Now, if you also notice, I'm also doing a check pointing here, wherein I have not specified a specific directory, but what I'm saying here is I would want to checkpoint, or I would want to basically save my computations for any kind of fault recovery. Now, this is a streaming application with window-based computation. We are using storage level for persistence. We are also doing the checkpointing, which takes care of fault recovery. Now, to run this application, we have already set our environment variables and so on. So I can basically start this application by just doing a run as Scala application. Now, this would start my streaming application with window-based computations. Now we can open up our command line where we would want to start a netcat utility. So I could go to downloads. Let me just minimize this window here. And what I can do is I can then be starting my netcat utility. So I could say nc.exe minus lvp and on a port 222. As soon as I do this in background, my application receiver will be able to establish connection to this netcat utility running on this particular port. Now that's done. So we can see if the word count happens for our 10-second interval. So let's do that. So I'll say this is my first test, and if I do this, it should give me the word count for the data which I have passed in. Now I can say this is my second test, this is my third test, and if you see here, it basically is doing this. Now if I say this is my first test again, so since we are doing window based operation also, we will see a consolidated set of transformations which happen for a window of 3 intervals. So if you see here, now my this is giving me a count, but it is not showing me totally this as 4 or say this, because it is only looking at a window of last 2 or 3 time intervals. So now it is back because it is looking at the last one. So if I say this is my test, test is done, test is done. So if you do this, it will show you the word count which is for whatever you have passed in, like test is done is twice, test is thrice. But then since windowing based operation is done, you will look at the time interval of the messages which were passed within that particular window. Now we can also, since my application is running and it is on Windows, we can bring up your Spark UI. So I can go to http and / I can be looking at my machine and the port. So for example, I could do this. This shows my streaming application which is running in, wherein I can see the window-based application which is running. But what would be interesting is to look at the stages. If there is any kind of shuffling which is happening, looking at the storage should show me the persistence which we are doing. Now if you see here, it shows me that we have been persisting in the memory, what size it occupies, how many partitions were cached, and this is because of the persistence or the storage level what we have used as memory only. Now if we change that to disk, we will see our RDDs will be cached on disk. And then you can look at your streaming tab which gives you more information about your batches. So this is a very simple example. Obviously you can change what kind of RDD computations you would want to do here, whether you want to do a word count or something else, whether you want to save your processed output. Now here we are able to do that. You can always do a refresh on your project, and here what we see is we see some entries of a folder getting created, right? And we can decide whether we would want our output to be created. We can also see within this what would be containing, and since we have set checkpointing in the project folder, it would also be checkpointing temporarily the information for any kind of failure. So this is a classic example of streaming application using window-based computations, persisting your computations, and also doing the checkpointing simultaneously. Apache Spark MLlib, which is one of the important components used by developers or users for building their machine learning algorithms. Now here in this tutorial, we will learn about what is Spark MLlib, what is machine learning, about machine learning algorithms. You have Spark MLlib tools and different data types that it supports, machine learning pipelines, machine learning library algorithms, and then we can have a quick demo on Spark MLlib use case. Now, when we talk about Spark MLlib, of different components in Spark, such as Spark streaming, RDDs, your data frames or data sets, you have Spark MLlib, which stands for Machine Learning Library in Spark. The goal of this library is to make practical machine learning scalable and easy to implement. Now, when we talk about MLlib, this is Spark's machine learning library, and basically it provides tools such as ML algorithms, which include common learning algorithms such as classification, regression, clustering, and collaborative filtering. It also gives you featureization, that is feature extraction, transformation, dimensionality reduction, and selection. You have pipelines, that is tools for constructing, evaluating, and tuning ML pipelines. It has the features for persistence, that is saving and load algorithms, models, and pipelines. And then you also have utilities for your linear algebra, statistics, data handling, etc. So when you talk about your MLlib, it has a data frame based API, which is a primary API. Now, as of Spark 2 onwards, the RDD based API, that is in the Spark MLlib package, entered a maintenance mode, and your primary machine learning API for Spark now is data frame based API, that is spark.ml. We'll learn about that. Now, when you talk about machine learning and Spark's MLlib, it basically works on data which is collected. It can process the data, that is, you can build your machine learning algorithms using Spark MLlib. It also helps you in building data models, which can then be used for further processing. So before we understand about Spark MLlib and its features and its capabilities, it will be good to learn about what is machine learning. Now, machine learning is the science of training computers to learn from data and perform specific tasks without being explicitly programmed. And when I say training computers, it is basically training computers or making your algorithms learn by themselves based on the input which is provided. You have a lot of use cases for machine learning. Recently, I have been working in autonomous driving space, and again, there is a lot of usage of machine learning algorithms, especially in driver assistance systems, object classification, or even autonomous driving. You have various use cases where think about your mailbox, where you receive emails and they are automatically filtered and pushed into a spam folder. Now, how does that happen? So there is a machine learning algorithm running in the background which looks at the content of the data, probably looks at some words or patterns, and identifies your mail as a spam. Take an example of Google search, where you would want to search something and your auto-complete feature allows you to complete what you would want to search for and then helps you in finding something. Other companies can be something like LinkedIn, where you have data-driven services based on the connections a particular user has, based on the postings a user has done. You could have recommendations based on courses or job openings and so on. And this is happening based on recommendation systems, which are also a form of machine learning algorithms. So when you talk about your machine learning, you have to have human intervention. So you would have data which might be accumulated. Now that might be batch data, that might be streaming data, and your algorithms or computer or system has to learn from the past data, and then it should be able to predict the output. Now when we talk about analytics, there are different kinds of analytics. So you have prescriptive analytics, descriptive analytics, you have statistical analytics, you have preemptive analytics, and you have predictive analytics. And in various scenarios, machine learning plays a very important role. It's an important branch of artificial intelligence. Now, when you talk about machine learning algorithms, they can be classified mainly into three main categories. You have supervised learning based algorithms, that is, algorithms which depend on labeled data or data which has response based on the features and which makes it easier to predict the output. Now you might also have unsupervised learning algorithms that do not have labeled data or do not have responses. So they have unlabeled data and it is used to discover patterns from the data. You could also have reinforcement based algorithms, and in reinforcement learning algorithms, an agent receives a reward in the next time step to evaluate its previous action. So these are three main categories of your machine learning algorithms. Now, if we would want to learn more on supervised learning, look at the image here which says labeled data of dogs and cats. And if this is the kind of data which is fed into your algorithm, we'd process the data, wherein it would again depend on the labels. So looking at the images, labels would say, well, the first part of the image is dogs, or you have cats, and so on. Now, once the data is processed, then you could say your algorithm is trained, or the model which is being used is trained based on the past data which was fed in, and then you have your trained model which basically can then look at an unknown piece of data to predict the outcome. So you could be working on labeled data, training your model, and then basically the same model can be tested against a data which does not have a label, but your algorithm would be able to successfully classify or identify the object. Now, when you talk about supervised learning, it is classified into regression and classification. So you have various different techniques. You have linear regression, you have logistic regression, you have decision tree, random forest, support vector machines, k-nearest neighbors, naive Bayes, and so on. So when you talk about these, one of the primary criteria of choosing supervised learning depends on the data what you have and whether that data has label or no. Plus it also depends on what is the kind of output which is expected. And based on that, one which is a data scientist or a developer would choose if he or she would go with linear regression or logistic regression, decision tree, or anything else. When you talk about unsupervised learning, now this is where your data is still fed to the algorithm, but here our data does not have a label or a response. Now, how does the algorithm work in that way? So algorithm would look at the features. Now, for example, if you look at the image, we might say feature would be color of the element or the size of the element or basically the shape of the element or anything else which can categorize or help us in identifying the object. So your unsupervised learning based algorithms would learn the patterns in the data. And based on that, you would have your trained model, which could then classify or group your objects into specific groups, which have similar kind of characteristics. Now, again, for your unsupervised learning, that can be classified into clustering and association rules. So you have various, again, techniques and models here, such as k-means clustering, quite popular one. You have hierarchical clustering, you have DBS scan, you have principal component analysis, Gaussian mixture, and hidden Markov process. If you talk about reinforcement learning, so in reinforcement learning, it basically has to interpret the shape. Now, when we talk about reinforcement learning, as I said, an agent is provided a reward to identify a particular pattern. Then you could have your trained model, which basically would identify the element based on the shape or any other pattern. Now, for your reinforcement learning, the popular algorithms or techniques are your Q-learning, temporal learning, and your general adversarial networks. Now, when you talk about Spark MLlib tools, Spark MLlib component provides different tools. So when you talk about your ML algorithms, you have your classification, regression, clustering, and collaborative filtering. You also have for featureization, that is your feature extraction, transformation, dimensionality reduction, and selection. For your pipelines, you have tools for constructing and evaluating tuning or tuning your ML pipelines. For persistence, you have saving and loading algorithms, models, and pipelines. And then you have different utilities such as linear algebra, statistics, data handling, and so on. So when we talk about data types, so your Spark MLlib supports different data types. So it supports local vectors and matrices stored on a single machine as well as distributed matrices. Now for your Spark MLlib data types, as I said, it supports your local vectors and matrices. So it supports many data types, your machine learning library. Now you have local vectors and matrices which can be stored on a single machine, or you could have your distributed matrices which are backed by one or more RDDs. So your local vectors and local matrices are simple data models. They can be serving as public interfaces. Now you have certain tools like Breeze, which offers the underlying linear algebra operations. A training example which we use in supervised learning is what we call a labeled point in MLlib. Now when you talk about your data types, your categories could be local vector, it could be labeled point, it could be local matrix, and it could be distributed matrix. And then you have other criteria such as row matrix, indexed row matrix, coordinate matrix, and block matrix. So when you talk about your data types, now on the left we look at local vectors, where we are seeing a vector with certain values. You could have different formats supported here, that is dense format or sparse format. So if you would want to understand about vector data types, let's see this. So in your dense vector data types, a vector which is backed by a double array representing its entry values known as dense vector. So here we are looking at a double array representation. Now when you talk about your sparse format, this is a vector which is backed by two parallel arrays or two parallel array-like elements. So you have indices and values which are shown here in sparse vector. Now we could represent a vector such as seen on the first line 1.0, 0.0, and 3.0 in a dense format as a list of elements, or in a sparse format where we give the size of it by specifying 3, and then we give our elements, that is we are giving here 0, 2 and your 1.0 and 3.0. So here 3 is the size of the vector being the base class of your local vectors, and it provides two implementations such as your dense or sparse vector. Now we can basically create these dense vectors using Spark's MLlib package, that is linear algebra, which then supports your vector and your dense vectors for both the formats. We would have to import also some packages like Scala.collection immutable vector or MLlib.linearalgebra.vector. We'll talk about that later again in detail. When you talk about your labeled point data types, whether you're talking about dense or sparse, which is associated with a label or a response. So a labeled point is a local vector which could be of any of these types such as dense and sparse, which is associated with a label or a response. So basically when we talk about your supervised learning algorithms, they use labeled points, right? Because supervised learning algorithms depend on labels. Now here we use a double to store a label. Therefore, we can use label points in both regression as well as classification. Now a label could either be 0, that is negative, or 1, which is positive for binary classification. But if you have multi-class classification, labels should be class indices starting from 0, such as 0, 1, 2. And a labeled point is represented by your case class called labeled point. Now you have other data types also other than your local vector and label point. So you basically have local matrix. Now this has an integer type row and column indices and double type values that is stored in a single machine. Now here, when we talk about your MLlib supports dense matrices in which entry values are stored in a single double array in columns, as we see here with major order. Now when you talk about non-zero entry values, they are stored in compressed sparse column format. Now if we talk about an example, let's look at this matrix what we are seeing here, which has 1.0, 2.0, 3.0, 4.0, 5 and 6. Now your one-dimensional array is represented in the form of matrix, which has a size of 3 into 2. Here matrix is the base class of local matrix. It provides again two implementations. You can have a dense matrix and sparse matrix. And to create local matrices, we can use different factory methods implemented in matrices. Now, when you talk about your distributed matrix, that has a long typed row and column indices and double typed values. So this is when you would have your distributed matrix stored distributively in one or more RDDs. It is actually very important to choose the right format to store large and distributed matrices. So converting a distributed matrix to a different format can need a global shuffle, which is quite expensive. So there are 4 types of distributed matrices. So you have a row matrix in Spark MLlib, which is a row-oriented distributed matrix without having any meaningful row indices. You can say it is mainly dependent on RDD of its rows, where each row is like a local vector. When you talk about something like indexed row matrix, the difference with if you compare your indexed row matrix with just your row matrix is that you have some row indices here. So indexed row matrix is backed by an RDD of indexed rows in comparison to row matrix, which is RDD of rows. Now here the index is long typed and a local vector represents its every row. You could also have a coordinate matrix which is backed by RDD of its entries. So we can say each entry is a tuple here of, you can say, I as long, j as long, and value as double. So it's a row index where you could have a column index and the value. So these are your different types when it comes to your distributed matrix. You also have something called as block matrix, which we do not see here. But when you say block matrix, it is basically RDD of matrix blocks. Now, to understand matrix block, it is a tuple of int, matrix. So to understand these different data types, we can look at some examples and then it would be more clear in understanding different data types which your MLlib supports. When we talk about your MLlib basic statistics, now just looking at an example here, MLlib provides summary statistics for RDD, that is basically a vector, through the function call stats available in statistics packages. So we could be using, say, PySpark to work on MLlib. So you have PySpark.mllib.stat and you could import statistics. You could have your Spark context initialized. You could have your RDD of vectors. And then you could compute column summary statistics using your call stats on your RDD. So here we say summary equals statistics.callstats on mat, and then we could print the mean, variance, or num of non-zeros. So call stat returns the column-wise max, minimum, mean, variance, number of non-zero values, and the total count. Now this is just a simple example of using your MLlib and the statistics package. If you look further, and if we look at this example where we say MLlib can perform correlation between two series of data, again using your statistics package. Now in this example, we see we are using the PySpark MLlib stat where we import the statistics package. We would define our Spark context. We would then have our series. Now when we say series X and series Y, we are talking about two series on which we would want to perform correlation. So you have a series and the other series must have the same number of partitions and cardinality as your series X. Now you could be computing the correlation using Pearson's method. You could enter Spearman for Spearman's method, and if a method is not specified, Pearson's method will be used by default. So here we are saying print statistics dot correlation, that is CORR, on these two series, and the method which we specify is Pearson. Then we have data, that's an RDD of vectors. So based on the type of input, if there are two RDDs which are of double type or an RDD of a vector type, the output would be a double or a correlation matrix. So this example just says that you could calculate the correlation matrix using Pearson's method, and you could also be using Spearman for using your Spearman method. When we say print statistics correlation, I could be saying I would want to work on a data which is a double RDD or an RDD of vector, and then I could be specifying my method. This is just a simple example of using Spark MLlib statistics basic package. Now, when you talk about simplifying methods, you have sample by key and sample by key exact that can be performed on RDDs of key value pairs or RDDs which have been converted as key value pairs. So your sample by key exact is not currently supported in Python, but in future the support might be added. Now this sample by key method or function will flip a coin to decide whether an observation will be sampled or not. You specify your Spark context, you specify the data, that is an RDD of any key value pairs, you give fractions, that is specify the exact fraction desired from each key as a dictionary, and then we use sample by key method saying data dot sample by key false and the fraction. So this is again one example, and we can look for these examples when we are looking into the demo of your MLlib. If you talk about your random data generation, then your random data generation is used for randomized algorithms, prototyping, and also performance testing. So if you would want to generate a random double RDD whose values follow the standard normal distribution of 0, 1 and then map it to a distribution of 1, 4, we could be using the random package here. So we say from PySpark.random import random RDDs. You create your Spark context. Now our aim would be to generate a random double RDD that contains 1 million IID values drawn from the standard normal distribution, evenly distributed in 10 partitions. So what we could do here is we could have your random RDDs dot uniform RDD, and here I specify my Spark context, I give the range, and then basically I say the number of partitions. So if you would want to apply a transformation to get a random double RDDs following the distribution of 1, 4, we could be using U, which is random RDDs.uniform RDD. You do a map and you use the lambda function to basically pass in the function which you would want to apply to get a double or a random double RDD with normal distribution of 1, 4. Now, when you talk about machine learning pipelines, now that is basically understanding your different stages, and that might include something like estimator, something which is evaluator, or you could also have your transformer. So machine learning pipelines provide a uniform set of high-level APIs, which is built on top of data frames, and it is usually and mainly used with your structured data or data which can be structurized. So it is used to create and tune practical machine learning pipelines. So as I said, when you talk about your pipelines, it would have basically your different stages. So when we talk about data frame, or in the older version of Spark, which was called as schema RDDs. So a data frame from Spark SQL is used as a machine learning data set. It holds a variety of data types such as text, feature, vectors, and labels. Now you also have something like a transformer algorithm, which is used to transform one data frame into another data frame. You have estimator, which gives you a model. So an estimator is an algorithm which can be applied or fit on a data frame to produce a transformer or to give you a model. And then basically you can have also an evaluator which will evaluate the model which was created. Now when we talk about pipeline overall, pipeline integrates your multiple transformers and estimators to specify a machine learning workflow. Now when we talk about your machine learning, there are two important pipeline components. You have transformer, which basically works on a data frame, transforms it to create one more data frame. When you talk about your estimator, you have a fit method which gives you a model, or you can say a transformer, which can be used for your further data processing. Now, before we understand about classification and regression in MLlib, we can just understand a little bit more on the classification and regression and what does that mean before we understand what are the different types for these two different type of algorithms. So when I talk about classification and regression in MLlib or in specifically machine learning and statistics, classification is a supervised learning approach in which your algorithm or computer program learns from the data input given to it and then uses this learning to classify new observation. Now this data set may simply be by class, like identifying whether the person is male or female, or that male is spam or non-spam, or it may be a multi-class too. So when you talk about different classification problems, you can have use cases such as speech recognition, handwriting recognition, biometric identification, document classification, and so on. When we talk about different types of classification algorithms in machine learning, then we have your linear classifiers such as logistic regression, you have naive Bayes classifier, you have nearest neighbor, you have support vector machines, decision trees, boosted trees, random forest, and neural networks. If we talk about regression in machine learning, then regression models are used to predict a continuous value. So predicting prices of a house given the features of house like size, price, etc. Or you could be having different other examples. So it's again a supervised technique. And when you talk about types of regression, you could have simple linear regression, you could have decision tree regression, random forest, you have support vector, you have isotonic, you have gradient boosted, and polynomial regression. Now, when you talk about regression, you could have your linear regression or you would have your logistic regression. In case of your logistic regression, this is used in different social and science applications. It is used when your dependent variable or target is categorical. Now, take an example. If you would want to predict an email is spam, then it could have an option as 1 or 0, which basically means whether the email is spam or it's not. Or take an example of checking if a tumor is malignant. And again, that could have binary values, which is 1 or 0. Or take an example of a content and you would like to classify it, whether that content is basically a science-based content or a social-based content. So in this case, you could be using logistic regression. Now, if we would have used linear regression for a problem like email is spam or not, there would be a need for setting up a threshold based on which classification can be done. Now, if actual class is malignant, predicted continuous value of 0.4 or threshold of value 5, right? Your data point would be classified as not malignant, which could lead to a serious consequence. Now, logistic regression can be very useful in solving such problems. If we talk about your binomial logistic regression, it is also referred as simply logistic regression, where it can predict the probability that an observation falls into one of two categories of a dichotomous dependent variable based on one or more independent variables that could be either continuous or categorical. Now, for this, I would suggest a little bit of reading on your dependent or independent variables, looking at your variate, univariate, multivariate variables, so that understanding on logistic regression can be in depth. Now, when we look at the example of binomial logistic regression, where we basically would want to work on a particular text file. So here we are using PySpark ML classification, and we are importing the logistic regression package. We would want to load the training data, and we would say specify a variable training. We say spark.read.format. We basically give a format and we load a text file. Now on that, what we would want to do is we want to use the binomial logistic regression. So here I say LR logistic regression, wherein you specify the maximum number of iterations, the parameters which you would want to pass, and elastic net parameters. You would want to fit the model. So you say LR model, and then you would want to do a lr.fit on the training data set. Now you could print the coefficients and intercepts for logistic regression using print and using string method str, and here you would be working on model.coefficients. We could also use multinomial family for binary classification. As shown here, you could fit the model on the training data set and finally print the coefficients and intercepts for logistic regression with multinomial family. When we talk about clustering in MLlib, then your MLlib supports following clustering algorithms such as your Gaussian mixture, latent Dirichlet allocation, bisecting k-means, and k-means clustering. So for k-means clustering, you could also be referring to, say, one of the easy examples of clustering, wherein this is basically an algorithm which allows you to cluster your data points based on some similarity. Now if you look at this is just a visualization of k-means algorithm, where in your set of data points you would select, say, random points, and then you would calculate the Euclidean distance or distance between different points with this random point. You would then shift the centroid in a cluster of points and again calculate the distance, and you would reiterate or iterate through this for a specific number of iterations till you can identify the right center point for set of cluster points which could be grouped together. So k-means clustering is a very efficient algorithm when you would want to cluster data points based on particular criteria. Have a look at this link for more details. Now here we also have an example of using k-means clustering. That is, you could be importing packages or modules such as NumPy, Math. Then you could be from your MLlib use clustering, wherein you would import k-means and k-means mode. You would load your file, and then you could be doing a map transformation where you would work on the values or the data coming in from this data.txt, and you could be performing a split based on delimiter or space. You would build the model using k-means.train method. You could evaluate clustering by computing within set sum of squared errors, and then you could save and load the model. Now we can see a demo on this, and then we could see how it works when you would create your applications using Spark ML or MLlib, and you could try and test those applications in a Windows-based setup or on a Spark cluster, or even where Spark works with Yarn. So let's have a quick demo on using Spark MLlib to solve some of our problems and see how Spark ML can be used. Now here I'll take an example of regression analysis. Now to understand regression analysis or regression line, it would be good to understand a little bit of basics about the equation of a straight line. And then we can see how regression analysis, which is a predictive modeling technique, which can be used to estimate the relationship between a dependent variable and an independent variable, which acts as a predictor. Now to understand regression analysis, let's just have some quick basics. So for example, if you would have a line, say y equals mx plus c. Now this is usually a form of line, or you can say usually the equation of line. So a straight line is represented in this equation where you basically have m and c as constants. Now let's see how would that look like when you are basically having different points and you would like to have a line which can represent these different points in a particular graph. So for this equation, if we would want to understand, let's take a simple example. Say I would say y equals 2x plus c. Now if this is an equation and if we want to plot a line for this equation, we could consider, say for example, we could take a table which could have x and y values. So let's say x and y, and here we can just put in some values for x. So for example, I would start with -3, -2, you can have -1, you can have 0, and then you can have 1 and 2. Now if these are the values of x, and these values can be seen on this particular place where we would want to plot a line for this equation, and regression analysis relates to this, and that's why it would be good to understand the basics of the equation of line. Now here, if your x value is -3, and if we substitute that in this equation, so we would get the value of y. So for example, here it would be wherein you would say, let's say this equation is y equals 2x plus 1. Let's say this is the equation. So if I had value of x as -3, that would be 2 into 3 -6 plus 1. So that would be -5 for the value of y. Now you could similarly, if x value was -2, then it would be -4 plus 1, that becomes -3. And similarly, you could calculate, so wherein you will get values as 1 and then basically as 3 and as 4. Now if we would want to point these values on the graph, then we could say for example, x, you have -1, -2, -3. So if this is my x for -3, and then y, I would go to -1, -2, -3, -4, and -5. So I could say my y point would be somewhere here, right? So that would be -3 being x and y being -5. Now if we have x as -2 and y as -3, then I could say I would have my point here. If I would say x is -1 and y is -1, so it would be here. So if we already see these points are falling in a straight line. Now if x is 0 and basically y is 1, so that would fall on the line itself. So we would put in here. Then basically we can have x value as 1 and y value as 3, so somewhere approximately here. And then you have the value of x value as 2, and then basically y value as 4, which would come somewhere here. So if I would join all these points, sorry for the curve, but then this would be a straight line. This would be a straight line. Similarly, we could take a different equation if we would want to see if this is a coincidence that we are getting a straight line for these points, or is there some kind of logic. So if I say y equals -x -3, and if I take a similar table where I would have the value of x and y, and x we can start with -4, -3, -2, -1, 0, and then 1. And if we calculate the values of y here, so if x is -4, then it becomes minus of -4, so that becomes +4, and 4 -3, that gives me 1. So if you have x value as -3, so it becomes minus of -3, and then that becomes +3 and -3, so this would give me 0. And if we calculate further for all these values, we would get say -1, -2, -3, and -4. So this is the values what we have got for y and x. And if we would want to plot these values where x is -4 and y would be 1, so we could get our point here. If x would be -3 and then y would be 0, we would have a point here. If we have x as -2 and y as -1, so it would be here. Similarly, x as -2 we have done, and then we have -2 and -1. And then we could say, for example, if x value was -1, y value would be -2, and so on. If x is 0, y would be -3, So if we basically plot a line joining these points approximately, it would give me a straight line. Now here, this is how your equation of a straight line is following a form of y equals mx plus c, where your c and m are constant, and here we say m is a gradient, and I'll explain what is gradient, and your y is an intercept, and your c is a constant. Now if we look at these numbers and if we look at these lines, we can also see that whenever a value of x is increased by 1, so basically we have -3, and then you increase the value of x by 1, so that is -3, it goes to -2, so we would see the value of y increases by 2. Similarly, you increase the value of x to 1, so y value will increase by 2, and so on. So if we would want to look into the graph, so if the value of x was -3, and if we increase the value of x by 1, we would see the value of y would also increase by 2. So where my x was -3 and my y was, say, -5, now when I increase the value of x by 1, that is, I move towards the left, towards the right, my y value would also increase by 2. If you further increase the value of x by 1, you would again see the value of y value increases by 2, and that we can see on the line. So this is basically the equation of a straight line. Now if we compare that with the second equation, even there we would see the same pattern which would be followed. So when you increase the value or you decrease the value of x by -1, you would see the value of y would increase by, y value would also be decreasing, right? So here if I say -4 has been increased by 1, so we would see the value of y is decreasing by 1, and then you again increase the value of x by 1, so you would see the value of y is increasing by 1. So if we understand these equations, then here we can see the value to what we see, the value of y which changes, or basically if you see the value of y here, so in first equation, whenever you increase the value of x by 1, it increased the value of y by 2, and that is what we see here, 2 in front of x. In the second equation, we see that whenever the value of x was increased by 1, your value of y was decreasing by 1, and that is what we see here. So these values, which is 2 or -1 in this case, are the gradients. Now at a particular time, your one of the point falls on the line of y-axis, and that is your intercept. So your y value is the intercept, your m is the gradient, and your c is the constant. Now this is what happens when we represent a line, whether the line goes in a positive direction or in a negative direction. Line is expressed in this form, which is y equals mx plus c, where m and c are constants. And if we look in graph, we see if the value of x is increased by 1 unit, then y value increases by 2 units. So this is how you can understand the equation of a line, which is represented in the form of an equation. Now sometimes you might also see that people would represent this equation as y equals b0 plus b1x, and that's also same as your y equals mx plus c, where your b0 is the constant, your b1, which is the gradient, is the slope of the line, and we could basically be representing this equation in any form. Now we could have basically x and y plotted on a graph. So if we had a small graph, we basically would want to find out if the value of x and if the value of y are related. That is, if you increase the value of x, does the value of y increase? If you increase the value of x, does your value of y decrease? So this is what we want to find out, and then we could basically get a line or a slope here. So you could either have a line going upwards or you would have a line going downwards. So this is how you understand the equation of a particular line. Now when we talk about real-time scenarios and when we talk about regression analysis, So if you have set of points which you need to work upon, if you have set of points, so basically finding a line that connects all the points possible is what you mean by regression analysis. So this line which connects all the points or all the possible points is called your regression line. Now this is calculated based on a least squares method, and we also need to minimize the estimated and actual value. So there are other points which do not fall on these lines, such as this or such as this, and these are called your residual points. Let's take a simple example to understand this. So for example, if I have x-axis, which is the height of a father, and y-axis is the son's height. Now we would want to find out if a change in father's height affects the son's height. So as we see the values of father's height plotted over x-axis, we could see or find out if that would basically relate to a son's height increasing or decreasing. So that could be represented in the form of your y equals mx plus c. Now if both of them increase, that is as the value of x is seen increasing, you see the value of y also increases, then that's a positive relationship. If the value of x increases but y decreases while x is increasing, now that is a negative relationship which would see a line going downwards. So your regression line or your regression analysis is about finding the relationship between dependent and independent variables. So let's look at this one. Now when you talk about your regression analysis, it's a predictive modeling technique. It estimates the relationship between a dependent variable, that is in our case we were saying whatever is on x-axis, and in an independent variable which is on the y-axis. So x variable can increase its value as much as it wants, so far an arbitrary value of x. We are predicting value of y. Now prediction is done using regression. So when you talk about linear regression, we would basically want to find out a line that can basically connect all the points. Also find out the points which would be your residual points, that is the points which are close to your regression line, whether your line goes upwards or it goes downwards. So your regression analysis is a supervised learning based powerful modeling technique, and it is basically used for predicting the unknown value of a dependent variable from the known value of an independent variable. Now to look at a use case, what we can do is we can look at a data set here, and we can use Spark MLlib to see an example on that. Now if we look at a data set here on my machine, which I have also uploaded in the Git link, so here you can look into this location where I have a sample data set which is called e-commerce customers. And if we would want to look into this data set, which is in a CSV format, let's look into this data set, and we can probably just look at some of the entries here. So we can say head might be -5. So this is the data set which I have, and it is in a CSV format where we see fields like email, address, avatar, average session length, time on app, time on website, length of membership, yearly amount spent. And then we have values for these. Now this is a CSV file. Now if we would want to find out what is the impact of yearly amount spent based on your fields, we would have to work on this data set. Now here we have some fields like email, address, avatar, and they would not have any kind of impact on yearly amount spent. So those fields are not required. But then we have other set of fields, which is basically your average session length, time on app, time on website, length of membership, and these fields are very important. So we could say your average session length, time on app, time on website, length of membership, all these are your independent variables. Your yearly amount spent is the dependent variable. Now, how do we do a regression analysis if we would want to work on this? So the first thing what we will have to do is, now as I explained earlier, your Spark MLlib has basically Spark MLlib basically has set of libraries and functions which can be used for your machine learning algorithms. So first, let's go to Spark, that is start Spark, and then import some packages. Now here in my machine, if we look in here, we have my Spark already set up. So let me see this. So here, if you see, I have a master and a worker running. And if I look at my second machine, I have a worker running. So I have a Spark standalone cluster, which has 2 worker nodes and 1 master, which we can also see from the UI. Now to test an application, first you can do the interactive way. And if that works, and everything is fine, you can even build an application using an IDE like Eclipse or IntelliJ. So here I see I have 2 worker nodes. I have my Spark standalone cluster running. So let's come in here and let's go back to this machine. Well, my Spark is already running, so I can just say Spark shell. Now there are other settings also which makes my Spark works with the standalone, but that's not the point here we are discussing. So we would like to do a regression analysis on this data set which has information about fields which can basically affect the dependent variable, which is yearly amount spent. As I was showing, we have average session length, time on app, time on website, and length of membership, which are the independent variables. So how do we work on this problem? So first thing is, let's import some packages which has these classes which will be used. So I will import one of these one by one, all of these packages. So import where we have your org, Apache, Spark, and that gives me a error here because I had a typo. So this is fine. So I import the package which is going for ML evaluation regression evaluator. Similarly, I'll go for linear regression. That's what we want to do here. Then let's import some more packages and we will go for log4j also. This would be good if you are building an application using an IDE, but we can just import the packages. Then we have a feature transformer, which is vector assembler. I'll show you the link where you can read more about it. And then we have vectors, because when you talk about machine learning, it would like to take the data as input in the form of vectors. So these are some of the packages which we have imported. Now, what we need to do is we need to get that data set, which we can create a data frame from. So here the path for my data set is this one. So this is the data set I'm interested in. So let me take this one, which is e-commerce customers.csv. Let's come here, and what we want to do is we want to just paste it here. I will use it, and what we can do is we can basically create a data frame out of it using this statement. Let's copy this, and here let's go into our Spark shell. Now what I'll do is I have imported the relevant packages. So I will say this is my file. So I'll say file : home hdu, and that's the path where I have my CSV file which I just showed you. So what we are doing is we are doing a spark.read.option. We are using header as true because we want the first row of that data set to be considered as the headings. We have option as infer schema. We say format as CSV, and then we are loading the file. Now this should basically create a data frame out of this file, which we can easily use to work on the regression problem what we have here. So let's just wait till it creates a data frame. We can always assign that data frame to a different variable. So let's do that by doing this. So we know we have created a data frame here. It shows me in the last line, org Apache Spark SQL data frame. So now I will assign this data to e-commerce data frame. You can always do a ecom df.show to see what does your data frame contain, and it shows me the values which we had in CSV are now transformed and existing in the form of a data frame, where we have fields such as average session length, time on app, time on website, and length of membership, which are basically your independent variables. And you have yearly amount spent, which is dependent variable. Now, what do we do with this? So basically now we would want to look at the schema of this data frame to understand the data types. And we can do that by just doing a print schema, which tells me what are the fields, what are their types, which are assigned to them. So Spark has inferred the data type based on the values. Now, what we can do is we can filter the columns here, especially the columns such as your yearly amount spent, so that we would want to project as label, right? So when you talk about supervised learning, you would have always data which would have a label or a response. So your yearly amount spent would be a response or a label, and your other fields would be more or less like features. So let's get this, and here we can just do this, which says val ecom. So I'm creating a new data frame df1. I'm taking df which has been created earlier, ecom df. I'm doing a select and I'm saying this yearly amount spent, which was the last column, would be the label. And then you have your other fields, which is your average session length, time on app, time on website, and length of membership. So I'm selecting all this data here and I'm creating a new data frame out of it. So that's also done. You can anytime do a ecom df1.show to see what is happening in this data frame. Now, one point, as I said, your machine learning expects data in an n-dimensional vector format, that is a matrix format. It does not like the data in an array or a list or something, although vector is also like a list which is vertically arranged. So if you would want to read more about your ML features or a feature transformer like vector assembler, then you can basically refer to this link which I have given here. And if you just go to your browser and just search for this, you should be able to reach to the Spark documentation which shows about vector assembler. Now what is that? It's a transformer that combines a given list of columns into a single vector column. You see here, single vector column. It is useful for combining raw features and features generated by different feature transformers into a single feature vector. So we have multiple fields here, that is time on app, time on website, length of membership, and we would want to convert those features into one column. And that's why we are using vector assembler, which we have not used so far, but we would want to use it. So we created a new data frame. Now here, if you see, I am using new vector assembler, wherein I am providing the input columns as the array, that is average session length, time on app, time on website, length of membership, and then I'm saying set the output column as features. So let's copy this. Let's come here in my Spark shell, and what I'll do is I will use this vector assembler and I will say set input columns, which will then have these fields as features. So earlier we did yearly amount spent as label, and now we have this one which will be your feature set. So now we have the data frame ecom df1. We have also the assembler which should have the values in the form of a vector, wherein the heading of that would be features. Now we have done this. Let me just close this window. And now once we have used our vector assembler, we can basically create a new data frame based on assembler, which will transform your first data frame which had labels, and then you are also using the features. So let's copy this, and I just want to avoid some time in typing all this and avoid any kind of manual errors. So here we are working on this assembler which we created in the first step, and then we are doing a transform using the first one, and we are selecting label and features all together now. So this is done. It has created a vector. Now, if you would want, this is a vector. If you would want, and you would do something like this, it shows me the label and it shows me the features. Now, all the features are in one column, which is basically the three fields which we have combined together. Now, we have done so far. We can do a show. Now we can create an object of linear regression. So this is where we are then moving towards machine learning, where we want to use the linear regression here, an algorithm which is already existing. We just need to use it. So I'm creating an object with this linear regression. Then I can use the fit method on my data frame. That is what we created here, which is ecom df2. So I'm using a new variable called LR model. I will use this object of linear regression, and then I'll use the fit method. So I'm doing this, and this basically is implementing the least squares method. As I said, when you talk about your regression, which internally uses the least squares. So this is also done. Now we have the model, and basically what we can do is we can extract information such as coefficients and intercepts, etc. That is your gradient coefficients and so on. So we can just go in here and we can try in this. This basically gives me the coefficients and intercept, which will make obviously more meaning to the data scientists who are looking for the coefficient values and the intercept values. Now further, we can also look at the summary based on this model, and we can do that by doing this training summary. We have the model, right, which shows the linear regression training summary. That's what we have in training summary, and we can print out how many iterations were done or the total number of iterations, which should show me 1, and that's perfectly fine. And then I can also print the objective history training summary in the form of a list. So that's also done. And finally, we can also list down our residuals, that is the points which are not on the line, which are far from the line. And one of the main things as a part of linear regression is that you would want to reduce the distance as much as possible. So this is list of my residuals. So this is a simple example of using your linear regression where we worked on a pretty much structured file, that is CSV, and this will give us information on your residuals, your gradients, your coefficients, and basically if we had a plotting integrated utility or software, we could have also seen this on a graph. So this is your linear regression and a simple demo on usage of MLlib. Further to this, if you would want to test or try this application, you can always refer to the GitHub link where I have given the sample data set, the code, and also some more applications. So you can look into this path, which is the Git link with my name here. And here you can be looking into Spark applications and setup. You can look into the Spark MLlib folder where I have given you the sample data set here, which is e-commerce customers, which I was using for this demonstration of using regression and linear regression. And you can also look into this linear regression document, which has the sample code, which we just now executed. Now for the application which we ran from an interactive shell, obviously we can go to the Spark UI, and here we can look for our application if you would want to look at the DAG and what it did. So here is my application. You can click on this. I can click on application detail UI, and which shows me that from the time we loaded data into data frame, wherein we created a data frame, what was the stage, what was the job number, we were doing a load, and it shows me what were the steps in the DAG. You can go further and you can look at all the show commands, what you did, where you were trying to see what is there in the data frame, and even towards the end where you have show or you have count at linear regression or sum at linear regression metrics. So we can always see these steps. How many stages did it take? How many tasks were running? And basically DAG, which will give you more information on what happened on your application. You can always look at different stages. You can look at the storage if there was any caching done. You can look at environment variables, executors which were used for this particular application and the steps it had. And we can also look at the SQL tab, which basically shows up when you are using Spark SQL and data frames. And we can look at the queries which were completed. Always click on a particular link, and that can give you more details on what was happening in the background when you were executing a particular query or using a statistical model. So this is how you can run your linear regression using Spark ML, and you can build a model, you can build a machine learning algorithm which is following a supervised way of understanding from the data, separating the fields as features and labels, and finally helping us getting the slope of the line, getting the residuals, and basically also doing a linear regression on set of data points, which finally end up in giving up a regression line. Let's have a quick demo on logistic regression and using Spark MLlib to solve a problem which is based on logistic regression. Now for that, let's also briefly discuss on what is logistic regression. Now this is a technique for traditional statistics and also goes well with machine learning, mainly to solve your classification problems. Now here outcome, that is the outcome variable or result, is binary. It could be 1 or 0, it could be true or false, it could be yes or no based on predictor variable. It's same as linear regression, but instead it predicts whether something is true or false.
instead of predicting something continuous like what we saw in linear regression. Now, instead of fitting data into a straight line, it fits points into an S-shaped logistic function or an S-shaped curve. Now, this S-shaped logistic function is called your sigmoid function. So you can search for sigmoid function in Google, and that could give you more information on how this function works. Now, it also depends on a threshold value which we would set. Now, below which we would basically have a probability of say 0, and above which we would have a probability of 1. So based on the threshold value which is set, we decide the output from this sigmoid function. So logistic regression is usually used for classification. It can work with continuous data or discrete data. Now, here we test if a variable's effect on the prediction is significantly different than 0. If not, then variable is not helping the prediction. So logistic regression's ability to provide probabilities and classify new samples using continuous and discrete measurements makes it a popular machine learning method. Now, with linear regression, as we saw, we fit the line for data points using a least squares method. That is, we find the line that minimizes the sum of squares of these residuals. Residuals are the points which are close to the straight line which we plot. Now, logistic regression does not have concept of residuals. Instead, it uses something called as maximum likelihood, wherein through iterations, the curve with the maximum likelihood is selected. So in case of logistic regression, we were seeing that when you have set of data points, you try to plot a graph or try to plot a straight line, which would be to have all the data points or maximum data points which would fall on that particular line. And that's how you find out the slope. In case of logistic regression, as I said, we would want to find out the probability of a result either being yes or no, or being true or false. So here the graph would look something like this. So it's a S-shaped curve where you would also have a threshold defined, and below which you could say that it would be say 0, and above which the data points would classify as 1, or below which the data points would classify as false, and above which they would classify as true. So that is the whole gist of your logistic regression. Now, how do we solve logistic regression? So MLlib also comes with different packages which can be used. So here we will try to solve a problem wherein the statement is you would want to predict a customer if a customer would be bankrupt or no. Now, this is probably for a bank which would want to identify if the customer is about to be bankrupt or no, and if customer will be able to pay back the loan. How do we do this? So for this, there is a data set qualitative bankruptcy text. Let me show you that. So here I have the data set. Let me come out of this. And here we can look at the data set which is in this location, and here I have qualitative bankruptcy.txt. This is the location, and if I look into this data set, it basically has some qualitative values which we will have to convert into quantitative. So if you look at these, this is the data set I have which has P and N and A and B. Now we want to work on this kind of data set to basically classify the customer if the customer is having more probability towards bankruptcy or no. How do we do that? So for that, what we can do is first we will start our Spark when we will import some packages which are more for your logistic regression. So here I will start my Spark shell. Now Spark MLlib comes with different classes and different libraries which help us in solving these problems. So it already has these algorithms, say linear regression, logistic regression, and many more which can be used. So here what we will do is first we will import the relevant packages which are required for our example. So import. Now this is what we have. So Spark MLlib. So I'm missing in something here, and then we can get the others also. So there is a correction here which I'll update in the Git also. So it should be MLlib, then we will get something else for the labeled points, and we will also get something for vectors, because when you talk about machine learning, it would expect the data in the vector format, for which in linear regression we saw using a feature transformer such as vector assembler. So these are the packages which we need. Now if you see here, I would want the data which we have to be understood. So the data file has these different fields, you can say, which are existing. So P is for positive, E is for average, N is negative, B is bankruptcy, or NB is non-bankruptcy. So this is the schema of the data file on which we have to work on. So what we would do is we would first transform each qualitative data in the data set into a double numeric value, which we can do using a function. So here we are defining a function called getDoubleValue. Let's do that. And this one will basically be declaring some variables, and then we would be converting the qualitative values into quantitative values. So that's the function. So let's copy this line by line, and looks like there was an error. Let me try it again here. So there was an error where there was an extra bracket, so I corrected that. So this is the function which will basically convert the qualitative values into quantitative values. Now once we have this, our function is ready. What we can do is further we would have to read the data in memory. Now here I would be using the older way, that is the RDD's way, to work on our data set. So I would be using val data sc.text file, and then I'll point it to my file, which is qualitative bankruptcy. So let's get that file from here. So let me open up a different terminal, and here the file is in this particular location where we have this qualitative data set. So let's take this, is what we are interested in. So here I would say val, and then I would say basically data equals sc.text file. So using the text file method of Spark Context, and here I would say file home htu, and that's my path of the file. So let's create an RDD of this particular file. Now once we have an RDD created, we can always see how much data we have here by just doing a data.count, and it shows me there are 258 rows which has these fields which we intend to convert into quantitative values using this function. Now once we are done with that, we need to prepare the data for logistic regression algorithm. So basically what we will do is we will do this where I will say parsed data. I will do a map transformation on my data wherein I want to split the data based on comma, and then I'm using the labeled point method wherein I'm using the function which we defined, which will basically then convert this data and convert the values into quantitative values. So let's do this, which says parse data, doing the map transformation, splitting the data based on comma as the delimiter, using your labeled point wherein I'm using the function, and then basically I'm going to convert that into a vector. Now once that is done, it has created an RDD which is based on MLlib regression labeled point, which we have used here. Once that is done, we can even print the data to see what are the values now, which should show me that my data, which was with attributes like P, A, etc., has now been converted into the quantitative values which we can use for any kind of computation. Now once this is done, then you can split your data into training and test data set, which will be used to train our algorithm. So what we will do is we would do splits wherein we are converting this into a 60 and 40%. So let's do this. Once that is done, I could then have my training data, which will be at index position 0, and I will have my test data set, which will have at index position 1. Once this is done, then we need to train the model. So how do we train the model? Now this is where we use the logistic regression algorithm with LBFGS, we will take this and we will apply this on our training data. Now, once this is done, we have a model which is based on logistic regression, which would work on our training data, which is 60% of our data set. Now, once this is done, it has basically given me a model, logistic regression based model. Now here I need to evaluate the model on training examples and compute the training error. So I can take this wherein I am working on test data. So that is being applied a map transformation where we would want to see if my model is working fine. So let's get this here. And that's done fine. So our model looks fine. Now we can basically get the training errors based on this. And once this is done, you can print your training error out of what you have done in the previous step. So that gives me training error of 0.20, that is 20% is the error. Now this is a simple example of logistic regression where we are basically reading data in memory. We are preparing the data to be used by logistic regression algorithm. We are then splitting our data into training and test. We are training our model and then we are evaluating our model on training examples and computing the training error. So this easily shows how we can use Spark MLlib to basically work on your problems such as linear regression or logistic regression. Now, since we have run the application, we can always come back here and we can look at our application which was launched using Spark Shell. We can look at application detail UI, which will show me what are the different steps we did when we were using Spark MLlib, and you can go into any one of these jobs and see what it has done. You can look at the DAG of the steps which were executed, which shows how we picked up the file, what kind of transformations we did, and finally how we got our resultant data. Now here, this is my Spark UI. If you would want to look at the code and the sample data set, you can find on the GitHub link in this particular place where you have Spark MLlib, where I've given you the documentation with the code. I've also given you the sample document, which sample data which can be used, and a notepad file which also has the code wherein there is one correction in our function which can be changed.
Spark SQL. We will learn about what is Spark SQL, what are Spark SQL features, its architecture, Spark SQL Data Frame API, Data Source API, Spark SQL's Catalyst Optimizer, running SQL queries, and then we can have a quick demo on Spark SQL. So, what is Spark SQL? It's a Spark's model or Apache Spark's module for structured data processing. Now, it allows you to work with structured, semi-structured, and even unstructured data, but primarily with structured and semi-structured. It originated to overcome the limitations of Apache Hive. Now we know that Apache Hive is a data warehouse package on top of Hadoop, and this basically is quite extensible. It allows you to work on structured data or data which can be structurized with the various features such as user-defined functions or support of complex data types or custom MapReduce scripts and many more. However, there are a lot of limitations in terms of using Apache Hive, such as it always depends on MapReduce as an execution engine or processing framework, or it could also use Days. You would not be able to do insert, update, deletes when it comes to Apache Hive. It is more of a batch oriented operation, and basically querying with Hive can be time consuming. However, Hive is quite extensible in the way it supports data warehousing use cases. It lags in performance. As I said, it goes for MapReduce and is not really suitable when you would want to do faster querying or ad hoc querying. It does not allow you to resume a job if it fails somewhere in the middle. And these are some high-level limitations of Hive. When we talk about Spark, it performs better than Hive. Now Spark, we already know, is a in-memory computing framework which basically works on having the data loaded into the memory, that is in the form of RDDs, and then having the DAG execution whenever a action is invoked. Now, if we compare latency in terms of hours, we would see Spark is quite competitive in that with Hive and is a better performant. When you talk about CPU in days or CPU reservation time, in all of these cases, Spark wins over Hive. Now let's look at Spark SQL features and let's understand how it helps. So as I mentioned, Spark SQL is a module for structured data processing primarily. Now, unlike the basic Spark's RDD API, the interfaces provided by Spark SQL provide Spark with more information about the structure of both the data and computation being performed. Now we know that Spark has a DAG scheduler behind the scenes, and if that DAG scheduler could know what are the steps which are part of your processing application, then it would understand the steps, it would benefit from data which would be structured and thus have a better way of processing your data. Internally, Spark SQL uses this extra information to perform extra optimizations. Now there are different ways in which you can interact with Spark SQL, including SQL and dataset API. You could be using data frames API, data source API, and also the older way, that is RDD API. Now some of these features really make Spark SQL a compelling framework for data processing and analyzing, especially if you have data which is structured. You can integrate Spark SQL and query structured data inside Spark programs. It is highly compatible with SQL based frameworks like Hive, so it can work on the data which is stored in Hive. It can work on the data which is stored in your RDBMSs, which are external to your big data setup, or even on the files which are stored on your distributed file system such as SDFS. When we talk Spark's integration with Hive, you can run unmodified Hive queries on existing warehouses in Spark SQL. So while existing Hive data queries and UDFs, Spark SQL offers full compatibility. Now, Spark SQL leverages the RDD model as it supports large jobs and mid-query fault tolerance. For interactive and long queries, it uses the same engine. So in terms of Spark 1.6 and older versions, we had RDD API. That is, whenever you do some transformations such as map, flat map, filter, and many more, that would create RDDs, and you can say logical steps in the DAG, which would be executed only and only when an action was invoked. Now in terms of older APIs, we said that Spark has RDD, and when we talk about newer versions of Spark, we have Spark data frames or data sets. And when we talk about data frames, that is using an implementation of RDD, which we call as schema RDDs. Or you could say in older versions of Spark, we were talking about schema RDDs, which get created based on your transformations. And in newer versions, the same schema RDDs are called data frames. There are different ways in which you can use Spark SQL. So you could use an ODBC or JDBC connector, and then you could be connecting to your external databases, business intelligence tools, and then extract the data from your underlying data stores and process them. Remember, Spark does not have its own storage. It has various components such as Spark SQL, streaming, MLlib, you have RDDs, and you have graphics. But then Spark always relies on a storage. Now that storage could be a Hadoop distributed file system, that could be a NoSQL database. It could also be a RDBMS to which you can connect using JDBC or ODBC, or it could be just your local file system on which your files are stored, and Spark can use those files and process the data within those files. Now, when we talk about your Spark architecture or Spark SQL architecture, you have basically at the lowest level, you have your data sources. Now that could be your data in CSV format or JSON format, or also coming in from external sources using your JDBC ODBC connectors. You have different APIs. So you have a data source API, we'll learn about it. You have a data frame and a data set API, which allows you to work with data. And then you have different ways in using these. So you could have a data frame domain specific language, that is DSL, or you could be using Spark SQL or Hive querying language to use one of these APIs to process your data. So Spark SQL is Apache Spark's module mainly to work with structured data. Now, when we talk about Spark SQL, it has three main layers. It has a language API. So Spark is very compatible compatible as it supports multiple languages such as Python, your Scala, Java, even R, which is used in data science activities, and your Hive querying language. When we talk about schema RDD, so Spark SQL works on schema, tables, and records. And what it creates behind the scenes is a schema RDD, or an RDD which has schema within it, which helps the DAX scheduler to understand the data and the steps which are being performed. And as I said, in newer versions, your schema RDD is your data frame, which is nothing but a representation of your data in the form of rows and columns with column headings, and you could call it as a temporary table where your data is getting stored. The third layer is your data sources. So that is your data coming in from varied sources. That could be your files in different formats such as CSV, JSON, text, Parquet, Avro, and so on. You could be getting your data from different NoSQL databases such as Cassandra, MongoDB, your HBase, or anything else. You could also be getting data directly from Hive, which are your logical structures such as databases and tables. However, the data is stored on an underlying file system such as SDFS. Now, when we talk about your data frames and data sets, so a data frame is basically a data set organized into named columns. So what is a data set? So a data set is a distributed collection of data. It's a new interface which was added in Spark 1.6, which provides the benefits of RDDs such as strong typing, ability to use powerful Lambda functions, and with the benefits of Spark SQL's optimized execution engine. So a data set can be constructed from JVM objects and then manipulated using functional transformations such as map, flat map, filter, and so on. So your dataset API is available in Scala and Java, and Python did not support the dataset API, but I think that's being worked upon for the future releases. When we talk about data frame, it is basically a data set organized into named columns, or we can say representing your structured data or semi-structured data in the form of rows and columns, with columns having headings. So it is conceptually equivalent to a table in a relational database or a data frame in Python or R programming language, but it has richer optimizations under the hood. So data frames can be constructed from wide array of your sources, such as your structured data files, tables in Hive, external databases, or even existing RDDs. So again, your data frame API is available in Scala, Java, Python, and R programming, and your data frame is represented by a data set of rows. We can just say data frame is a simply alias of your data set of rows. Now, when we talk about your data frames, let's also understand about your Spark SQL data source API. Spark SQL, it supports operating on a variety of data sources through the data frame interface. It supports your different formats such as CSV, Hive, Avro, JSON, Parquet, text, and so on. As we know about in Spark, it is lazily evaluated like your Apache Spark transformations and can be accessed through SQL context and Hive context. So as we have seen in previous tutorials, your Spark context or your Hive context, or in later versions what we have is Spark session, these are basically the classes which are your entry point of your application. So when you start a Spark shell in an interactive way or a PySpark, you would see the Spark context is initialized, or your Spark session is automatically initialized. If you're building your applications using an IDE, then we would have to define and initialize our Spark context and Spark session, which is in later versions of Spark. In older versions, you had Spark context and then you had SQL context or Hive context. It can be Spark can be easily integrated with big data tools and frameworks via Spark core engine. Now, before we learn about Spark Catalyst Optimizer, let's have a quick look. So if I look in my machine here, and if I look in my machine, I could look in my C drive, and if you see here, I have downloaded Spark and Spark 2.4.3. Now, if you could follow previous tutorials, you would know how to set up Spark on Windows. However, just for new people, I can just give here some information saying, let's look at environment variables. And here I have set up two important variables. One is your Hadoop underscore home, which points to a folder called Hadoop on my desktop, and I'll show you what is there in that. I also have Spark underscore home, which has been set to my Spark path. Now, what does my desktop and my Hadoop folder contain? It basically contains a bin folder, and within that I have a winutils executable, which helps our Spark when launching to just realize if there was a dummy Hadoop support here. Now, what we can do here is I can go into my command line, I can go into my Spark directory, and then I can go in bin here. If I just do a dir/p, I would see that within this I have different binaries or different programs, and what we can do is we can just start by doing a ./Spark shell. So this is basically an interactive way of working with Spark. For people who would be more comfortable with Scala as a programming language, they could use Spark shell. Or if people are comfortable with Python, then they could be using PySpark. So here I'm trying to launch the Spark shell, which will run in a local mode. It will not be contacting any yarn or resource manager. However, it will just start an application locally on this machine. It will initiate the Spark context, as I mentioned earlier, or basically your Spark session, depending on which version of Spark we are working on. So if you see here, I have Spark version 2.4.3, Scala is 2.11. It has a Spark context which is available as SC, and Spark session which is available as Spark. So this basically allows me to work either with RDD API using SC, or I could be creating a data frame using Spark. So both of these classes have got initialized, and they will act as an entry point of my application into the cluster. In older versions of Spark, which is 1.6, we still had Spark context available. But then if we wanted to work on Spark SQL, which was launched in an experimental way with Spark 1.6, we could be using, instead of Spark session, we could be using SQL context or Hive context. So this is the Spark context or Spark session which is getting initialized. If I was building an application using IDE, then I would have to, depending on my use case and need, I will have to initialize Spark context or Spark session within my IDE. Coming back and understanding about your Catalyst Optimizer. So when we talk about Catalyst Optimizer, what is it? And what does it do? Spark, your Catalyst Optimizer, leverages advanced programming language features such as Scala's pattern matching and Casi quotes in a novel way to build an extensible query optimizer. So what it does, it works in 4 phases. Your Catalyst Optimizer, it analyzes a logical plan to resolve the references when you are querying the data. It has a logical plan optimization internally, which will come up with the best way to get to the data. It has a physical planning layer, and then it also does code generation to compile parts of query to your Java bytecodes. When we talk about your Catalyst Optimizer, we can say if you have a SQL query, now that SQL query would result in an unresolved logical plan, which can then help in analyzing the logical plan, and it also depends on the reference to internal catalog, which has information about your data which you are trying to query. Then there is a logical plan based on the analysis, and a logical optimized plan which is post your local logical optimization, which then relates in physical plans, and a cost model which helps the Catalyst Optimizer know what is the best way to reach and access the data. It gives away a selected physical plan which will then generate code based on the RDDs which would be implemented based on your query. Now that's how Catalyst Optimizer works. When we talk about SQL context or Spark session, as I explained, it is a class used for initializing the functionalities of Spark SQL. So in older versions of Spark, such as Spark 1.6, when you would start your Spark shell or when you would start your PySpark. So we can see that here. Now I could just do a simple quit and I could then try bringing up PySpark, which is also a binary or a program to work with your Spark, but then that brings up your Python's shell, and useful for people who are well versed with Python as a programming language. Now if you see here, we again have Spark context initialized as SC, and then we have Spark session available as Spark. If I was working in older version, I would not have Spark session, but I would have SQL context, which could be used to use the functionality of Spark SQL, or basically using Spark to work with structured data. So your SQL context is a class which is used for initializing the functionalities of your Spark SQL, or you can say it is the class which becomes an entry point of your application for the resources which your application would need for processing. So we could just start a Spark shell, and basically that would start your Spark context or Spark. So when we talk about this Spark context or Spark session, you can also create a SQL context or a Spark session using something like this on an interactive cell. So you can say val SQL context equals new org Apache SQL context SC, and you could then start building your application. I will show that how you do that in your IDE, wherein you have to initialize your Spark context. However, as I said, in Spark shell or in PySpark, your Spark context gets initialized automatically, and you can work with your RDD API, or you could be using Spark session, which is available as Spark to work on Spark SQL, whether you're working with PySpark or you're working with Spark SQL using your Spark shell. Now moving forward, when we talk about Spark session, so this is an entry point to any functionality in Spark. So to create a basic Spark session, you could be using a Spark session.builder if you're working in an IDE like Eclipse. So here you have to import a package that is org Apache Spark SQL Spark session, and then you could create a variable such as val Spark. You could use Spark session.builder. You could provide an app name. You could also provide config properties, that is your configuration properties, and then you could say get or create. Now that creates Spark, which can then be used to work with your Spark SQL. You could then do import Spark implicits and continue to work. Now here, let me start my Eclipse parallelly and I can show you how it looks here. Now, when we talk about working with data frames, either we can be doing that using your Spark shell, PySpark, or we could be using our Eclipse. So let's see how we can work with data frames here. So let me just quit PySpark and let me get into Spark shell. So I could just do this, and this will start my Spark shell. That's an interactive way of working with my files. I could be using Spark here, and I could be using Spark session. Now for this, we would need some files. Now I could be working on Windows or I could be working on my Linux machines. So here I can show you both. Now this is basically a Spark standalone setup where I have set up things. You can refer to the previous tutorials where I have shown how you can set up Spark standalone or Spark on your Windows. I've started my Spark standalone cluster. If I look at the processes on these two machines, that would show me that I have a master and two worker processes. I can also open up the Spark UI if we would want to look into our applications. And here we can just say http://um1 and then 8080. So that shows me my Spark standalone cluster, which had two worker nodes. As of now, there are no applications which are started, and we can start Spark shell here. So I can go into user local Spark, and then I can see that I have basically a bin folder which has my programs or binaries which we can use. Now we could be using that from anywhere because in my bash RC, I have set up my Spark path. So that will allow me to give my Spark commands from anywhere. And here we can also see that I have some data in sample files. We can pick up one of the files here, which we can then use to create a data frame. So I can just say Spark shell from my home directory where I will target a JSON file, which is already here, to create a data frame. Now, once I'm starting my Spark shell, it basically shows that it has started an application. It shows a UI which is available. It is basically interacting with my Spark master. There is Spark context available as a SC and Spark session, which is available as Spark. Same thing we see in our Windows machine. That is, you have Spark context, a web UI available, which I can launch. I can look at Spark context available and Spark session, which is available. Now, taking this file, what we can do is we can say val x, and then I can say Spark, which is the short form of Spark session. And then if you are not sure what method should be used, you can just do a tab and that will show you all the possible options which are available within Spark. So here we can use read and again do a dot and then do a tab, and it shows me that we can get our data in different formats. Now by default, if you do not mention a format, then it will expect the file which you are working on in a Parquet format. We can use a load method here, or I can just say spark.read.json and then I'll point it to a file which is in my sample files folder, and I will point it to people.json and I can hit on enter. Now here, since we are using Spark session, we will see if it creates a data frame. Now if you see here, it is pointing to a driver issue, basically saying it is not able to reach MySQL or the meta store. So by default, Spark also expects if it can connect to your meta store, which is being used by Hive. So now I'm on my right machine, UM1, where I have my MySQL installed, which I just checked by testing, and I have my MySQL installed here, which is being pointed within the Spark conf by hive-site file. So now I will start my Spark shell again here, which should bring up your Spark context and also your Spark session. It will basically interact with Spark master, which is running on this machine, and as we have given in the conf and in your Spark default conf. So once my Spark shell has started, I can start doing this. I can say val x spark.read.json, and then I'll point it to a file which is in this directory called people.json. So that's the file and it is in sample files directory. Now once we do this, we are using Spark session, which is available as Spark, and when I do this, it refers to the config files, and then it is able to internally discover the Hive's meta store, which is in a MySQL database. That's because of the way I have set up my Spark standalone cluster also, so that it can work with Hive. Now here we see that a data frame has got created, and we can always look into this. So I can just do a x.show to see what is in my data frame. So we pointed to a JSON file, and my Spark session allowed me to create a data frame. Now at any point of time, unless and until you use a show or an action, you will not see the result. It would just create a data frame. Now here we have x.show, which shows my data frame. I can also do a x.print schema, and then I can see what is the schema assigned to this. So in this way, we just easily created a data frame using a JSON file. Now if I come here and if I do a refresh, that will show me the application which is running, which has been started by Spark shell. I can click on this and then I can go into application detail UI to see what we have done. So I did a spark.read.json, and I can look at the DAG here, which shows what happened, what code was generated, what were the transformations which were done. It shows me how many tasks were run for this. And then I can go and look back at my second job, which is basically ending with show, where I see this in a different stage. I see the code which was generated. I see the map partitions and then the map transformation. Also, we can always look at the SQL tab, which is getting created when you use Spark SQL. And within that, we can see what kind of queries were run, how much time did they take, and you can always click on the query to see what internally it did. So it's had a scan JSON, number of output rows, number of files, what was the metadata time, and basically I'm seeing the result. So this is how I create a simple data frame from a file. And as I mentioned, you can read any file format. However, if you do not give a format or if you do not specify the right method, then it will expect the file to be in Parquet format. So we just created a simple data frame from a file. Now we can do many other operations. We can do filtering, we can do selection. So we can do this. I can just do a x dot select and I can choose one or multiple fields. So either you could use a dollar and then mention your column name here, something like this. And then I could say I would want to look at the name, I would want to look at the age. But remember, if I just do this, it will just create a data frame. So if I would want to see the result, I will be doing a dot show and that shows me what I have. I can always do some more things here. I can do a filter and I can say I would want to see the age which is more than say 20. And at any point of time when you do these transformations, it always creates a data frame or a data set. Now here I see that when I did a filter, it created a data set. So it is using the data set API. Now I can just do a show to see the result and that will show me the result in the form of rows and columns with column headings. I could do a select, I could do a filter, and I could work on my data in this way on a particular data frame. Now, you could also do some computations if you are interested in. So you could always do a x.select, and then you could be selecting a particular field. For example, I would say age, and I would say I would want to increase its value by 1 and I would like to do a show. So we are working on a data frame wherein it shows me the column name and then it shows me the values. So these are some simple data frame operations which we are doing based on a file which we have here. Now I could be picking up a bigger file and doing more functions or more transformations on that. I could be doing a filter, as I said, a select. I could be running my SQL queries by creating a temporary view out of it. Now here we could pick up a different file. I would say val my data and then I could say spark dot read, and this time I'm going to use the format method here. So I'll say format. Now I would specify I would like to work on CSV file. Then I could basically also use something called as option, and then I could be specifying I would want to infer the schema from the file. So I'll say true. I will say option, and then I could also say a delimiter if you would want to specify. Now here I have infer schema as true, and we would then want header, that is first row in the file, to be considered as the header or the column headings. Then I can just say load, and I would want to load my file. So I'm going to pick up sample files, and then I will point it to a file which I think is existing in this directory, something like this. And then I do this, which should basically create a data frame from a CSV file. You see, it shows 15 fields and the schema is understood. So I can just say my data.print schema, and this will show me the schema which was inferred, and we have our data frame created. We can always do a my data.show, and that shows me some rows and columns. Now remember, it will always show you only 20 rows. If you would want more, then you could be giving it here in the bracket, and then you could see more values. So here we have created a data frame from a CSV file. We could do a filter, we could do a select from this, we could basically do any kind of computations. I could give different conditions. So this is a bank related data where some kind of campaign was done to find out if customers would be interested in subscribing for a deposit. Now all these sample files are existing in my GitHub link, and I'll share that link towards the end of session. You can always use these files, or you can use some of your own files. Now here I could just do a my data dot select, and I could be selecting multiple columns if I'm interested in. So I could just do $. I could say I would be interested in age. I could be interested in job, marital status, or even the column which says about subscription, the last one which says why. So I could say $, and then I could say job. I would say I would want to see the subscription, and then I could be doing this, close the bracket. Now remember, that will just create a data frame. So we need to do a show to show me the results. So I'm doing a select, and I've started working on my data frame. You could be doing some other kind of calculations. Say we want to find out what are the total number of rows in this particular data frame. So I could just do a count, and then I could do show, or what I could do is I could convert this to a double value by doing this, and it shows me the total count of entries in this data frame is 45,211. Now I could basically be assigning this to a variable, say val total count, and then I get my value. So for example, we would want to find out what is the success rate of this campaign and how many people were really interested in subscribing for a deposit with bank. I could do that by just saying creating a variable called subscription count, and what I would want is I would want to work on my data frame. I would want to basically filter the values where the value for subscription holds true if it is yes, and then we could just do a count of this and convert this to double value like we did earlier for total count, and that tells me how many people were interested in subscription. So it gives me a count of people who were interested in subscribing for a deposit. Now we could do some computation on this. So we could say val success rate, and then I could just say subscription count divided by total count, and you could even multiply this by 100 to see the percentage. So it tells me the success rate of this campaign was 11% because this or these many number of people were interested in subscribing for a deposit. And in this way, you could be doing many more computations. You could be using different functions. You could be using different combination of functions. So for example, I could just do a my data dot select, and then I could say I would want the average on the balance column to find out what is the average balance of the customers which we would want to understand. Now here I could just do a show, and that could show me what is the average balance of a customer who was inquired about his or her interest in a deposit. In similar way, you could be using multiple functions like average, mean, median, percentile, and so on. Now there is one more thing about data frames. You could basically be creating a temporary view, and then people could be using their select queries to work on data. So we could do the same thing. Now here we could say my data dot create or replace temp view, and we could give it a name. So let's say bank data, and this basically facilitates querying. So now we can just use Spark SQL and then start using our queries to query structured data, which we would have basically used to create a data frame. So now I can do a select star from bank data where age is greater than might be 75, and I could just close this. And whenever I do this, remember, it creates a data frame. So if you would want to see the result, you can just do a show, and that will show you the result of your data frame. And we are seeing the fields which are having values greater than 80 or 75. So I not only created a temporary view, but now I am able to query that using Spark.SQL. Now here, this is one way in which you can work with your data frames, work on different formats, look into the schema, run your queries, do some computations, and then basically also save it as a data frame. We could do many more things. So here, for example, if I would want to write this data in a different format or save it, I can always do a spark.sql. Now the same query which we ran here, we could put this in a variable. So for example, let's say val result, and I can just do this. Now I know that creates a data frame which has been now assigned to result, and now with result I can basically look into different methods which are available. So if you would want to save it, if you would want to write it in a particular format, remember, if you do not specify a format, then it will always be read or written in Parquet. So I can always do a write dot, either I could be using a particular format, or I could straight away say save, and then I could say, for example, my new df data frame. And if I do this, the whole point is your data frame would now be saved on your machine in this particular directory in a Parquet format. So I can come in here and then I can look in if I have the directory created. So we see here, and we can look in this, what does this have? And this basically has a Parquet file which got created. Now I can always do a SSH to my second machine because this is a standalone cluster, and then I can see if there was any directory created on this machine which has the data. If no, then that's fine. If we have a data directory, we can always look for our file. So we just saved the output of our data frame in a Parquet file, and that's my Parquet file. Now there is an easier way of checking if this was fine. So this is in my new df directory. Now what I can do here is I can just say spark.read, and this time I will not specify a format. And we know when we do not do that, it expects the file to be in a Parquet format. So I'll say load my new df, that's the directory. I'll give the file name, and then basically I'll see if it reads this Parquet file, creates a data frame, and yes, it has done that. We can always do a show and we can see our new data frame. Now I know you might see some error like this, and that is because this file did not exist on both the machines. And when you're looking in a Spark standalone cluster, if you're trying to do a read operation, it basically expects the file to be existing on both the machines, or you should have been getting the file from a distributed file system. Now we can try this again, and I can just do a SCP. I can take this directory, and I know there is a SSH access which I have set up across machines. So I can say sdu at um2 in the home directory, so that this directory and file exists on both the machines. And now we will try it again. So if you see, now I'm trying to read the file. I don't get any error message. So we worked on a CSV file. We created a data frame. Then we saved the data frame using write.save. And by default, it was stored in a Parquet format. We could test that by just doing a read.load. Now, the way we did a write.save and we did not give a format, we could have chosen a format. So we could have said format, and we could have said JSON, and then do a save and basically give a directory name. Now this is also saving my data frame, but now it is saving it in a format of my choice. So I can look in new df1. I should have my data coming in here. It might take some time, and then we can come back and check here if it has saved my file in a JSON format. So in this way, you can either store the data in a default format, or basically you can store it in a particular format of your choice, such as JSON or text or some other format. So this is how we are just interacting with a file on local file system. I'm creating a data frame out of it, and then basically I'm doing some computations. Now, as I said, if you have a setup, now in this case I have a Spark standalone cluster, but if I would want, I can start up a Hadoop cluster. I can just say sbin start dfs.sh. Now that will start my Hadoop related processes based on the setup I have. And why am I doing it? Because I would want to try Spark interacting with Hive. Now Hive is using HDFS as the storage layer. So I'm starting my Hadoop cluster. I can go into my second machine, and then basically I can again start my rest of processes. So I can just say sbin, and then I can say start yarn.sh, and that will start my yarn related processes. So I have a Hadoop cluster running, which basically means now I can also work with Hive. So I can just go into Hive directory. I've already set up Hive. I can get into Hive by just doing a bin/Hive. I can look into a database if it is existing. I can look into a table which is existing, see if that contains data, and try querying it using your Spark. So I can say show databases, and that basically shows me that I have a database called testdb. Let's use that in Hive. And now I'm in the database. I can say show tables. That shows me some tables. Let's select one of the table. I can say test TBL2. Might be we can just do a limit of 10 rows and see if it works fine. So that does not have any data. Let's look into another table and let's see if that has some data. That also does not have any data, and that might be if we are not looking into the right metadata. Let's look into one more and see if that's fine. So we will say test TBL limit 10 doesn't have the data. So let's do one thing. Let's create a table. So I'll say create table new TBL. I will say ID is integer, name is string. I will say the table is created. You can always do a listing from here by looking in user, Hive, warehouse, my test database, and then I can see if that my database has the table directory. It has new table. Let's look into that new TBL. And then does that have any data? As of now, no. So I can say load data local in path. I will take this sample files. I know there is a file called kv1.txt which has internal format, and I will say overwrite into table, and then I can say new TBL. So I'm loading some data. It does not like because it does not find this directory. So let's give the right path. So we will say home hdu sample files. Now I'm loading some data. I've done that, and now I can say new TBL limit 10. So this is a simple example of loading some data in Hive table, which has two columns. We did not give any delimiters because I know the file also does not have any specific delimiters. Now here I can just exit this. Our main task was not to work with Hive, but to work with Spark SQL in interacting with Hive, which is a data warehouse package on top of Hadoop. So it is using Hadoop's distributed file system. Hive is using Hadoop's distributed file system to store the data, and we would want to use Spark SQL and especially its data frame API to work on interacting with Hive. Now let's do a spark.sql. Now if you remember, I mentioned that my Spark conf directory has already a Hive-site file, so it knows where Hive is storing the metadata, and that basically means that your Spark SQL can directly work with Hive, and you can then start using all your Hive queries within Spark, benefit from in-memory processing and the data frame API. So here I can say use testdb. So I basically would want to get into the database, and I'm using this Spark SQL. You see there is an empty data frame created. Now let's say select star from new TBL limit 10, and I could do this, and this is basically your data frame. Now you could do a show, and you have started interacting with Hive directly, which creates a data frame which allows you to look at the data, and then you can store it in a variable. You can store this file. Not only this, you could also create a table from Spark SQL. So you could basically do all your Hive related operations from here using your data frame API. So I could be saying similarly create table new TBL2, and then I could say ID would be integer, name would be string, and then I could just close this. So I'm creating a table, and I would like to close this. So let's do that. Now you see somewhere it interacts with Hive meta store. It has created a new table, and that should be stored in my Hive meta store and also on your HDFS where Hive related data is getting stored. Now we can even load data into it. So we will say spark.sql. I will use the same statement, load data local in path. I will pick up the file from sample files /kv1.txt. I will say overwrite into table new tbl2, close the bracket, and that should load data into your Hive table. Now let's try querying it. So we'll say spark.sql. I will say select star from new tbl2. I will say order by id descending, and then I can say limit 10. So I'm running a query which, if would have run in Hive, would have triggered a MapReduce job. Now here this uses a data frame, and you can always do a show which will show you the result. So we are interacting with Hive, we are creating table, we are loading data into it, we are running a query using in-memory processing using data frames, and that does not trigger a MapReduce job. If we had done the same thing using Hive, let me just show you here. So let's get into Hive. Let's start the Hive shell. Let's use our database, and then we can query our table. So I can do use test db, and if I say select star from new tbl2, order by id descending, limit 10, and just run this, now you will see that this triggers a MapReduce job because Hive uses MapReduce. Now it also mentions on the first line that Hive on MapReduce is deprecated in Hive 2, will not be available in future versions. You can use other execution engines like Spark and Thais, but we are querying the table which we had created using Spark, and now we are using Hive to do it, which obviously takes more time. It triggers a MapReduce job and does the work for you. So this is how you can use your Spark SQL and your data frames to work. Let me just exit this. And there is one more option where you can be interacting with your RDBMS. Now that is, say I have MySQL here, and I can log in into this. I can just say show databases. So I have my databases here. I can say use MySQL. I can say show tables, and then I can query one of the tables, like for example help underscore keyword, and then let's do a limit 10. So that shows me some data here. Now it would be good if we could interact with RDBMS and then get the data from here, and for that we will have to do certain things so that we can connect to this and we can work with this RDBMS. So if you look in your user local Spark, now that has a jars directory, and if I look in my jars directory, I have a lot of jar files here, but I would be interested in doing a grep and finding out if I have a MySQL related jar file. So if you see here, we have placed the MySQL jar file. Now where does this jar file come from? So this MySQL jar file, if I look in my home HDU downloads, and then if I look in here, you would see I have a MySQL connector tar file which I have downloaded. Now that particular tar contains your MySQL connector jar file, and this MySQL connector jar file has an inbuilt driver class which allows any particular service to connect with MySQL. So we need the JDBC connector jar file. Only then we can have our Spark connect with MySQL, which we already know is doing because your Spark is able to look at the Hive metastore, and Hive metastore is getting stored in MySQL. Now, how do we establish a connection from Spark SQL to this MySQL? Like we connected using Spark Hive, you can always use Spark to connect to an external RDBMS, as I mentioned, and you can always search for that. You can just say Spark SQL JDBC data frame, and then look into the data frame documentation, which will show you the syntax. But for this, remember, you will have to set up a MySQL instance, you will have to get the driver, and then you can be giving all these options such as URL, DB, query, your driver, and then other options to connect to an RDBMS. You can connect to any particular RDBMS by just basically doing this spark.read.format, connect to an RDBMS, get the data from it, create a data frame, and work on it. For many more examples, you can always look into the data frame documentation. You can always be clicking on this, and then you can see how you can connect with Hive, how you can work with data sets and data frames. You can also look into different data formats which are selected, and you can do much more with data frames. PySpark tutorial, and here we will learn about what is PySpark, what are PySpark features, PySpark with Python and Scala, PySpark Contents, PySpark Subpackages, companies using PySpark, and also we will see some demos using PySpark. So what is PySpark? Now, it is an Python's API to support Apache Spark. Now, all of you would have known about Apache Spark or would be knowing a little bit about Apache Spark as of now, that is a in-memory computing framework which basically gives you a faster processing capability, and it is widely used in terms of real-time processing or machine learning, and then there are various other use cases. So when we talk about Apache Spark, it supports different programming languages such as Python, Scala, R, and even you could be working on structured data structures using Spark SQL. Now we all know that Spark Context is the entry point to any Spark functionality. So we'll see that. Now here when we talk about PySpark, it is basically a way of using Python, or for people who are more comfortable with Python programming language, to use Python and work with Apache Spark. And that's what you have as a component from Spark called PySpark. Now here, just to show you, I have two machines. Now I have already set up a Spark standalone cluster on these two machines. So if you see here, I've given a start all command, and this has basically started my Spark master and two worker nodes. So we can check this by just doing a JPS on this machine. And if I go to my second machine and if I do a JPS to see the Java related processes, I see two workers and a master node running. So my Spark as a standalone cluster is running. Now we can always check this using the Spark UI. If I go to my browser, and then if I just do http / and then if I say um1 and 8080, so that shows me my Spark cluster, which has two worker nodes. It shows their address and all these details. Now, if we come back to the terminal and if I look in binaries, so I see a lot of Spark related programs, like you have Spark Shell. If you would be interactively working using Scala and you would want to work with Spark, you can use Spark R if this has been set up, and you can use your R programming language knowledge. You can be using Spark SQL to work with structured data. You can use PySpark, which is Python's API, allowing users to use Python to work with Spark. And obviously you also have Spark Submit. Now the other way would be that if your machine has Python installed, you could write your applications in a Python file, that is a file with an extension of .py, and then you could be using that. So here, if I would want to work with PySpark, I can just say bin PySpark, and that should start my interactive shell in Python. And then basically I can be using my Python's language. Now here, if you see, it says Spark session is available as Spark, and then by default when you start your Spark shell or basically PySpark, it would have Spark context, which is the entry point of your application available so that you could do your processing. Now there are different ways of doing it. For example, if I would just say xsc.text file. Now text file is basically a method of Spark context, and as I said, when we use an interactive way of working with Spark, such as using PySpark or Spark Shell, then we have Spark context and Spark session automatically getting initialized. If we are building our own application using an IDE, for example in case of Python using a PyCharm, or you writing your code in .py files, then in that case you would have to initialize the Spark context. Now here I could be pointing to a particular file which could be coming in from my machine. So for example, I could do this home/stu /sample files / let's take a file which I think should be existing here in this location, and this file and this directory would be existing on all your worker nodes. So if I just do this, we know that this, since we are using Spark Context, which is an entry point, it would have created an RDD. Now, RDDs are the building blocks of Spark. You might have learned about that through the previous tutorials. Now, if I just say what is X, it shows me it is a map partitions RDD, which has got created because we used a Spark context. Now, if we do further transformations on this RDD, it will further create multiple RDDs. So we'll see that, but this was a quick look at you using your PySpark. Now we have not seen the complete execution, but if I go here, if I say refresh my UI, it tells me that there is an application running. So we have started the PySpark shell, which is using all the cores of the machine. It is basically using 1 GB memory. And then we have an application which was started because we started PySpark shell. Now I'm clicking on this. I can go to application detail UI, and as of now, I have not done any execution. In terms of Spark, until and unless you invoke an action, everything would be lazily evaluated. So we don't see anything here, but we do see that PySpark shell has started an application. That application is using some resources, and basically as we do further processing, we will see the application related DAG getting built up. Now, when we talk about PySpark, as I said, it's Python's API. Now, if we look further into PySpark features, it basically, as I said, when you work with Spark, it is a in-memory cluster computing framework, which is polyglot, which basically supports different programming languages, such as you could be doing things with Scala, you could be doing things with Python, you could be working with R, or you could also be using Spark SQL. When we talk about other features, Spark also allows you to do faster processing. It allows you to do real-time analysis, and there are also features where you can be caching in your computation. That is the intermittent computation. So you could be caching in, and you could also have disk persistence. So those are the features of your Spark, and when you work with Python, you will be able to leverage all Spark's features. Now, when we talk about Spark with Python and Scala, and if we do a quick comparison, if we talk about performance, then Python is slower than Scala when used with Spark. However, when you talk about Spark, since it is written in Scala, it integrates well and it is faster than Python. Now, learning curve. Obviously, we know that both of these languages support concise code, and Python is very rich with the amount of libraries which are available, community support, and so on. But Python has simple syntax, and being a high-level language, it's easy to learn. Scala has a little bit of complex syntax since it is newer in comparison to Python, but then it also allows you to write concise code. And sometimes it might be for the new programmers, learning Scala might not be so easy in comparison to Python. When we talk about code readability, so in case of Python, readability, maintenance, and familiarity of code is better in Python API. Now, Scala is a sophisticated language. Developers have to pay a lot of attention towards the readability of code. And if we talk about data science libraries, as I already mentioned, Python provides a rich set of libraries for data visualization and model building. Now, Scala lacks in providing data science libraries and tools for data visualization. There is a lot of work happening when it comes to data science and machine learning with Spark, different components such as MLlib and ML, which allows you to work with data science kind of projects. However, Python would be more advanced in that case. Now, when we talk about PySpark Contents, so these are a quick list of PySpark Contents. So you have a Spark Conf. Now that is basically how we define our configuration. So we would be creating a configuration object using Spark's Spark Conf class. Spark Context is basically the entry point of your application, which will basically take your application to the cluster manager, whether that is Yarn or it is Spark Master in case of Spark Standalone, or even local. Now we have Spark Files. Now that allows you to read files from a file system, whether that's a local file system or a distributed file system. You have RDD. These are the building blocks of Spark. That is, anything you do starting from using a Spark context or Spark session till you invoke an action. That is, anytime you use a method of Spark Context or Spark Session, you do some transformation, you are always creating an RDT. That's a resilient distributed data set in memory, and that is in one way a logical step which is part of a DAG, that is direct acyclic graph, which gets executed when you invoke an action. Now you also have storage level and different classes within that, which allows you persistence. You can be using Spark's higher API such as data frame or datasets, and then you also have ways where you can be efficiently doing wider transformations or wider operations using broadcast and accumulators. Now, when we talk about Spark Conf provides configurations to run a Spark application. Now, we will see that further when we build our applications using PySpark. Now, if we look at the code block of Spark Conf class, which is used, so that would show you class PySpark.SparkConf, and that has load defaults. It has for JVM and J configuration, which can be passed. Now, if we look further, these are some of the most commonly used attributes of Spark Conf. So you have something called a set key and value to set a configuration property. And this is where we can be passing in our configuration properties and passing in values. We can basically say how many executors we would want for our application. We can say how much memory per executor or cores per executor, and many other properties which can be set in the form of key value. Now you can also be saying set master and then pass in a value. Now that will take your master's URL. You can set an app name, which is basically value to set an application name, and you can do a get key and default value to get a configuration value of a particular key. Now there are various other options which you can use with your PySpark.SparkConf. So if we look into Spark Context, now as I said, when we look or when we understand Spark architecture, which you would have learned from previous tutorials or some of your ways of self-learning, that's Spark basically has, or whenever you build applications to work with Spark as a processing framework, your applications would have a driver program, and driver program basically has a Spark context. Now Spark context is the main entry point in any Spark program. So if we look at the data flow, so in terms of local, we are talking about Spark context, which basically allows you to talk to local file system. And then you basically have something called as Py4j. So when you run any Spark application, a driver program starts, which has the main function, and it has your Spark context, which gets initiated. Now the driver program then runs the operations inside the executors. So what are executors? These are JVM processes. Now Spark Context uses Py4j to launch a JVM and creates a Java Spark context. By default, your PySpark has a Spark context available, which I just now showed on the machine, and that's your SC. So creating a new Spark context would not be required if you are working in an interactive way. But if you are developing your application using an IDE or basically in a file, then you would have to initialize your Spark context. Now, if we look here, so we see that Spark context has some kind of socket connection with Spark Py4j implementation, that's the JVM, and then you could be having a cluster underlying which has multiple worker nodes, wherein on those worker nodes you would have executor processes which will take care of your execution. Now if we look at this code, we see that this is an implementation of PySpark class and the parameters Spark context can take. So we can be passing in values for all these parameters such as master, app name, Spark home, Py files, and so on. So master, now this is where you will say the URL of the cluster it connects to, right? So we would be interested in using Python to work with Spark, and Spark would be either as a standalone cluster or that would be integrated with Hadoop or Apache Mesos and so on. So your master will point the URL of the cluster. App name is basically your application name. Spark home basically says where your Spark related jars or config files or what's your Spark installation directory. Py files basically tells the .zip or .py files to send to the cluster and add to the Python path. So this is where you would specify what are the Python files wherein you have written the code which needs to be added to the class path. You have a parameter environment wherein you would specify worker node environment variables such as your JVM or your memory and cores which need to be used. You have something called as batch size. So this is number of Python objects represented as a single Java object. Now it is set 1 to disable batching, 0 to automatically choose the batch size based on object sizes, or -1 to use an unlimited batch size. Then you can also be specifying serializer, and this is the serializer which will be used. So RTD serializer, now here we can be specifying, say for example, pickle serializer. So by default, we know that when we work with Spark and we work with RTDs, Spark internally uses either a Cairo serializer or Java serializer. You have something called as conf. Now this is an object of your Spark conf to set all your Spark properties, right? So this is where we are creating a configuration object. We have something called as gateway. Now we can use an existing gateway and JVM, otherwise initialize a new JVM. You have Java Spark Context Instance, that is JSC, and you have Profiler. Now this is a class of custom profiler used to do profiling. And for example, we can pass in PySpark.profiler.batch profiler. So in all these above parameters, master and app name are mainly used. Now we could basically write a particular code, and I'll show that in further slides, wherein we can just say from PySpark import Spark context, and then we can be specifying parameters which go into the Spark context. If we go further, we can see how that looks. So Spark files. Now, what is this used for? So you have Spark files, which allows you to upload your files using methods of Spark context, such as add file. And you can even get the path on a worker node using Spark files.get. So this is just a simple example which we can use. So you have these class methods. One is get. So you can get the file name, and you can even say get root directory if you would want to look at the path. So this is a simple example. Now get root directory function here, or method here, specifies the path to the root directory, which basically contains the file that is added through your add file method. So if I would be writing the code in a file and not doing it interactively, I could be doing from PySpark import Spark context, from PySpark import Spark file. So if we are doing it from the interactive way, we don't need to really use Spark context. We can just import Spark files, and that should be enough. Then here I'm saying find distance, and I'm specifying a path to a file. Then basically I am saying find distance name, and then I'm pointing to this file. Here I'm creating my Spark context, or I'm initializing my Spark context by passing in parameters such as what would be my master, and I'm saying local, what will be my app name, and I'm saying Spark file app. And then I'm using a add file method where I'm passing in this find distance, where we have created a variable to point to a file. Finally, I'm doing a print absolute path, and I can also say Spark files.get to get the root directory for this particular file. So we can be just doing this in a simple way, and I'll show you some examples here. So when we talk about your PySpark RDD, now RDD is the building block of Spark. So you have resilient distributed dataset. That is basically the basic abstraction in Spark. So anything you do in Spark until you would want to see the result, starting from using your sc dot method till you're doing transformations like map, flat map, filter, or any other transformations, all that would be creating a resilient distributed data set. And what is that? It is basically a logical data set. When data is not evaluated, you're not doing any transformation, every step in your application is ending up creating a RDD. And that RDD is basically a step in the DAG, and this DAG will get executed when you invoke an action. So it's an immutable partitioned collection of elements. Now by default, whenever an RDD is created, it will always have partitions, and we can always look at the partitions. We can see how many partitions are there, and the more number of partitions you have, the more number of parallel tasks you will have. So when we talk about RDD, there are mainly two kinds of operations. So you have transformations, So these are operations such as map, filter, join, union, and so on, which are performed on an RDD that basically results in a new RDD. Now, how is the first RDD created on which you could do a map or a filter or a join or something else? Is by using a method of Spark Context. Like I showed you an example in this session in the beginning. Action is when you would want to see the result. So these are operations such as reduce, first, count, take, and so on, which basically trigger the execution of DAG right from the beginning. So this is a simple example of creating a PySpark RDD. So here you are using class PySpark.rdd, and then you are saying JRDD. You can have your whatever name you would want to give, like context. You can be specifying your serializer which you would want to use. Okay, so if I would be doing this in a file, I would be writing in code like this. Now this is just a simple PySpark program to return the number of elements in the RDD. So you are creating a Spark context. You say sc.parallelize. Now sc.parallelize is a method to work on collection of elements. And here you have some words which are being passed. So this is just like a collection or a list, you can say. And then you are doing a counts where you take this RDD and you are just doing an action on it. Now that would give you the result, and finally you are printing it out. Let's just have a look at some examples where we can use PySpark and in an interactive way. So let me go to my console here, and what I can do is, for example, I can be referring to a file. Now, as I said, with your Spark context and Spark session both get initialized. So here we can use SC, and then with SC you have different methods which can be used to work with your Spark. Now here we can be looking at method like text file, which basically allows you to pick up a file. So let's say text file, and then I can be pointing it to a path. So I can say home HTU sample files. Now that's a directory in my machine, and this directory exists on both the worker nodes because we are working on a Spark standalone cluster. And here, for example, I can pick up people.txt. So I know that there is a file here in this path, and let's also give this in quotes. So this would have created a RDD. If I just do X, it shows me that it has created a map partitions RDD using a text file method. Now I can do some more transformations on it. So for example, I can say y x.map, and map is basically a transformation which I'm doing on an RDD which is already created using a method of Spark context. So here when I would want to do a map, I would have to pass in a function. Now in Spark, and when you're using Python, you can be using lambda functions, which is for anonymous functions. So I can say lambda, and then I can say take every element here, and what do you want to do with that? So I can say n.upper. Now that's a inbuilt function which we can be using, and when I do this one would again create an RDD, and here we see it has created a Python RDD, and this RDD again has not really done the evaluation. Now unless and until we would want to look at the result, there is no evaluation happening here. So in the first one we created an RDD using a file. In second one we applied a function using map. Now I could do a filter, I could just do a simple y.collect, and that's basically an action which you are invoking, which will let this DAG get executed, and then I look at the content of my file which has been converted into an uppercase. This is one example. Now I could also be, say, creating a list. For example, let's create a list of strings. So let's say hello, let's say world, let's say cool, let's say winter, okay, and let's say summer. So I could be giving in some words, and this usually creates a list, right? So I've created a list, and I can basically see what is this. So it has created a tuple, and that's also fine. So basically now you have created a list or a tuple, and you would want to work on it. So it's a collection of elements. Now I can basically say B, and then I can use again sc dot, and this time I would be interested in using this method, which is parallelize, which allows you to work on collection of elements. So I can just pass in A here, And if I look at B, it has basically created a parallel collection RDD using the parallelize method of Spark Context. Now we can be printing out some values from here. So for example, I could also be invoking an action. So I can say b.count, and this should give me the count of elements in this particular RDD. So these are two applications which I just ran, starting from creating a list, passing it in parallelize, and then doing a count. Or in our previous example, we read a file, we applied a map function, and then basically we did a collect. So if I would go back to my Spark UI, if I would do a refresh, now here it shows me the application which is now running. You can look at application detail UI, and that shows me the two jobs which have run, starting from the first RDD created till the action was invoked. So if you look at this one, so this one shows me the DAG, and it shows me it started with a text file, and then basically you did a map. So it also shows me how many tasks which were run. So this also means that there were two partitions created for this particular file. And I can also be looking at, say, different stages, what were there in my application, which has two jobs. You can look at storage if there was any caching done. You can look at the environment variables. You can look at how many executors were used for this particular application, and how much memory was used for storage, how much was it for processing, if there was any shuffling happening. And you can also look at a Spark SQL, although we are not using any Spark SQL component here. If I look at the second one, which shows me 4 tasks, so it started with parallelize, and then basically we created a Python RDD. We finally ended up with a count. And this tells me how many tasks we had run. So we can always go and look at the number of partitions of a particular RDD. So whenever you would be creating an RDD, so for example, we have B here, or in this case, we have Y here. So you can always do a Y dot and search for different methods which are available, and then you can basically be checking. So for example, if I would want to look at the number of partitions what was created for these Y when I was converting my text into uppercase, and then I can be just doing this, and this will tell me how many partitions were created. Similarly, if you would search for B, which was when we worked on a list, and if you would want to see, so it shows me the number of partitions were 4. And that also tells me that based on the number of partitions, you are seeing the number of tasks which were executed. So automatically, based on your data size or based on the number of cores which are being used, it has created partitions, and per partition you would have a task running, right? So for example, we had this where we were creating a list, and then in B is what I was doing was I was doing sc.parallelize. Now what if I had done something like this? So if I would have done something like this, then my B would have created 2 partitions, right? And then if I do a execution on B, like what we did for count, so it still gives me the count, but now the partitions were 2. So we can again see how many tasks were run. So if I go back here, and if I go to the jobs, and then I see one more job which was run, and you see it shows me 2 tasks. So the same job which was showing 4 tasks earlier is showing now 2 tasks, and that basically means that the number of partitions was changed, and per partition you will have a task running. So this is just a simple example of seeing how you can be basically using PySpark. Now I could also be taking this whole thing and putting it in a file and then executing it, and I'll show that later. So when you talk about storage level, now that's a very important concept. And if you have followed previous tutorials where we would have spoken about storage level, so basically this decides whether the RDD should be stored in memory or should it be stored on disk or both. So when we talk about your storage level, now if we look into the package which comes for Spark, it basically has storage level, and you can always go to Google and check more for this one. So for example, I could basically be checking this. So for example, if I would say storage level and just check this, so storage level, and then you can do a Spark, and you see it says you have different options, memory and disk. You have memory only serialized, memory and disk serialized, disk only, memory only. So there are different options here, and this one you can also search what package it comes in for, and then you can see there should be a package which talks about storage level, and that would be, for example, let's see. So here it says org Apache Spark .storage level. Now this is a way wherein you would be importing a package in terms of Scala when you're doing, but then storage level as a class comes within your org Apache Spark storage level. And similarly, you would have your storage level for PySpark also, wherein you have to import the particular package, and this storage level then has different options like memory only, disk only, memory and disk serialized, and so on. So here what we can do is we can basically see what is the usage of storage level. So in this example, if you see, we are saying class PySpark.storage level. Now we could be saying it should use disk, or it should use memory, it should use off heap, or should it be deserialized, what should be the replication. So storage level is one way wherein you can have your RDD which gets created at any step of your application to be cached. So that's basically making your computation cached or computation persisted, so that if down your application, if you are using the same step again on same series of steps, you will not have to have your complete DAG executed right from the beginning, but you could benefit from the cached or persisted computed RDD. Now here we are saying from PySpark import Spark Context, we are saying import PySpark, and here we are creating a Spark context, that is Spark context local storage level. Then I say I would want to do a sc.parallelize on these elements, and then I can basically say that this RDD which gets created in this step needs to be persisted using PySpark in storage level, and then you can say memory and disk with a replication of 2. Now I could then just be checking if my RDD was persisted, and I can check for the get storage level. I could even print it. So this basically tells me that if I was doing something on RDD1 for the first time, it would have cached my computation or whatever we did in this step in one of these options which comes as a part of storage level. And if next time I would be executing that series of step, it would benefit from getting the data from cache. Now here we have a quick example of using storage level and then caching your RDD, and we can then also see how we can recognize if that is coming from your UI. The information can be seen in UI, and you can see if the caching is really benefiting. So for example, like what we did earlier, we can basically create a list, and then I am doing a b sc.parallelize. And here, before we can use this PySpark, we will have to import the package. So for example, I could be just doing this. Now I could import this PySpark package here, which we will be using to use the storage level class. Now what we were doing earlier is we were just doing a b.sc.parallelize. Now that creates an RDD, and we can do that. And here I am doing a persist, where I'm saying that sc.parallelize, which creates an RDD, that RDD or that stage of computation should be persisted using PySpark storage level, and I'm specifying memory only. And as I said, you can have different options here like memory only, memory and disk only, memory and disk replicated. So you can give different options here with storage level. Now we could be straight away doing this, where we will be caching in this in memory. Now once I've done this, I can basically just do a b.count, and when I do this, now this b.count would have triggered the execution of DAG right from B onwards. So basically this list would have been created. That's not part of your DAG. Here I'm basically using sc.parallelize. So this is where my first RDD is created. You're persisting it, and then you're doing a count. Now if I go back to my UI right now, if I do a refresh, it basically shows me an application which completed with 2 tasks. If we see here, we see that there was a parallel collection cached, now which we have done that, and it shows the duration is 2 seconds. If I look at my storage, it shows me that the parallel collection was 100% cached, and the size in memory is 175 bytes. and then it says how many partitions were cached, and we can look at the executors to just tell me we had one for driver, and then you had two executors for two tasks. Each one of them were running on two different nodes. They were using by default two cores. How much memory was used for storage, how much was used for execution. It tells how many tasks were run by each executor, and that gives me an overall summary. Now, if we basically run this again, now what will this benefit from? We will not again start with sc.parallelize because that RDD is already persisted in memory. So I could just be doing a b.count where it will get the persisted RDD from memory and give me a count. So if we do this and we go back here in my jobs, it shows me the second job. Look at the time difference. So this is 2 seconds and this is 0.2 seconds. And if we look at this one, it basically says the input is 175 bytes. Now that's what we know, that RDD was cached in memory and we are benefiting from caching. So this is a simple example of using storage level where I could have written the whole code in basically a file and done it. Now, as it says, you can also do a get storage level. So you know which RDD you have persisted. And basically you can, if you would want to check that. So we have b.get, and then I can do a tab which shows me different options. So we will use storage level to basically see what was the storage level, and it basically, based on different storage levels, it gives me, when we used memory only, it shows the value as true. So you can also be looking at the storage level here. You can be printing out the storage level if you would be interested in doing that. So the same thing, what I have b.get storage level, I could just wrap it using a print to see what it shows here. And that shows me memory serialized with 1x replicated. That means it was not replicated. So I could be using storage, and then I could be using memory and disk too. So that's one more option which you can do. And then you can see how is it cached, where is it cached, where is it persisted, right? So that's an example of your storage level. Now, when we talk about PySpark, it also has something called as data frames, and we'll look at that. So when you're working with Spark, Spark's basic or core API was RDD, and then there were higher level APIs, that is data frames and data sets, which were introduced as experimental features in Spark 1.6, but then they became the main APIs which are extensively used these days when you're working with structured data, and they were introduced from Spark 2 onwards. Now, PySpark, or basically using Python, you can also be working with data frames, and data frames is basically a structured way of looking at data. Or you could say, if your data is already structured, it would be good to inform about the structure and format to the backend DAX scheduler, and then it would be more efficient in accessing the data. Now, when you talk about data frames in PySpark, data frame is basically a distributed collection of rows with named columns. Now that's what you would have seen if you have worked with Python's pandas library, or you can be using or creating data frames using Scala as a programming language. So data frames is basically a table of data with rows and columns. Now, when you talk about RDDs, we know that they are immutable in nature by default. If you are working on a collection of elements, you could basically have mutable or immutable structures created. But when you talk about RDDs, these are immutable in nature. You have basically lazy evaluation. So RDDs are lazily evaluated and they are distributed across memory. So when you talk about creating data frames in Spark, you can be creating using different data formats. You can be loading data from existing RDD. You can also be programmatically specifying schema. So there are different ways in which you can work with data frames. So let me quickly show you an example here. Now, when we go to our machine and let's get to PySpark. So here I'll just say bin/PySpark. That brings my Python prompt to basically allow you to work with Spark. Now, as I said, your Spark context gets initialized automatically, and when you use a method of Spark Context, you are moreover working with RDDs. And if you would be interested in working with structured data, then you would be using Spark Session. So for example, what we can do is we can say x equals, and then I can just say Spark dot, and then I can check what are the methods available here. So you do have a method which is called create data frame. Now we would be interested in reading a file which might be say JSON or a CSV file, and then creating a data frame out of it. So we can do that using read, and then I can again say what are the methods which are available with read. So you have an option like format which can be used, or you can straight away be using CSV or JSON or text or ORC. So I can say format, and for now I will select a JSON file. And what I would also do is I would want to infer the schema, so I can basically use option, and with option I can say, for example, infer schema, and then I can say true. What I can also do is I can specify one more option, and I can say header. If there is a header, then I can set it to true. If there is no header, then basically it will just look at your data. And then we can do a load where we would want to point to a file. So I'll say home/hdu/sample files. And here I have a file people.json, which does not have huge data. We can take a look at bigger data set also. And here when I do this, this would have created or should create a data frame. So data frame where it infers the schema, where it understands the first row as the header, and it creates a data frame. And whenever you would want to look at a data frame, I could just do a x.show that shows me it is a data frame which has got created. Now since we are in Python, we could do a type, and that shows me it was a data frame created. You can straight away start doing a select, and here I could say, for example, show me the age. Now at this point of time, if I do not do a show, then it just shows me that it is a data frame and it has one field, and that's of the type bigint. So I could again do a show, and that shows me the result of data frame. So you can be then doing multiple other operations. You can do a filter, you can basically do a group by, you can do a count. So you can do all that, and if you have any doubt, just do a tab and it will show you what are the options. For example, I'll say let me get age which is greater than 19, and here you are working on basically a string. So you can do these things, but then you will have to follow different syntax. But if you see x dot, and then I can search what are the different options which are available, so only the syntax has to be corrected. But then I have something called as x dot filter, and then basically I can be specifying what I would be interested in and then filter out the values. Okay, now this is basically a data frame. So similarly, I can be also looking at a bigger file. For example, let's say I have a file called bank_full1.csv, if I'm right. And then we can basically point this to format as being CSV. Let's quickly check if we have this file. So let me open up a new terminal. I look into the sample files, and I have a bank_full.csv. So that's the file I'm interested in, and that's a CSV file, unless like last time we saw a JSON file. And here we gave the path which is wrong, and that's why it was giving me an error. So let's go back here and change this to the right path, and then basically it should create a data frame out of this. If I do a x.show, that should show me the data frame, and by default when you look at your data frame, it shows me only the top 20 rows. And then you can start doing a select on this, you can filter the data, you can do a group by, you can do operations, you can do functions on it, and you can do various ways in working with a data frame. So this is just a simple example of using PySpark to create a data frame, and then you can start doing your other operations on it. Now, when it comes to your broadcast and accumulator, so broadcast variable allows the programmers to keep a read-only variable cached on each machine rather than shipping a copy of it with tasks. Now, why do we need this? So for example, you are doing a bigger operation such as join or union on two RDDs or two data sets or two data frames. Now, in that case, we know that whenever we basically have a data frame created or an RDD created, it would have partitions. So for example, we had this here, and I can do a X dot and check what are the different ways in which I can be looking at this. So as I said, by default, each RDD or data frame which gets created, that would have your partitions. Now you could convert your X into say an RDD if you would want to do it, right? And then basically I could have done this by saying Y equals, right? And then you can check at your Y what are the different options, like you have get num partitions, right? So I could just do it this one, and I could see how many partitions are created. So that was a big file, and it shows me there is only one partition created, right? So based on the partition, you would have the number of tasks. Now, if you have multiple data frames or data sets on which you would want to do a join operation, then the point here is that if both are large, and if you would be doing a join based on a particular column, now in that case, there would be a lot of shuffling involved. So basically, if you have your data in the form of a pair RDD, or if you have your data frames where you would want to do join on a particular column, it would have to shuffle the data for both the data sets or data frames or RDDs so that it can be doing your operation. Now in that case, we can always use a broadcast variable, and in that what happens is that the smaller data set or data frame can be converted as a broadcast variable, and then this variable is shipped to the memory of each machine, which can then be used to directly do your join or other operations with the variable or with the smaller set of data in memory with the larger data set on that particular node. Now that's where broadcast variables are useful. So for example, you can be saying dot broadcast. So like what we were doing earlier, you can create a Spark context. You can say broadcast, and I would want to broadcast this particular list as a variable. Now you can always be looking at the value of it. Okay, now once this broadcast variable is created, we can then be using this. So for example, B is my broadcast variable, and A could be a huge list of elements, and if I would want to do a join or some other operation between them, then this B would be shipped to the memory of every node. Now what would have happened is on every worker node, the memory would have a partition of your larger data set. So this small variable or this broadcast variable having less number of values could be used to do a join operation with each partition on each node. Now that's the benefit of broadcast. Now when you talk about accumulators, these are variables that are only added through an associative and commutative operation. So for example, if I would want to use accumulator, so here I would say sc.accumulator. Now I'm defining a function here, so I'm specifying global num, and then I would want to increment the value of num based on x. Now here you create an RDD, so you say sc.parallelize on a particular number, and for each element here you would want to apply this particular function. So basically this function which takes x as a value and it keeps adding all the values, we are applying this function to every element in the list. So once we start iterating through the list, 20 would get added to 30, then the total would get added to 40, and so on. Or you could say other way, that you will start with 20 and then 30 plus 20, and then 40 is added to the sum, 50 is added to the sum, and finally look at the value. So when you're talking about accumulators here, so we can basically be looking at the accumulator value here, which would show me 150. So you can try this out like what I've shown other examples, either this one or the broadcast, and basically you will get a better idea of how broadcast variables and how your accumulators work. So moving forward, now that we have looked at broadcast and accumulators, let's also look at some sub packages in PySpark. Now, as I said, whether you work with Python or Scala or R or Spark SQL, you have Spark has different components which allows you to handle different kind of workloads, handle different kind of work packages, and work on different kind of data sets. So when you work with PySpark, it has a component for SQL. So you can also be using PySpark.sql module, and that basically allows you to work with structured data like what we were seeing an example of data frames. You could be using PySpark.streaming module, and that is if you are interested in working on streaming kind of data, wherein you could be doing stream processing. If you would be interested in building machine learning algorithms, then you can use PySpark's.ml package and also the MLlib package. So these are two different packages, one mainly for data frames and one with other machine learning algorithms. So there are a lot of sub packages in PySpark which you can use, and you can be appropriately using the modules. Now there are different companies which are using PySpark, and I would say all the companies which are using Spark would be having their applications either in Scala or written in Python, where they would be benefiting from PySpark or Spark Shell and thus working on structured data. So you have MLlib, now that's basically where Spark started. You have Mindtree, you have Walmart, Repro, Tech Systems, Tridence, Capgemini, Alibaba, and many more. So there are different other companies which are using PySpark. Now to look at the demo, we can be looking at a particular data set, and then we can see how we can use PySpark to analyze that particular data. Now for our demo, we will look at this Walmart stock related data what we have, and this is basically saved in a CSV format. So as I showed earlier, we can be using the CSV format, we can create a data frame out of it, and then we can basically ask some questions to it. So for example, if I would be interested in working on this one, so here if you see, I have imported find Spark and I have initialized it, and then from PySpark I'm using the SQL module where I import Spark session, and then I can be doing a Spark session builder, app name, Walmart. I can just say get or create. Now you would not be doing all these things if you were working in an interactive way like I was showing in our Spark setup. So you could straight away start from here where you are reading a file into a data frame. So you could be loading the data now if that data is existing. So here in this step, you are basically doing a read.csv. You are pointing it to a file wherever your data is stored, and then you say infer schema and you say header true so that it knows the first row is basically your heading. Now once you're done with this, now in certain cases if you're using a notebook to do it, or if you would want to do it from your command line, right? Now in that case, you will have to make sure that if you're doing it from the command line, you will have to get these packages. So for example, what I can do is I can be going into, say in my case, I have Anaconda installed, and that's where I'm showing you this notebook. So what you can be doing is go into your Anaconda prompt if Anaconda is installed, or if you have your Python, then you can just be doing a pip install find Spark. You can be doing a pip install PySpark, and it should get your modules. And then it also installs Py4j, which I was explaining earlier. It will basically set up all these packages. So Py4j and PySpark shows you the version, and then you should be all set. So if you're using Anaconda, which has basically all these different ways of working with your Python, so you have Jupyter, you have basically Spider, you have Visual Studio Code. So if you would want to use Anaconda, then just install Anaconda Navigator where you can use Notebook. Then you can also get to your Anaconda prompt and install the packages, and then you can start your Jupyter Notebook. So here you could be doing this. Other way is you could be doing it from your command line, provided you have installed these packages. The third way is you can be doing it from your Spark standalone cluster, and in that case you don't have to do all this stuff. You can straight away start reading the CSV and then start working on it. So here we are reading a Walmart file. Now this is what we have open. What was the open price? What was the high, low, and closing price, right? Shows me the date and it shows me the volume. So if you want to do some analysis on it, so you can create a data frame out of it. Then you can be looking at the columns, what are part of those data frames. You could be just looking at the first row of the data frame using head, and you can see the values. You You can check the schema using a print schema. You can be printing in first 5 rows. So for line in the data frame dot head, and you are saying I would want to look at first 5 rows and I would want to print it in line by line. Now I can be getting some general statistics out, so I can just be using a data frames.describe. Now that's the method which gives you just a summary, right? So when you are looking at these values, so it gives you count and mean, standard deviation, minimum, max. So that's like your finum summary or your describe summary. You could also be formatting columns to just show 2 decimal places. So here I'm using from PySpark.sql functions within the SQL package. I'm importing format number, and what I'm doing is I'm doing a describe to look at the stats, and then for the same stats I would be doing a select where I would be interested in looking at this summary, and what I would want is all of these columns which we were seeing here, open, high, low, close, volume, all of these I would want to just look at values with 2 decimal points. So I'm just specifying from my data frame what is the column name, how do you want to cast it as, and basically giving the limit, and then I'm saying what would be this called. So you could change the name if you would wish to, and here we have reduced the information what we were seeing here just to 2 decimal points. So this is a simple example where you're doing some formatting. Now you can create a new data frame with a column called HV ratio, that is ratio of high price versus volume of stock. And how do you do that? You use the with column method. So with column method. Now here we are doing this. Now with column, I could also be passing a function if I have created my user defined function. So here I am saying df, that's my data frame. I say with column. What would be my column called? So that's your HV ratio. Now how do you get that? So out of your data frame, you take the high column, divide that with the volume, right? And then you would basically do a select on this HV ratio. So what we are doing is we are not only in this part creating a new column into the data frame. So this data frame df underscore HV, the new one, will have this particular column. And what we are doing is with this with column, it would have added HV ratio as a column in your data frame. And then I'm just doing a select on that. So here it shows me the HV ratio and the values. So if you would want to answer some more questions like which day has the peak high in price, you can do a order by. So here you're again working on your data frame. You say df, you would be interested in looking at the high column. You would want to sort it in a descending way, and then whatever is the result, you would want to basically select the date and head value for your first index position. So you could also be doing a mean of the close column. So here we are using import mean, and then we are applying the mean function on the close value. What is the maximum and minimum value of volume column? So you could be doing this by just doing import minimum and max and apply this on your volume column. How many days did the stock close lower than $60? And you can be looking at 60, and you can be doing a filter. So what percentage of time was high greater than $80? Again, you're doing some computation on the high column where you're looking for the value which is greater than 80, which is given in this brackets, and you're doing a filter. What is the Pearson correlation between high and volume? So you can just use the correlation method here on high and volume column, and you can get the value. You can import correlation, and you could also be doing it in this way where you could do a df.select, use the correlation method, or you can say function on high and volume, and then basically show the results. If you would want to find out what is the max high per year, now in this case you would be importing some other packages like day of month, hour, day of year. You have month, year, week of year, and so on. And then you are using with column where you are creating year, and you are extracting the year aspect from the date, and that would become your year column. And then what you're doing is using this year column, you're doing a group by and finding out the max high value per year. So what is the average close for each calendar month? And basically you create a month column using with column by extracting the month out of this date, and then you do a group by month and do a mean, or order by month, and then you can do an average close. So these are different ways in which you can answer questions on a particular data set using PySpark. And then Obviously, once you have run this, you can always go to the Spark UI and basically look at this. So this code will be available for you, and here you can always look at this, which basically gives me an idea of working with your data frame using PySpark and different modules and functions and different packages which we are using to extract useful information from a particular data set.
We've almost reached the end of this tutorial. Now, Ajay will help you learn some of the important Spark questions that you might tackle in any big data and Spark interview.
Let's have a quick look at some Spark interview questions, which will just prepare you with different aspects of Spark and its components and can help you when you're facing an interview. Now, here we have some generic Spark questions, such as how is Apache Spark different from MapReduce? Now, this is one of the common questions which you might be asked about. You would have to answer about differences between Apache Spark and MapReduce, right? Now, MapReduce is a programming model and Apache Spark is a processing framework. So when we talk about Spark, you can basically say that Spark processes data in batch, but then it is also good for real-time processing. In fact, it is one of the features of Spark that it is good with real-time or faster processing. Spark runs nearly 100 times faster than Hadoop MapReduce. Well, that actually depends on how your Spark application has been written and in comparison to how your MapReduce application has been written. But then if you would say Spark application, whether that is written in Scala, Python, your R, in any way, if it has been well written, then Spark can give you a performance benefit. It would be 100 times faster than your traditional MapReduce. Now, Spark, as I mentioned earlier, does not have its own storage. So for processing, it would be picking up the data from, say, an RDBMS or from Hadoop distributed file system or from a data warehouse package such as Hive. But then Spark is known to do a in-memory processing. Now it stores data in RAM in the form of RDDs, and that is why it gives you a faster performance. Now when you talk about MapReduce is slower due to the reason that it has two phases, mapping and reducing, wherein the intermittent result, that is the result of your map phase, is basically written to SDFS and then it is picked up from SDFS for your further reducing. So MapReduce also processes the data stored in SDFS, but as I mentioned, while processing also, the staging data or the data which is result of map phase and has to be picked up by reduce phase is also stored in SDFS. Spark also has features such as caching and in-memory data storage. So you can have your computations, that is the result of RDDs, getting stored in cache. Now that could be different ways. So you can use a storage level and then you can specify whether the caching is going to be in memory, is it going to be in disk, or is it going to be a combination of memory and disk, but those possibilities are there in Spark. Now MapReduce does not have this. Well, you have a feature of distributed cache, but that's not as efficient as Spark. So Hadoop is highly disk dependent. Now, if somebody asks you what are the important components of Spark ecosystem, so Spark basically has language support for different programming languages such as Java, Python, Scala, and even R programming language. And Spark has different components for different use cases and different kind of data. So it has a core API, that is your Spark core engine. You have Spark SQL to process your structured data. You have Spark Streaming, which helps you in processing streaming data. MLlib to create your machine learning algorithms by using different statistical methods and algorithms which are available. And GraphX, which is for your graph-based processing. Now, when you talk about Spark, it can be set up as a standalone cluster, that is having one master and multiple worker nodes. It can be integrated with Apache Mesos. And then you also have Yarn, with which your Spark cluster can be integrated. So if you are describing about important components of Spark ecosystem, then you will mainly speak about the mid layer, that is the core components. You could also speak about your language support and the cluster management solutions, which can be used when you're working with Spark. Explain how Spark runs applications with the help of its architecture. Now, when we talk about Spark application, it runs basically as independent processes, or basically you have application which would be split into tasks, and these tasks would be running across your different machines. Now, you could have basically Spark session or your Spark context, which are these important classes, or you can say the entry point of your Spark applications. Every Spark application would have a driver. And what does that driver have? It basically knows the flow of your application. At the back end, you also have a DAG scheduler. So for all the steps what you're doing in your application, DAG scheduler is aware of what are the different steps which make your DAG, that is direct acyclic graph, for your in-memory processing. Now your Spark session or your Spark context, which is your entry point of your application, interacts with the cluster manager. Now in this case, we can be specifically speaking about Yarn, which has resource manager as the master of the cluster and node manager as the slaves of the cluster. So your Spark session or Spark context speaks to resource manager, that is the cluster manager, which basically would request resources from the worker nodes where the execution would happen. Now, worker nodes would have a processing slave, that is node manager, which grants the approval of usage of resources to resource manager. Now, this request which we are talking about, that is requesting resources, is called container. So resource manager requests containers from one or multiple worker nodes. Worker nodes or the node manager process running on them grants these containers, and it is within these containers a executor process is launched, which is responsible to take care of the application related tasks. So when you talk about iterative algorithms, they apply operations repeatedly to the data, and they can benefit from caching data sets across iterations. So you can also have the RDDs which are created or the computations which are done. They could be cached, and this cache can be beneficial for your further run of the similar tasks or similar computation. Now, what is a task here? It is basically the unit of work to the data which is coming from the respective disk to basically transform or work on it. So when you talk about execution, which is taken care by executors, which could be either one or multiple on a particular node, now which depends basically on the data on the node, which depends on the resources available on the node. You could have multiple executors. The result is then sent back to the driver, and that's how your application execution happens in case of Spark. One of the common questions which is asked is, what are the different cluster managers available in Apache Spark, or how does Spark work with different setups? So by default, you can have Spark in a standalone mode. That basically means Spark would be running with one master and multiple worker nodes, with one master and multiple worker processes. Across machines, you would not have any Hadoop setup or Mesos or anything else. So by default here, applications would be submitted to the standalone mode, and they would run in a FIFO order, that is first in, first out, and each application would try to use the resources on available worker nodes. Spark can also be integrated with Apache Mesos, and that's an open source project to manage computer clusters and can also run Hadoop applications. In fact, Spark initially came into existence to prove the credibility of Apache Spark, and then later became a independent project. You have Spark integration with Hadoop Yarn, so that is where Yarn is taking care of resource allocation in a Hadoop cluster, and Spark leverages the benefit of using Yarn. You could also have Spark working in a Kubernetes environment. Now, Kubernetes is an open source system for automating deployment, running your microservices, scaling and management of containerized applications. So Spark can even work in a Kubernetes setup. One of the important things of Spark, which really makes it powerful, is lazy evaluation. So what is lazy evaluation in Spark? When Spark operates on any data set, that is the data which you are interested in processing, it would take care of the processing based on various steps within your application. Each step basically creates a RDD, a resilient distributed data set. So for example, if I would want to read a file, I could use a method of Spark context called text file, and this would create an RDD. Then you could do a map or a flat map or a filter, and all these steps, what you code in your application, are lazily evaluated. That is, they are not evaluated as soon as the step is created. They are evaluated, they are executed only when action is invoked. So whenever you do a transformation such as map or filter or flat map, or you just use a method of Spark context, in this case, it will only and only create an RDD, a resilient distributed data set which exists in the memory. But this RDD does not have any data loaded, does not have any transformation done. So transformations in Spark are evaluated only when one would invoke an action. So till then, it is called as lazy evaluation. That is, it does not evaluate the file which you are processing or any map or filter or any other transformation. So the question is, what makes Spark good at low latency workloads like graph processing and machine learning? So how does Spark achieve that? So as we discussed earlier, your Apache Spark is good in storing data in memory for faster processing and model building. So any component of Spark you use, such as Spark SQL, Spark Core, Spark MLlib, Spark Streaming, or Graphics, in any of these cases, it is in-memory processing. That means the data is loaded into the memory of the respective worker nodes, and then the processing happens. Plus, the data which is loaded in memory, which is undergoing some transformations and results in some kind of intermittent data, that data can be stored or cached in memory for further processing. When you talk about machine learning algorithms require sometimes multiple iterations to create a optimal model. Even your graph algorithms traverse all the nodes and edges. So basically, these low latency work nodes that need multiple iterations can lead to an increased performance because you are doing the processing in smaller iterations by loading data in the memory. So there is also a concept of automatic cleanups. So the question is, how can you trigger automatic cleanups in Spark to handle accumulated metadata? And there is a parameter, or you can say property, which needs to be set. To trigger the cleanups, you need to set parameter spark.cleaner.ttlx, time to live, and that's where your job, which is running, which is divided into batches and writes the data to the disk, you could trigger a cleanup based on this parameter. Now, how do you connect Spark to Apache Mesos? So suppose you have Apache Mesos set up, but then you would also want to do in-memory processing using Spark. How do you do it? So first thing what we will have to do here is configure the Spark driver program to basically connect to Apache Mesos. That is, you have to give your connection details to connect to Apache Mesos. Then you will have to put your Spark binary package, that is Spark installation package or binary package, in a location accessible by Mesos. So Mesos knows that where Spark is existing. Spark can install in the same location as that of Apache Mesos. And then you can also configure some properties which says what is the Spark Mesos executor home, pointing to location where Spark is installed. So basically your Apache Mesos has to be informed about Spark, and Spark can be existing with Apache Mesos or within Apache Mesos so that it can use Apache Mesos. Now, one more question which you can expect in interview or if somebody is testing your knowledge is about different data formats. Now, other than your regular formats such as JSON, XML, text, CSV, there are other intelligent formats such as binary files or sequence file formats. You have Avro, you have Parquet, and so on. So Parquet is basically a columnar format which is supported by several data processing systems. So if you have, say for example, you have data which is in CSV which has multiple fields or multiple columns, and you do not access all the fields or all the columns all the time, it would be advisable to go for a Parquet format wherein Spark can perform read and write operations by default. That is, whenever Spark tries to read a data set, it will assume that data is in a Parquet format. And if your data is in a different format, then you have to specify that. So advantages of having a columnar storage is you can fetch specific columns for access. It consumes less space, obviously, brings down your disk usage by 62% approximately. It follows type specific encoding and controls your IO operations. So if you would be interested in reading about different formats, I can share a good link with you which talks about formats, and here you can find, let's look at formats. This is the good link which basically shows you details about different data formats such as compression schemes. You have metadata management, you have different common file formats, you have binary files or sequence file formats which can be compressed at a block level or record level and support splittability. You also have other formats such as Avro and Parquet, and this is a very good document you can refer to. Now, coming back, let's look at the next question. So what is shuffling in Spark and when does this happen? Now, shuffling, as we know, would basically mean similar kind of data being brought together. So shuffling is the process of redistributing your data across partitions. Now, what we know is whenever we do a transformation, whenever we use a method of Spark, what does it do? It creates an RDT. Now, unless and until you have specified how many logical partitions of that RDT you want, it will by default create number of partitions based on either the data set size or based on the number of cores which are available in your cluster, or it could be that you are basically creating partitions by default, that is 2. So say for example you have a data which you would want to process and that data is converted into a key value pair. So take an example, you have a sentence, welcome to my world. Now if I want to split this in a key value combination where I would say my first word will become the key and the complete line becomes the value. So my key would be welcome and the value would be welcome to my world. Now, if you have similar data like this, which is key value pairs, and that is because of some transformation you did on a data set, all this data would be in a RDD during the time of evaluation. And this RDD would have partitions. So you would have some key value pairs in partition 1, some key value pairs in partition 2. Now, suppose you would want to do something like a join, or suppose you want to do a group by or a sort by based on key. Now, how would that happen? That would be possible when the similar keys are brought into the same partition. So that will trigger shuffling so that your key value pairs, which are stored in RDD, in partitions, you will have your similar keys shuffled and brought to the same partition, where then you can do some key based operations. Now that's where your shuffling in Spark happens. There is also an operation called coalesce, and why is that used in Spark? So Spark uses coalesce method to reduce the number of partitions in a data frame. Now what we know is whenever you're working on structured data, and this structured data, basically whenever you do a transformation on it, it creates a schema RDD, or what we call as data frame. So what is data frame? Like a table which has rows and columns with headings. So coalesce is basically used to reduce the number of partitions in a data frame. So for example, you have 4 partitions which have some values, and what you would want to do is you would want to filter the data in such a way that you will remove the multiples of 10. So here you see we can be using coalesce for this, which will remove all the values which are multiples of 10. So data is read from a CSV into an RDD. The RDD has some empty partitions. It makes sense to reduce the number of partitions. Why not? And using coalesce, you can bring your data together in less number of partitions and get rid of the partitions which really do not have any data. Now the question is, how can you calculate the executor memory, or calculate the memory which will be required by the executors which will take care of your tasks?
Okay, so let's continue learning on some Spark interview questions. Now here's our next question. So how can you calculate the executor memory, right? Now when you talk about executor, it is the JVM process which will take care of your Spark application related tasks that would be executed. So let's say this is your cluster. So you have 10 nodes, each node has 16 cores. That is, you can then take away 1 for your operating system itself. Each node has RAM, which is 61 gigabyte of RAM. And when you talk about your cores is the number of concurrent tasks an executor can run in parallel. So the general rule of thumb for optimal value is 5. Now it depends. Now when you talk about number of executor identification, how do you do that? So number of executors is equal to number of cores that the machine has divided by the concurrent tasks. So if we say we have 15 cores and we have 5 concurrent tasks, so we get number of executors is 3. And depending on the number of nodes you have, you can multiply that with the number of executor in each node which would run for your data processing, and that will give you number of executors for your Spark job. So in our case, we have 10 nodes. We are talking about the number of executor in each node, which we just calculated as 3, and then that gives me the total number of executors, right? Now this is how you can basically calculate the executor related memory. Now let's look at some Spark core questions. So what are the various functionalities supported by Spark core? So what is Spark core? Spark core is the engine for parallel and distributed processing of large data sets. So you could be scheduling and monitoring your jobs. You could be doing memory management, fault recovery, and task dispatching. So these are various functionalities which are supported by your Spark core. Now, what is the significance of RDDs? That is your resilient distributed data sets in Spark. Now, RDDs are the building blocks in Spark. So Spark core is embedded with RDDs, which is basically the fundamental data structure of Apache Spark. What are RDDs? These are immutable, fault-tolerant, distributed collection of objects that can be operated in parallel. And when are these RDDs getting created? Whenever you do some transformation. So either you would be using a method of Spark context, or say the initial entry point for your application, that's your Spark context. So methods could be something like text file, whole text file, parallelize, and so on. Or you could be doing some series of transformations. So per transformation you do on your RDD, it creates a further RDD. So you could be doing a map, flat map, filter, and many more. So RDDs by default, whenever they are created, they are split into what we call as logical partitions. Now, when we are creating an RDD, we could also mention how many partitions we want. So RDDs are split into partitions and they can be executed on different nodes of a cluster. How do you convert a Spark RDD into a data frame? Now, we know that Spark core comes with the RDD concept, that Spark RDD is the basic API, and then you have other APIs in Spark such as data frame and data sets. So if you would want to convert a RDD into data frame, you could be using a helper function called toDF. So here we are importing a package and then we would want to create a data frame. So we use the Spark context. We load from map RDB. So we basically are getting the data from a table. We are also giving some conditions like where field is something, you're doing a select, and finally you're doing a toData frame, which will convert your RDD into a data frame. Now, you could also be doing that using Spark sessions method, create data frame. So as we know that when you work with Spark RDD, you use Spark context. And when you would want to work with Spark SQL, you would be using the internal class that is Spark session, and that has different methods. So you could be creating a data frame using create data frame. So you can convert an RDD of row to a data frame by calling create data frame on a Spark session object. Looking further, so if somebody asks you, explain two types of operations supported by RDDs. Now, as I said earlier, RDDs are created either when you use a Spark context and a method of Spark context like text file, parallelize, whole text files, or when you do some transformations. So there are two kinds of operations which are mainly supported by RDDs. One is your transformations and second is your action. So any or every transformation you do, it will only result in an RDD, which basically means a logical step, but there will be no execution happening. So your transformations are operations that are performed on an RDD to create a new RDD. How is this RDD initially coming into existence? So if I would have said val x equals sc.text file and then I pass a file into that, that would create an RDD. Or if I do a sc.parallelize, or if I do sc.whole text files or a sequence file, so that would have created my initial RDD, and then I could be doing any transformations on that. You could also be doing the second kind of operation which actually leads to the execution of your Spark DAG, and that's your actions. So whenever you launch an action, you would have your Spark application application's execution happening. So when you talk about actions, it could be take, it could be collect, it could be reduce, it could be first, count, and so on. So these are your two kinds of operations which are supported by RDDs. Now, how do you programmatically specify schema for a data frame? So we know that we can be reading, say, CSV or text or JSON or Avro or Parquet. So you could be reading any kind of data in different data format, and if you use Spark sessions method like read or read.format.load, now that creates a data frame. But sometimes you may be interested in working on a data where you would want to specify the schema for every field that data has. For example, you have a list which has ID, name, and salary, and what you want to do is you want to assign a schema to it, and that can again be done in two ways. One, you can be creating a case class and then passing in the schema to every field, or you could be using struct field. So here we are doing a dot map. We are selecting every field, and then we are using a struct field which will basically get the data type and apply that to every field. What is a lineage graph? Now, when you talk about Spark, as I said, every step you do in a Spark application, starting from your initialization or starting from using your Spark Contents method, it creates a RDD, and each RDD is like a logical step in your Spark application's DAG, right? So when you talk about Spark application's DAG, it has series of steps which you have coded, which have either a method of Spark context or series of transformation. So this whole DAG is basically like a lineage graph. Now, Spark does not support data replication in the memory. Well, we can have persistence, which can be done. So if you would want Spark to benefit from a RDD graph or a RDD lineage which was already created, then Spark has an internal way of capturing the lineage of your steps. So lineage is basically a flow. So it is also called an RDD operator graph or RDD dependency graph. Now let's look at some Spark streaming questions. So one of the question is, what do you understand by D streams in Spark? So when you are working on streaming data, or when you intend to process streaming data, you would be interested in capturing the data at various time intervals. Now your D streams or discretized streams is basically the abstraction. So what happens is, when you have a continuous stream of data that is coming in as input, coming from some source, or you have a process data stream by some application, this data stream or this input stream is broken down into smaller batches of data, and these smaller batches are called your D streams. So if we see here, we see data from time 0 to 1, 1 to 2, 2 to 3, and 3 to 4. So this is nothing but my D streams, and each D stream is a smaller batch of data on which you would have series of transformations which will be applied based on what you have coded in your Spark applications. Now let's learn about caching in Spark streaming. So if somebody says, what is caching in Spark streaming? So we know Spark does in-memory processing. So does it have caching? Yes. So that is your persistence. So caching is also known as persistence or optimization technique for Spark computations. So basically, when you have your processing happening from one D stream to other D stream, you could have persistence implemented. Now that helps you to save interim partial results so that they can be, if required, reused in subsequent stages. So when we talk about the default persistence level, that is to replicate the data to 2 nodes for fault tolerance. So when you have your streaming and stream processing happening, we can have the persistence of that computation across nodes. Now, one of the main problems which also is seen when you talk about Spark application is operations like joins. So if you intend to do joins across multiple RDDs, one of the problem it poses is that, first of all, the RDDs which you are working on should be like a pair RDD, or what we call as a key value pair RDD. And if you do something like join, then in that case, in every RDD, which is nothing but a pair RDD, or you can say the data within the RDD is in the form of key value pairs. So all the similar keys, and we know that RDDs have partitions, so all the similar keys have to be shuffled across partitions so that similar keys land in the same partition. Now this would be happening on other RDD also, which you would want to join. So you have RDD1, which has partitions, and this RDD1 has key value pair, and all the keys have to be sorted and brought into same partition. Similarly, it will be on the second RDD, and then a join can happen. So this can be triggering a lot of shuffling, which would be happening when you're doing a join kind of operation. Now that could be tackled by using broadcast variables. So basically this one allows the programmer to keep a read-only variable cached on each machine rather than shipping a copy of it. So you could be creating a broadcast variable, and this broadcast variable can be used in operations like join. So this broadcast variable will then be shipped to memory of every node. So if you do a join in two RDDs, one of the RDDs can be broadcasted as a broadcast variable, and when you do a join using this broadcast variable and the other RDD, it will be faster, it will avoid a lot of shuffling, and then you could do your operations more efficiently. So which transformation returns a new D stream by selecting only those records of source D stream for which function returns true? So if we have this question, so the answer would be filter. So filter transformation will give a new D stream by selecting only those records of source D stream for which function returns true. Now, does Apache Spark provide checkpoints? And the answer is yes, there is a checkpointing mechanism which can be used in streaming. So Apache Spark provides an API for adding and managing checkpoints. So checkpointing is the process of making your streaming applications resilient to failures. So you could be creating a streaming context. You could set also a checkpoint path, and you could define a D stream. So when you start your streaming application, it will not only be capturing data at regular intervals based on how your receiver has been set, but you could also have a checkpointing mechanism which makes sure that every computation which happens over a D stream can then be using a checkpoint mechanism if any kind of recovery is required. What do you mean by sliding window operation? Now that's one more extensibility of your Spark streaming. So you can not only do streaming at regular intervals using your Spark streaming context, but then you can also control the transmission of data packets between multiple networks. You could be using Spark streaming for it. So Spark streaming library provides windowed computations. So windowed computations basically means a set of intervals for which the data was received, and you would want to do a processing based, a window based operation. It will look at the last three instances, and then it gives you a window based output. So that's your windowing. Now, what are the different levels of persistence in Spark? So Spark, as we know, whatever steps you create in your application, those steps lead to an RDD whenever you're doing some transformation or using a method of Spark context. But if you are triggering an action, that basically triggers the execution of your application. Now, at certain times, in some steps, whatever computation was done, you may want to use the same computation again down your application. Now, in that case, caching can benefit. So you could do persistence. By default, it is memory, but then you could use all these different options of storage level, such as disk only. So you can have the RDDs or the computations stored on the disk. You could have memory only in a serialized way. So that is storing the RDD as serialized Java objects with 1 byte array per partition. You have memory only, that is storing the RDDs as deserialized Java objects in the JVM. And if an RDD is or cannot fit into memory, it will be recomputed. Now you could have something like off heap. So it works with memory only serialization, but stores the data in off heap memory. You have memory and disk, and you can choose the percentage. So memory and disk basically means the RDDs which are getting created as a part of your application, those RDDs are stored as deserialized Java objects. And if in case the RDD is not able to fit in the memory, additional partitions are stored on the disk. So you could also have memory and disk serialized. So all of these come with storage level, and this is how you can have persistence achieved in Spark, where you would want to persist some RDD computations. Now, somebody might ask you a difference between different transformations, like you have map and flat map. So what's the difference? whether it is Spark Streaming or Spark Core. So when you talk about your map function, it basically, in terms of Spark Streaming, gives you a new D stream by passing each element of the source D stream through a function. So technically speaking, you are applying a function on that D stream which is getting collected or which is getting created. Now Spark map function, what does it do? It takes one element at a time, and based on whatever you have given in your code, it applies that function of the data it takes every time, or of the element it takes every time. When you talk about flat map, it is basically a combination of map and flattening, or it is basically flat map does the flattening. So it is similar to map function. It applies the function to each element of RDD. So your flat map allows returning 0, 1 or more elements from the map function. So it is basically flattening it, or it is splitting your data into individual elements. Now, how do you compute the total count of unique words in Spark? So this is basically you doing a word count in Spark. Now in layman terms, you could take a file. Depending on if you're doing a word count, you would want to split that file and get individual words in the file. And then you would want to write some kind of loop which looks into these words and does a counting of these words if the words are repetitive. So you can load the file as RDD using sc.text file. You could then apply a function to the particular line. So you could be doing a tokenizing, that is splitting your line into individual words. Then you could do a flat map so that you can get all the words split and exploded or extracted from the file. You could convert each word into a key value pair, because you remember we are doing a word count. So we can have a key value pair where key is the word and the value is, say, number 1, which is assigned to every word. Then you could be doing a reduce by key action. So reduce by key action is basically going to reduce the data based on the keys and give you a total. Okay. And finally, you can print the result. So this is how you can do a word count in Spark. So suppose you have a huge text file. How will you check if particular keyword exists using Spark? And that's pretty simple. So you could already be doing a if line dot find and then give your keyword, and you could be pushing it to say -1. You could be doing a return 1 or return 0 depending on what you're trying to do. So here we are creating a function which basically takes the lines, does a map and applies a function called isFound, and then what it does is you want to search for a particular keyword. Now that could also be done using something like starts with or contains. So there are other ways in which also you can search for particular keyword that exists using Spark. Now, one of the important questions is, what is the role of accumulators in Spark? Now, like we discussed, broadcast variables, which are basically shipped into the memory of nodes and when can be useful when you would be using joins. Similarly, when you talk about accumulators, these are variables which are used for aggregating information across the executors. Now, this information can be about the data or API diagnosis, like how many records are corrupted or how many times a library API was called. And you can always look for this information in the Spark UI. So accumulators play an important role when it comes to aggregating information, which can then be used across executors. Let's look at some Spark MLlib questions. So basically, understanding about Spark MLlib or Spark ML library, which is used for machine learning algorithms. So what are the different MLlib tools available in Spark? Now, when you talk about ML algorithms, you have algorithms for different kind of statistical or machine learning problems, like you have classification, regression, clustering, and collaborative filtering. You also have for featureization, that is for feature extraction, transformation, dimensionality reduction, and selection of data. You have pipelines. These are tools for constructing, evaluating, and tuning ML pipelines. That is basically having a set of different algorithms which can be used. You have persistence, that is saving and loading algorithms, models, and pipelines. So you could always be persisting your algorithms. And you have utilities for linear algebra, statistics, and handling. So these are different tools which are available in MLlib in Spark. What are the different data types supported by Spark MLlib? Now this is again a common question asked. So Spark MLlib supports local vectors and matrices stored on a single machine, as well as distributed matrices. So you have local vector, which when you talk about local vector, that's a data type which MLlib supports. So MLlib supports two types of local vectors, which is dense and sparse. So if you would have vector in this particular form, you could create a dense format out of it or a sparse format. And if you talk about label point, which is mainly for your labels or responses, so this is a local vector which is either dense or sparse and mainly associated with label or response. So in binary classification, a label could be just 0 or 1. If you look at other data types, so you also have local matrix and distributed matrix. So Spark MLlib supports local vectors and matrices stored on a single machine as well as distributed matrices. So when you say local matrix, it has integer type row and column indices and double type values that is stored in a single machine. So here we are looking at a matrix of 3x2 size. And if you look in one dimensional array, this is how it would look. If you talk about distributed matrix, a distributed matrix has long type row and column indices and double type values. So it is stored in a distributed manner in one or more RDD. And there are various types of distributed matrix. So you have row matrix, you have indexed row matrix, and coordinate matrix. For data types, you can always go and type, say, Spark MLlib data types, and that takes you to the Spark documentation, wherein you can look at these different data types which we were talking about, like local vector, label point, local matrix, and distributed matrix. And that basically has your 4 different types, such as row, indexed, coordinate, and block matrix. So moving further, what is a sparse vector? Now we were talking about local vector, local matrix, which has dense and sparse vector. So sparse vector is a type of local vector which is represented by an indexed array and a value array. So for example, if we have sparse 1 and you create a sparse vector, so here 4 is the size of the vector, 1, 3 are ordered indices of the vector, and 3 and 4 are the value. So you have an indexed array and a value array which is represented by sparse vector. Now, if somebody asks you, describe how model creation works with MLlib and how the model is applied. So basically, Spark MLlib has 2 main components. It has a transformer. Now that's which reads a data frame and returns a new data frame with a specific transformation applied. Now that transformation could be anything. It could be map, it could be flat map, it could be filter, or you could have other transformations. When you talk about estimator is a machine learning algorithm that takes a data frame to train a model and returns the model as a transformer. So the output of estimator would be a model which could then be tested against our data. If you look at the model creation, and if somebody says how model creation works with MLlib and how model is applied, so Spark MLlib lets you combine multiple transformations into a pipeline to apply complex data transformations. Now, if you look at the image on the left, it says pipeline for training a model. So you would be looking at estimator. So you have a tokenizer, which will basically do the tokenizing or splitting of data. You have hashing TF, and then you are applying a logistic regression model. So this would be your estimator. Now you could have a transformer. So model produced can then be applied to live data. So that is, you have a pipeline model. So you are using, this would be called as a transformer. So you again have tokenizing, hashing TF, and you're applying a logistic regression model. Now, based on this pipeline where you have estimator, so you could be doing a fit method. So pipeline.fit, which will then be working on a raw text. It gives you, say, tokenized output, that is words. It will give you feature vectors, that is where you're doing featureization, and then you're solving the problem using logistic regression model. If you talk about pipeline model, so where we are talking about transformer, so you can say pipeline model.transform, and this basically will work on raw text, gives you words or feature vectors, and finally gives you the prediction. So this is how a model creation and application is done in MLlib. Now let's look at some Spark SQL questions. So Spark SQL is again an important component in Spark when it comes to processing your structured data. So what are the functions of Spark SQL? Now Spark SQL is a Apache Sparks module for working with structured data or data which can be easily structurized. So what are the different functions here? You can load data from a variety of structured data sources. You can then query the data using SQL statement. So you could be having your SQL statements within a Spark program or from external tools that connect to Spark SQL through standard database connectors such as JDBC, ODBC. So you could be using Spark SQL to connect to, say, Hive data warehouse on top of Hadoop. It can be used to connect to RDBMS, and you can get in your structured data, or you could be accessing the structured data which lies on HDFS and then run your SQL queries, which would still be using Spark's in-memory processing capability. Your Spark SQL also provides rich integration between SQL and your other programming language codes such as Python, Java, Scala, and so on. And you can also join RDDs and SQL tables and expose custom functions in SQL. So these are some of the functions, or you can say features, of Apache Spark SQL component. How do you connect Hive to Spark SQL? So we all know that when you work with Hive, Hive would have a Hive-site file, which would have different properties for Spark, for Hive. And this Hive-site file would also have the metadata information, or the location where Hive stores the metadata. And this particular config file of Hive needs to be placed in the config directory of Spark. Now, once you place this Hive-site file in the config directory of Spark, if you would use Spark, either Spark Shell or PySpark, or even running a Spark application, you could directly say spark.sql and then give your select queries targeting your Hive table. So this is how you can be directly working with Hive using Spark SQL. Now, one important question is, what is the role of Catalyst Optimizer in Spark SQL? So what does it do? Catalyst Optimizer, it basically leverages advanced programming language features such as Scala's pattern matching and CASI codes in a novel way to build an extensible query optimizer which is used by Spark SQL. So you would have your SQL query, which is intending to access some data, and that would have some kind of unresolved logical plan to get to the data. Now, you also have metadata, which is stored in case of Hive, which Spark would need to access. So this unresolved logical plan is converted into a logical plan. Based on some logical optimization, you have optimized logical plan. Now, this plan is nothing but your execution path. So these physical plans, what we are talking about, use a cost model, and they select a physical plan which will be used to access the data, which is then used by RDDs, and the code is generated. So this is how Catalyst Optimizer performs or helps you in an optimized way of SQL query. Now, these are some examples here, and this shows how can you manipulate structured data using domain-specific language in Spark SQL. So Spark SQL, as I mentioned, allows you to work on structured data. Now you could be creating a data frame, which is a schema RDD. So you could be using Spark sessions method, which would be reading a file, or you might be interacting with directly Hive. In any of the cases, you would have a data frame. And then on the data frame, you could do a select and select a field. You could be selecting multiple fields and also do some computation. You could be doing a filter or a group by, and all of these functions work very well with your data frames. Finally, let's look at some Spark GraphX questions to see how GraphX helps us in graph-based processing. So what are the different type of operators provided by Apache GraphX library? Now we know that Spark GraphX will allow us to work on graph-based processing. So there would be vertices, there would be edges, and there would be a property graph. So when you talk about different type of operators provided by Apache GraphX, you have a property operator. Now this modifies the vertex or edge properties using a user-defined map function and produces a new graph. You also have a structural operator. Now this operates on the structure of an input graph and produces a new graph. How about join operator? So join operators will basically add data to graphs and generate new graphs. So these are three important operators which are used in Apache GraphX. What are the analytic programs provided in Apache Spark GraphX? So there are some important analytic algorithms provided by GraphX for your graph-based processing requirements. You have PageRank algorithm. you have connected components, and you have triangle counting. You can read about these more by looking into the Spark graphics documentation, where all these algorithms and what they do is explained in a very crisp and a explanative way. So what does the PageRank algorithm do? And you might have heard of PageRank algorithm, which is used by Google or some other search engines. So PageRank basically measures the importance of each vertex in a graph, assuming an edge from, say, U to V represents an endorsement of V's importance by U. Now, what we are doing here is we are looking at two different vertices. We are looking at a relationship between them, and we are looking at the overall graph, which is created by this U and V, and how V is endorsed based on U's importance. So, for example, if a Twitter user is followed by many other users, that handle will be ranked high. So we are looking at a connection where one Twitter user is followed by many other users. Now, internally, when you talk about PageRank algorithm, you can understand this by looking at or thinking about what Google does. So where you could have multiple pages which are being searched, and each page is initially assigned a rank. And based on the searches, based on the possibility of a page being found, every time the rank is incremented. Now that's how page algorithm works. So these are some of the important and critical questions when it comes to your Spark role-based interview. You can also look into other aspects of Spark, such as partitioning, different kind of partitioners which are used. Look at Spark data frames and data set API and what are its capabilities. Look into Spark MLlib and how you could have your code written in Scala or Python to solve ML problems or building your machine learning algorithms for different statistical requirements. Or also look in Spark graphics, where you can build graphs out of your data and then basically use that for graph processing.
I hope this helps you in your interview. With that, we've reached the end of the complete Apache Spark tutorial. I hope you enjoyed the video. Do like it and share it. Thank you for watching. Keep learning and stay tuned to Simplilearn.